for the time, the block. Oh, this is fun. This is for, okay, this for the, so I have the computer. Okay, everything okay. But the boss got very yeah, we deliver the hotel. Five with stuff. Was it? The boss is coming?
It's not yet here, so they told me to wait until 97.
The boss?
No, because there is no power, which is still coming. One of the buses. So we have to wait for it. So I was checking, but they told me that it's supposed to arrive in a few minutes, so probably at 97. Here. She did that the bus.
The bus is here? The bus is here?
I don't know, but you can start because we are
Yes, good morning. Good morning, everybody. Just to say that we are waiting for the last bus is arriving now, and maybe also you could come a bit closer. It's a bit empty in front.
so the people that come, they always sit in the back.
Yeah.
Otherwise, nobody wants to do it.
Okay.
Sorry, they arrive now. They arrive here in front of the. Okay.
According to this clock, because maybe different people. So also probably my work.
I have to check my phone and check the time. It's exercise to make 1 minute.
Yeah. I know I was talking during the coffee break with some of the speakers, and they were worried that they may not make that 10 minutes. And look, I mean, but you have 10 minutes. This is part of the game, so you have to be able.
Again, 10 minutes.
Yeah, unfortunately, at the end of the year, because I have to leave. I have another meeting tomorrow morning, and I have to take a flight at 6, which means I have to leave from here at 4 or even later. So I will not get some time for the recommendation session, so we will make a presentation. I want to prepare the draft. Because unfortunately, I have to stay tomorrow, to be tomorrow, but I have to. And my only direct flight was at 6, otherwise I have to go to Madrid.
Yeah. So I have my flight tomorrow morning at 8 o'clock, 8:30. So we leave from Frascati.
But you have direct flight.
Yeah.
I try to get direct flight, otherwise.
Spend half of the day like yeah. Okay, so
we will
7.
start.
So please take your seat. We will start in 1 minute. I take this
We can go one, then I take the second one.
second one. Okay. Okay, let us start the session this morning about droughts, pests, and other stressors. But we have 4 talks about the droughts and 2 talks about the pest. And then each of you will have 12 minutes, including 1 question. And at the end of the session, we will have a little time for discussion. So, my name is Thuy Le Toan from CESBio Toulouse, France, and my colleague, Professor Moreno, you present. We are sharing the session together. Okay, so go to right to the first talk, EO for Syrian stress. It will be presented by Booker Ogutu. Okay, thank you.
All right, thank you for that introduction. So my name is Booker Ogutu from the University of Southampton. I will present the EO for Serial Stress project that is being undertaken by a number of consortium members. You can see listed there. Some of the consortium members are in the audience. However, before I go into the project specifics, it's first important to provide some background. And as you all know, we need to increase food production to meet the growing global population. But crop production is subject to multiple biotic and abiotic stressors, which can reduce crop yield. And with expected climate change, there's expected increase in frequency and severity of these stressors. Therefore, there's a need to develop methods that can be used to monitor and detect the impacts of these stressors, both single and compound stressors. So the aim of the EO for Serial Stress Project is to use multi-source Earth observation data and in situ data to understand the effects of single and combined stressors. A secondary aim is also to develop products that can be used to monitor these stressors and provide a scientific roadmap for future development of EO products aimed at monitoring stressors. So here is just an overview of the project framework. So basically, we'll be collecting a number of field data from pilot sites and also acquiring a number of satellite data and also airborne data, UAV data, and such. And then we'll put this data through a number of processing methods, including empirical regression methods, machine learning methods, and radiative transfer methods, with the aim of detecting important bands or combination of bands that can be used to detect stressors. And then we'll develop new algorithms out of this that we can then, that we'll then use to generate experimental products, which we will evaluate in other sites that we haven't done our work, and eventually we'll produce a scientific roadmap with open questions and where there needs to be investment to make this kind of monitoring a reality. So we have a number of sites. The first pilot site is Andalusia, Spain. It's a rice farm, and this work is led by our consortium member from the University of Sevilla. And here we are focusing on a number of stressors, so salinity, nutrient deficit in soils, and toxicity by heavy metals. So we've so far collected a number of biophysical and biochemical variables and soil properties from the field, and also acquired a number of satellite data. So some of the preliminary work that has been taking place at University of Sevilla include developing predictive models for monitoring or for generating soil parameters or soil stresses using field data, UAV data, and satellite data. And there's a number of tasks that they've been undertaking, for example, identifying sensitive bands or band transformations, and also evaluating a number of machine learning algorithms using the framework that is shown here on the board, on the screen, where you have things like undertaking dimensionality reduction, hyperparameter tuning, model deployment, and evaluation of the models. So they've also evaluated or tried to generate around 21 soil properties. So as an example, these are some of the best performing models for this example, four example parameters. So we have here electrical conductivity, soil organic carbon, nitrogen, and iron. But the goal is eventually to generate maps from those best performing models of the spatial representation of that particular soil parameter, and then link that soil parameter to biochemical or biophysical variables of your crops to be able to detect the impact of stresses. So that's just an example of work that's going on in Sevilla. The second pilot site is the Bonifique farm. This work is led by ITC, University of Twente, and here the key stressor that we are looking at is lodging in wheat. And lodging, for those who haven't come across it, is basically just the displacement of stems from their upright posture. And at this site, again, we've acquired a number of EO data and also collected several biophysical and biochemical variables. And on top of that, we've developed some derived variables such as crop angle inclination, lodged area, and the key index there, the lodging score index, which is what we use to determine whether a plot is lodged or not. So some of the preliminary work that's going on there is we try to look at the spectral pattern of lodged and healthy and severely lodged plots to see if there's any spectral bands that can be used to distinguish between lodging and unlodged plots. And you can see here in ASD spectral measurements, NMAP measurements, and even Sentinel-2, the near-infrared and the shortwave infrared seem to be hinting at some useful information contained there that can be used to detect lodging. Additionally, we've generated these heat maps looking at trying to determine which combination of bands can be used to detect lodging. And again, if you look at those plots for all the various data, you can see that the vegetation indices that use shortwave infrared and near-infrared band seem to be much more related to lodging score, which is our lodging stress index. So the next thing is basically to then develop some kind of models that we can use to then map lodging stress in the fields. And here we just try to use a partial least square regression model using all the data from all the reflectance data, some significant bands, and also a number of vegetation indices. This is just a scatter plot of the results that are coming out of testing that particular model. And then again, the goal is to apply it across the field to generate a spatial representation of lodging score across the field. The interesting thing here is that even though these two maps are from NMAP, and the Sentinel and the spatial distribution look quite similar, even though you have more spectral bands in NMAP compared to Sentinel, which means the low spectral bands of Sentinel doesn't diminish its ability to detect lodging stress, at least in considering these initial results. The final site that we are working at is the Matchfield region in Lower Austria. So this is a kind of considered a semi-arid region. And here we are looking at water stress in maize and some wheat. And again, we've collected or acquired a number of data sets, EO and meteorological data sets, and some field data sets, and also we'll be using some historical data. So some of the tasks that's going on there, first of all, they're developing some machine learning-based methods of predicting dry conditions in this site. The aim basically, because they want to use also historical data to detect impact of stress, of water stress on maize and wheat. So therefore they need to kind of look at the find a method of generating historical dry conditions, and they're trying to do that using machine learning methods. And so they've just evaluated a number of models, and here's just the ROC and AUC plot for the outcome of the models that they've tested to see which ones would perform well in predicting dry conditions at this site. So just to summarize, so what the project is expected to produce is basically experimental data products from the pilot sites, and also new stress detection algorithm. If we can do combined stress, the better, but we will see. and also do some impact assessment at a large scale for just test the models or methods where we didn't pilot them to see how well they are doing. And eventually, we hope to generate some scientific roadmap with knowledge gaps and urgent scientific questions, potential EO gaps, and recommendation for in situ observational gaps. And with that, I thank you for listening.
Okay. Thank you for keeping the time. We have time for one question. If not, just I have one question. Your models derive in a pilot plot. Could you think that it can be applied to other sites?
Yes, so that's one of the tasks that we will do is to then apply these models in other sites to see how they perform, just to check in other sites. We have partners in Canada who are going to actually undertake this check on our models with what they're already doing in Canada.
Okay.
Thank you.
And so for your recommendation, it's that you put in the scientific roadmap is that to have to fill the gap in knowledge and urgent scientific question, potential EO gaps, and in situ observational gaps. You say that the roadmap to fill those gaps, but you don't know how. You don't say how.
Not yet, because the project is just I think it's the 7th month.
Yeah.
So we will generate this roadmap once we kind of close to completion of the project. So now this is one of the aims of the project is eventually towards the end of the project we'll have learned some lessons and include those lessons in the scientific roadmap.
Okay, so thank you very much. And
Thank you.
okay, it's time to pass to the second one.
Yes, the idea is to have only one or two short questions for each presentation in order to give time at the end for some general discussion at the end of the session. So now we will move to the second presentation that will be given by Olin Hia from the University of Strasbourg. And the title is Assessment of Multi-Source Agricultural Drought Indices, Sensitivity to Soil Moisture Variability in Africa.
Thanks for the introduction. Good morning, everyone. My name is Olin Jia, and I'm from Luxembourg Institute of Science and Technology. Today, I would like to introduce our work in African drought. And basically, we did a comprehensive evaluation of different drought indexes in Africa. And then we proposed a new drought indexes using eco-stress data. As we all know, agricultural drought is a long-term soil moisture deficit that harms crops. However, in Africa, there are very limited soil moisture ground sites. And currently, we don't have the high-resolution soil moisture remote sensing products. So, but we have several drought indexes which developed from models like the SWIR band or thermo-infrared band. But they are not evaluated in Africa. But in recent years, we have eco-stress data, which provides high-resolution LST. Compared to Landsat LST, it has a unique feature that it can capture the LST from different time in the day, which can give us a high-resolution diurnal temperature range. This is the new information we can get from this new data. So we want to use this advantage to propose a new index. So it drives out the first research question that what are the sensitivities of the traditional drought indexes to soil moisture at different land cover types and crops in Africa. So in this study, we select 6 drought indexes, including 2 microwave products from NASA SMAP and the Copernicus Soil Water Index. And also, we include a meteorological drought index, which is called KBDI, and it includes precipitation information and air temperature information. And also, we include 3 models-derived drought indexes using shortwave infrared band, including NDWI, STR, SDCI. And we use 33 sites, soil moisture sites from RSMN in Africa to the evaluation. And here's the site map. Here is the scatter plot of 6 drought indexes compared to the soil moisture. Here's one representative site. We can easily say that, of course, the soil moisture products from microwave data perform the best, and its correlation is close to 0.9. But the problem is the microwave-derived soil moisture products currently has a relatively coarse spatial resolution. And in comparison, the third one, the KPDI, the third one only works in the drought season, which are marked as red. And compared to the 3 MODIS-derived drought indexes, the NDWI performed the best. And initially in this study, we also include the EcoStretch ESI products, but it has very limited sampling numbers, so we want to try. So it makes us to derive the second research question: how can we make the EcoStretch data more feasible to drought analysis? So in the second research question is we want to try to improve the feasibility of the EcoStretch data for the drought monitoring. So in the first step, we recover the EcoStretch LST because it is, has a cloud cover or the low refrequency. So we make this continuous EcoStretch LST, and then we propose a new drought indexes based on the new diurnal temperature range information. And this diurnal temperature range information help us to drive us to use the apparent thermal inertia, which is a very classic drought indexes. And this ATI is mainly derived from the temperature range and the energy we received in the morning time, the solar energy. So the physical interpretation of ATI is that how many energies do you need to increase 1 degree in this area? So if this is very dry, it's easier to get the higher temperature range. And if it's like this figure showing, like forest site, it has a very small diurnal temperature range, and it needs more energies to increase the temperature. And then we apply this ATI index in different sites, and then we found that it performs very well in semi-arid and arid regions, but the correlation coefficient decreased in vegetated regions. So we wanna fix this problem, or we want to improve this situation. So we propose our new drought indexes, with the equation is here. And we kept the basic form of the ATI index, and the bottom is the temperature difference, and at the top it is the energy received from solar radiation and also the atmospheric long-wave radiation. But more than that, we include a correction factor. This correction factor, it is an exponential form, and it includes the precipitation and NDVI, which means this exponential form is close to 1 when this place is dry and there's a limited vegetation cover, which means it can keep the high performance of the traditional ATI. But if there is more vegetation or more precipitation, this correction factor can help us to improve the performance of the traditional ATI. And regarding the evaluation method, we collected the soil moisture data from site, and here's the soil moisture in different years. We remove the seasonal cycle, and then we can get the soil moisture anomaly in different years. We can see after removing the seasonal cycle, we can capture those very low soil moisture anomaly cases. And we do the correlation coefficient comparison to see which drought indicators has the most sensitivity to the soil moisture anomaly. And in the next slides, I will show the reconstruction of RST accuracy. And the reconstruction of the RST help us, first, we can better to compare the noon time and midnight time RST at the same time. And then it also helps us to remove the seasonal cycle to help us to detect the soil moisture anomaly. And the left figure is the daytime validation accuracy, and the nighttime, and the right figure is the nighttime accuracy. And overall, the accuracy is slightly lower than the clear sky retrievals, like 0.5, 0.6 lower. But we think it's sufficient for us to remove the seasonal cycle to capture the anomalies. And here are the 4 representative sites, the scatter plots between soil moisture and the ATI and the RATI. We want to, using these 4 sites, we can explain why the revised ATI works better than the ATI. If we focus on the white site, as example, the second one, the crop site, the blue scatters are the traditional ATI results. And we can see that below the soil moisture less than 0.2, the correlation between ATI and soil moisture is pretty high, and has a direct positive correlation. But when the soil moisture is larger than 0.2, the correlation or the relationship between soil moisture and ATI is saturated. And if we focus on the orange samples, which is revised ATI, it kept the high correlation at the arid region, but it enhanced the performance when the soil moisture is larger than 0.2 because of the correction factor. So that's the reason why the RATI is performed better. And the saturation issue is because when the soil moisture is high, this LST increase is mainly controlled by the radiation rather than the surface condition. So that's the reason why there's the saturation effect. But after we include the correction factor, this saturation effect has been minimized. And also, we remove the seasonal cycle, and we compare the different drought indexes with the soil moisture anomaly, and then we plot this scatter plot. This is a correlation statistic at different sites, and we draw this figure along with the NDVI, which is the x sites. We can see first of all at the arid and semi-arid regions, which NDVI is close to 0.3, the correlation is very high, it's larger than 0.8, but slightly when the NDVI is increasing, the correlation of the blue scatters, which is ATI, has decreased. But compared to the rest samples, which is RATI, our new index perform always better than the blue scatters. And also, we classify the statistics into based on the land cover types. The first figure is the overall statistics, and also we compare with different drought indexes. The RATI, which is the right column, always has the highest performance compared to the traditional drought indexes. Also, no matter in crops or grassland or savanna. So overall, so in summary, we propose refined drought indexes, and this is the first study that using eco-stress data to monitoring agricultural drought at a high spatial resolution. And we also proposed a new eco-stress LSC reconstruction method. So and of course, it includes a very important temporal sensitivity analysis of different drought indexes to soil moisture deficient in Africa. Thank you.
Thank you. We have time for some questions.
Yes, please.
Please wait for them.
Thank you.
Maybe this will be a bit too technical. We can maybe discuss later. But I was curious how you derived your correction factor. Like I saw 0.05 as well. And also clarification on your final chart with the box and whisker plots. So you say the RATI is higher than all the other ones.
Oh, the SWI is the microwave.
But that has coarse resolution, basically.
Yes.
Yeah. Thanks.
And this correction factor, what's your question? It's a.
Yeah, where does that form?
I created this form. Yeah.
How?
Because first, based on the evaluation, the thermal-based drought index works really well in arid and semi-arid regions compared to NDVI or NDVI-based drought indexes. But the correlation or the performance slightly decreased when the NDVI increased. So we want to try to mitigate this situation. So we want to increase, because NVIDIA will perform slightly better in those kind of conditions. We want to integrate this information together rather than solely using the thermal information. But we want to keep the high performance of the thermal infrared LS diurnal temperature, those kind of contribution. So how can we keep this kind of information at arid and semi-arid regions, but we introduce additional information at vegetation regions? So we introduced, I just came out exponential form. It's exponential form when the precipitation is in the arid and semi-arid regions, when the precipitation is very low and NVIDIA is very low, the exponential form will like close to 1, right? So in that case, it will not affect the performance of the thermal infrared, those kind of information. But when the vegetation is higher, and also there could be rainy season and there will be more precipitation, and then this beta correction factor will work, and it will increase additional information to the equation and increase the sensitivity of this index to soil moisture. That basically is the logic. To try to take the advantage of thermal and NVIDIA together. Previously, there's another drought index which is called SDCI. This is the weighted average of the PCI, VCI, and TCI. And this factor uses the same information compared to my new drought index. But the problem is, like as the drought regions or semi-arid regions, the weight of the NVIDIA is still high. The weight cannot be changed. It's always like the 0.5 from the information. 0.5 is from 50% from NVIDIA. But the NVIDIA at the arid regions, the problem is the signal noise ratio of NVIDIA at arid regions is low, and the accuracy of NVIDIA itself is limited in those regions. So I think that could be the reason why the NVIDIA does not perform well in these regions, but the thermal information really helps in those regions. So we just combine the strengths of different indexes into I would say physical form. Yeah.
Okay, thank you for the very detailed explanation, but unfortunately we don't have more time for questions right now. We will have a discussion at the end of
thank you.
Of the session.
Okay. The next talk is by Gohar Gavardhan on national scan drought impact and risk assessment with the use of Sentinel-2 and Sentinel-3 time series. So thank you.
Thank you for the introduction, and good morning from my side. My name is Gohar Gavardhan from Leibniz Center for Agricultural Landscape Research, and I'm really happy to be here to present the first results of ADM Kenya project, which focuses on agricultural drought monitoring in Kenya with the use of multi-source remote sensing data. The consortium consists of several organizations from Germany, that's TALF and Remote Sensing Solutions, as well as 3 key Kenyan organizations, namely RCMRD, ISIPE, and the Ministry of Agriculture and Livestock Development in Kenya. ADM Kenya is a part of the EO Africa National Incubators Initiative, and our main aim is to co-develop solutions to monitor crop condition and cropping systems with multi-source Earth observation data, and to have evidence-based quantitative vegetation condition estimates. And here the keyword is the co-development. From the inception of the project, together with our partners, we looked at the user and policy needs to formulate the main products that are needed for national scale agricultural drought monitoring, develop several workflows for that, and we didn't stop there. So one of our main focus is also to continue with cloud integration and publication of all data sets and bringing back all of this output to our users. But before looking at the main products, just let's have a quick look on why Kenya was selected for this project. Drought conditions in Kenya have been a persistent problem for many communities, especially those that rely on agriculture for their livelihoods. There were several prolonged drought events. You can also see on the table the FAO statistics for several years where we could see negative yield anomalies, but also I'm sure many of you have seen several news reports talking about the multi-season drought events in the recent years. Considering the issue and the discussions with our users, we came up the following solutions to improve drought assessment. The first one was improving the currently used drought assessment methods with the use of new datasets, such as integration of Sentinel-3 data, and also develop methods for high-resolution drought impact monitoring with Sentinel-2. And here we focus not only on drought hazard, but also drought impact and risks. Then, when considering drought risks, vulnerability and susceptibility to drought is a really important factor, so for this we need contextual information. This is why we also integrated frameworks to map different cropping systems, particularly focusing on rain-fed and irrigated systems, and also mono and mixed cropping systems. And the last focus for our project was validation of our approaches. So many drought assessment activities do not include validation. So we made sure that we have in situ data, but also collect all the other available data, and also integrate a new validation approach, which I will talk about in a second. So yeah, as mentioned, we really focused on the validation of our products. We had direct validation with the in situ data collected in the field from 2023. For those products where we don't have data, for example, drought events from the previous years, we used all available data, such as yield anomalies or other products, such as evapotranspiration from vapor, to compare the spatial and temporal consistency of these products. And to my opinion, the most interesting validation was the user-based validation, where we send our products to our users with questions regarding the accuracy and applicability of the products. And based on their feedback, sometimes we had to revise either the specifications or implementation approaches, and then brought back the version 3 or version 4 of the product back to the users. Now, let's look at the products that we developed. I will start with the high-resolution crop condition assessment, where we used Sentinel-2 data together with phenology and land cover information to have high-resolution crop condition maps. Our assumption here is that during the drought and non-drought years, we will have, during the drought years, we will have deviations from the normal phenological development, and knowing these drought and non-drought events, we can we can generate training data and get the crop condition output. But considering the complex cropping patterns in Kenya, namely the bimodal cropping practices with 2 growing seasons during the long and short rain seasons, we have to do season-based stratification, and also we had to train the model for each agroecological zone. Here you can see the output for long rain seasons for 2018 and 2022. 2018 was a near normal year, so with also with our output detecting not so much affected croplands, but 2022 was a severe drought year, and we can see almost all croplands were affected. You can also see the accuracy metrics. The accuracy varied depending on the season and the agroecological zone, but we have quite good results in semi-arid and arid zones, with slightly less accurate results for transitional zones, which is due to also complexity in these systems. So I will move on with the next product, which is the national scale irrigated systems mapping. And with this product, I will also show how the user validation shaped our product. So initially, we used Sentinel-2 with manually curated thousands of training data collected, used harmonics, and then with a machine learning model, predicted the irrigated rain-fed systems. The product was sent to the users, and the feedback came that we have to improve our product, which led us to add more data, such as evapotranspiration and land surface temperature, and also run some post-processing steps. This led to the national scale map, which has a very high accuracy based on Sentinel-2 data, and also very high accuracy and applicability score from our users. Quickly moving to the next product, which is the downscale evapotranspiration. Here we combine Sentinel-3 land surface temperature with Sentinel-2 data using two-source energy balance model and machine learning methods to downscale ET. And here we use the intercomparison with other products. You can see the comparison with vapor evapotranspiration and with GEOGLAM evapotranspiration. And we can see quite nice agreement, for example, with the time series with vapor data. But here the complexity is that the data sets have different spatial and temporal resolutions. So one of them is only decadal. We provide data for every usable observation available over Kenya. And the examples are from one county, Busia, but we provide this output also for the whole Kenya. The last product that I will talk is the spatially transferable national scale drought risk assessment, where we used Sentinel-3 data together with MODIS data and other data sets such as precipitation to derive relevant metrics such as different indices, standardized precipitation index, to calculate anomalies which will be the basis for the drought hazard. But again, reminding that the drought risk is depending also on the vulnerability. We use the irrigation maps that you have seen a few minutes ago, and also some other data sets such as GDP, farming animal density, population density to have the vulnerability and at the end the agricultural drought risk. We combined both MODIS and Sentinel-3 data to have longer time series to train the models. And here you can see the example based on the sensor offset was tested for 30,000 pixels, but you can see the example from 2 locations where we can be sure that we have the continuous time series from these 2 sensors, and we can ensure this long time series. And yeah, we have the national scale product. Again, the example is from 2018 and 2022. You can see that this product gives more information because it's not focusing only on croplands, but it also includes rangeland areas. And we have this product at the monthly level, and together with the static vulnerability and the hazard, which is monthly scale, we can have monthly drought risk product at a 1 kilometer resolution. During the project, we had several activities with the users. That was the user need assessment, validation meetings, which were both offline and online several times. Field data was collected for a pilot area for mono and mixed cropping systems, which is now underway. And we also, together in the consortium, we prepared policy report, which will be also published next week during our user workshop in Nairobi. And just some discussion points from my side. I think I convinced that the integration of multiple datasets allows derivation of valuable, spatially explicit information on drought impacts and risks. And we see very high potential for direct uptake and implementation of these methods and the project results into the stakeholders' operational systems. And some recommendations / challenges from my side. So contextual information is needed. A few days ago, many people talked about irrigation systems mapping. I would add here also mono-mixed cropping mapping, not at a pilot level, what we did, but a larger level, preferably national scale, for which we need in situ data. Then remote sensing does a really good job getting pixel level information about crop condition or drought hazard, but still for vulnerability, the indicators are often aggregated to national or administrative level, so this is a challenge. And we need, when we talk about food security, we have to think about multiple hazards and cascading effects. Here you can see the shocks of the agricultural production in Kenya. And you can see that each drought is followed by flood, and then drought again, and then flood. So we have to consider these effects of different hazards together. With this, I would like to thank you for your attention. And if you have any questions, please feel free to ask.
Thank you much. Is questions to the speakers?
There is
one question there. Okay.
Thank you very much for your presentation. My question is, what informs the resampling decision, and does it influence the replicability? Thank you.
I think your question refers to the this mix between the Sentinel-3 and Sentinel-2 data. So, we need to do this because with Sentinel-3 we get the thermal information. With Sentinel-2 we have the higher resolution with several bands. So we have to do it to have this high resolution at the end product, for example, for ET. We do validation, as I mentioned, so we are quite sure on our output, and actually resampling and giving the high resolution output increases the applicability score that we get from our users. So that was also a green light to us that we can do that and we should do that. But we can also discuss later during the discussion.
We can discuss later, but it's interesting if you compare and you reset the MODIS and Sentinel-3 in order to have a historical data, time series, long time series. Very interesting. Thank you.
Thank you.
Okay. No other questions, so go to the next one.
Okay, if there are no questions, we will move to the fourth presentation. It will be given by Sergio Contreras, and the title is InfoSequia Forecast, enhancing impact-based seasonal forecasting by combining EU-based drought indices, climate data, and decision trees ensemble techniques.
Good morning to everybody. I'm Sergio Contreras, working on Future Water. It's a small research consultancy company hosted in the Netherlands, in Wageningen, and also we have a small office in Spain, in Cartagena. Thanks to the organization for the invitation, the opportunity for presenting our service. And also, I would like to acknowledge also my colleagues Alicia Grunskova, Amelia, Gaby Nobre, Marta Wens, and Hai Simons that were actively involved during the development of this project. Well, this is InfoSequia. InfoSequia is the operational drought monitoring and impact forecasting service that is being developed by Future Water. We started with the project several years ago. And thanks to the funding received from the InCube program from the ESA, we were able to improve the forecasting component of this drought monitoring system. That basically consists of what does is combine different sources, different type of data from different sources and sensors with climate data and also with cloud geoprocessing techniques and machine learning techniques for providing these seasonal outlooks of impacts, actionable alerts that can be used for institutions that need to provide anticipatory action. So basically, InfoSequia has three components: InfoSequia Monitor, InfoSequia Forecast, and there is another one, InfoSequia Viewer or Dashboard, through which all the data is shared with stakeholders and users. Basically, what we do in InfoSequia is try to collect all the information available in the cloud and also ground information at the national level for generating different drought indices that after are used as potential predictors and are ingested in our forecast algorithms for providing these seasonal outlooks of impacts. We are focusing on very site-specific monitoring and forecasting at the district level and the basin scale. We are not working at the higher spatial resolution. And the idea is try to, co-develop and co-design. I would like to highlight this. In InfoSequia, the system is fully co-designed with collaboration and the implication of the stakeholder from the beginning. So all the training and activities related with the system is completely developed with them. We started to be in contact with the World Food Programme in order to evaluate the real needs for this type of solutions. And we surveyed them through different questionnaires, and we identified real real needs from them that encourage us to implement InfoSequia in their current workflow chain. Basically, what we program in Mozambique, because we were piloting the InfoSequia system in Mozambique, require us actionable information of expect crop yield failure at the end of the crop growing season, timely and reliable information using, if possible, a simple and intuitive forecasting technology, and all the data should be shared through a user-friendly way, through bulletins or a dashboard with easy functionalities for accessing the data. Well, the pilot implementation was in Mozambique, in 2 provinces, Gaza and Tete, and the objective of the project was to try to deliver monthly bulletins that generate this or inform about this crop yield failure or the probability of crop yield failure at the end of the growing season. The harvesting month was set in May, and we used the maize as a model crop for implementing the survey, for training the algorithms. Due to the lack of ground truth data, crop yield is a difficult metric that is not always available in data-scarce regions. We decided to use a surrogate indicator, the water requirement satisfaction index at the end of the season. This index is generated using a crop model that is forced with precipitation and evapotranspiration data, and also consider the crop development of the crop development phases of the maize. And we started to provide, or the idea was try to provide seasonal forecast with a lead time up to 6 months before the end of the season. So basically, InfoSequia forecast has different machine learning techniques implemented. Here I'm presenting what is related with the fast and frugal tree. It's one of the technologies that we are using. And we are constructing forest from these trees using an ensemble technique, a parallel ensemble technique, in order to provide also metrics of probability of failures, and also in order to provide more information about the uncertainty of the probability of failure. So this working with forest is a huge advantage in order to try to reduce or evaluate how certainty is we are providing, or accuracy are providing. So basically, the InfoSequia forecast techniques consist of 3 steps. One is related with the data preparation, in which all the information collected from different sources are integrated into the model and harmonized. Also, we are applying different algorithms for enhancing the current products that are available in the cloud or in different platforms. All this pre-processing is done through this data preparation phase. We generate the predictors that will be used, and also we define and quantify what is the failure. That is a binary output, 0, 1, okay, based on this water requirement satisfaction index, adopting a threshold-based approach. After that, in a second step, we run different, we tune and train the model, looping over a hyperparameter space in which we are using for hyperparameter variables, and all these variable parameters are saved, are generating different trees, different models that are saved after for testing the performance of during the validations subsets of our period of analysis. When we select the best model from this training, tuning, and training validation periods, we test again the performance in a whole-out sample for evaluating the performance of the system without any disturbance or noise during the training and validation. Well, some results, in general, what we did in Mozambique, because we have a very short period with information about the water requirement satisfaction index. We started in 2006, probably it's a very short period for training a machine learning technique. What we did was try to work, train the model at the province level. And once the model were trained and generated, we applied this model at the district level with the predictor generated at this level of information. Well, here you can see several performance indicators generated during the hindcast at the district level. In general, well, we are really happy with the performance of the system. For the different provinces and districts, we were able to get good performance metrics that inform us about the accuracy and the certainty that we assume. Another thing that is important that increases the transparency of this type of technologies is the ability that we have for evaluating the relative importance and the relative contribution of each potential predictor in forecasting the outlooks and forecasting the yield failures. For example, in this particular case, you can see what are the most important predictors that are used in each lead time for doing the prediction of the crop failure at the end of the season. And you can see, for example, in green, that you have those predictors that are related with the greenness, the land surface temperature, and the vegetation health. All this indicator has a better or a higher contribution during the first lead time in November, December, at the beginning of the crop season, while climate indicators related with the oscillation, the atmospheric oscillation indices, like NOAA or the dipole mode index, have a more importance during the rest of the year. So this type of technologies allows us to evaluate the performance of the system itself and contribute to better interpret the result that we are providing. Well, here you can see a heat map with the probability of failures for a particular district in Gaza for the hindcast period that covers from 2006 to 2022. And in the right, you can see a 0 month in May is the failure, no failure, the binary condition that we generated for this province based on the water requirement satisfaction index. And in the left side of the plot, you can see the probability of failure, and the dot represent when a trigger in the probability of failure is exceeded, and this trigger represents the probability, well, I can explain after, the probability in which we have a good performance for different metrics, statistical metrics, in order to evaluate this.
Can you up, please? Yeah. Can you?
Yeah. So some results in operational implementation from 2022 to 2 years ago. At the end, we are providing this type of maps at the district level, where you can see for different districts when we are delivering a recommendation for action. And all this information also is provided through bulletins to the stakeholders and through a dashboard where you can quickly evaluate all the outputs from InfoSequia, the monitor indicators, the drought indicator, the drought indices, and also the results per month and district about these seasonal outlooks of impacts that you can see in dots red. Well, message, I can jump ongoing. We are evaluating other machine learning techniques like string gradient boosting. That preliminary result seems to reflect that provide better performance than the FFT. Also, we are evaluating compound hazards, dryness heats, and the combination of statistical and dynamical forecasting is something that is one of the next steps that we want to develop. We are doing also some benchmarking, upscaling, and stakeholder involvement in other regions in order to increase the implementation of the system. Recommendation, well.
Okay, so can you wrap up, please? Yeah.
Ground drought, I totally agree with my previous presentation.
Okay.
So thanks.
Thank you very much. We have no time for questions, so we can ask you questions during coffee breaks, yeah, or during the discussion. Yeah. Thank you. You are me. Oh, I'm okay. So the next talk will be given by Fatima Della Believer. Thank you. Yeah. Okay.
So, hi, good morning. Thank you for the intro. My name is Fatima Della Belluer, and I'm going to show you the work that we have been doing from University of Valencia, which is based on the study of the mealybug pest through orange trees. It works or not? Yeah. There is a problem to solve. Well, there are many, but in our case, our challenge is called cotonnet de les valls. It's a mealybug insect that, despite its little size, is causing serious economical losses in the agricultural sector in Spain. So there is a necessity to monitor those control methods that sometimes are not perfect. And we suggest the use of remote sensing to assess this problem. We have two main objectives in this study. First one, the characterization of the incidence of the mealybug by using remote sensing. And the second one is to analyze if we find or not a separability between healthy and affected fields. Both objectives will lead us to a final goal, which is to develop some remote sensing monitoring tools, because we encourage that transferation of knowledge. We want to empower the agricultural sector. Our study zone has been La Vall d'Uixó, as it is the zero zone. In 2018, the pest appeared there, and in this graph, we can see a classification, a ground truth, from 2020-2021. We have affected plots in red and healthy fields in blue. About the materials that we used, we use the imagery from Centulake processor, as it fuses Sentinel-2 and Landsat data and increases the temporal frequency that we have. And we are working on a Sentinel-2 scale at 10 meters. About the period that we used, it is from 2017, 1 year pre-plug, to 2022, 1 year post-classification. And regarding the spectrum regions in which we focus, we use the red, the near, and the shortwave infrared because of their relationship with several biophysical parameters of interest, as are the chlorophyll content, the volume, and the water stress. And of course, we also use the NDVI. Then, before explaining the methodology, I would like to highlight the paper of BRDF correction here, because when doing a first study of the surface reflectances, we detected in the evolution a seasonality behavior, which we thought that could be due to BRDF effects. So these BRDF effects are linked to the solar zenith angle, and we can see in that graph how surface reflectance is related with solar zenith angle in this case. So we corrected this effect by using the BRDF algorithm ABA, and this reduced that seasonality. Regarding the methodology, it's quite simple, just making a spatial means and the standard deviation of each plot, dividing this plot into groups, healthy and affected one, and start playing with those parameters, with those mean. First of all, we also effectuate surface reflectance evolutions, and the seasonality is still here. There is maybe a remaining angular effects, or maybe it's due to the phenology. Then we also made differences between means of healthy and affected plots. And here we are showing the SWIR results, which are the most significant, and we see a negative tendency. This negative tendency is maybe due to an increase of stress in the affected fields. Then we collect all that means into monthly collections and evaluate linear regressions in each month. Here I'm showing the slopes of each month, and I'm also highlighting the SWIR because we can establish a slight first separability between healthy and affected fields, especially in the second part of the year. And I have to say that visible effects of the plug are, the effects of the plug, are visible mainly in the second part of the year, at the end of the year. So maybe we are going in the good way. Also, we made an anomalies study comparing each month of each year with respect to 2018. And at first, what we can see is that there is more dispersion in affected fields, which maybe makes sense because a pest advance is not homogeneous. And we also see more difference between groups in the second part of the year, in the time that I told you that the effects of the pest are visible. So I would also like to highlight the 2020 year, because in this year we started seeing differences between healthy and affected plots. Maybe I can use this. Okay, here we have negative anomalies, which are related to pest presence. So comparing with the bibliography that we found, in this year, mealybug pest started to developing a lot. So that also makes sense. And in 2022, we have a negative anomalies increment, as you can see in the affected graph, which is also consistent with the bibliography that says that the pest increased from 2020 onwards. So one thing is that I'm just showing the results of the SWIR because I just have 10 minutes, but we can discuss it later. And from these anomalies studies, we maybe can establish a first general criteria to characterize those affected plots. That this criteria, of course, will depend on the channel that we are studying, we are seeing. And in the case of SWIR again, we can see negative anomalies, especially from July onwards, which can be related with pest presence or pest incidence. And I would like to show you this map in which we are representing the anomalies from October 2022, in the case of SWIR again. And we see how negative anomalies are related mainly with affected plots. So yeah, we are think we're going in the good analysis, in the good way. Oops. Yeah. So to summarize, we found a seasonal behavior in the crop cycle, which can be reduced with BRDF correction. And we also evaluate monthly linear regressions, which can help us to avoid this seasonality, and can allow us to establish a first separability between between healthy and affected plots. But we need previous information about the field. We need to have a starting point, which is that indicates that there wasn't plague. Okay. Then, regarding the anomalies analysis, it allows us to compare each year with respect to the others. So it's a good methodology. And it helps us to establish a first general criteria and more firm about the plague presence. So all these results are indicators that spectral differences due to mealybug pest can be found. But we know that we are in a starting point. We are planning to do future activities as are improve our database. In fact, we are doing this right now. And we also want to try this methodology among other crops, as can be persimmon, which are also affected by this mealybug pest. And we are realizing field experiments, as you can see in that photo with my colleague Cesar. We are doing temperature measurements, we are analyzing climatic variables in relation to the pest incidence, and we are doing spectral responses, studies of the spectral responses at that field scale to evaluate that remaining seasonality. Why we have that seasonality. So our final goal will be to develop an index that will help us to study how plague is advancing. So thank you very much. If you have any question, I will do my best.
Thank you very much. The questions in, okay, so 1, 2 questions.
Sorry. Oh,
Thank you very much for the presentation. So coming back to the infestation, what physical characteristic or what biochemical characteristic do you observe when there's infestation?
Yeah. Are you meaning on the tree level?
Yes. I mean, at the canopy level, what do you see? What is changing in terms of biochemical and biophysical characteristics?
Yeah, at a physical level of the tree, we have morphology changes because infected tree turns like more, I don't know how to say it. It's like reduction of the size of the fruits, and we also can maybe think about an increase in the temperature of the trees also. So visible effects are more about the morphology of the crop than about its color or something.
So you are basically, do you measure any structural morphological parameter?
No, not yet, not yet. But that's why introducing the BRDF is important here, because morphology maybe interacts.
Yeah, because I think what would be important is that at the first stage, when you are considering the infestation, the first thing for me would be to look at the spectral reflectance of this infestation versus a healthy situation, and what is healthy. That's also another question, because at this stage, I think that it could be an effect of multiple stressors that actually exist. You see only that insect because you know it, but maybe there is already another stress going on. So that's I think disentangling the stressors is very important here, but I would say that the first stage would be looking at the reflectance, perhaps, and see what are the changes in the reflectance.
Yeah, in fact, I have to say that we are doing hyperspectral measurements at the field scale, and we are taking healthy trees at tree level, and at the same time we are measuring an affected tree. So what we plan is to compare both signals to understand what is really happened at the tree level, and then we will be able to export these conclusions to a more high scale.
Yeah, and thank you very much. Just a recommendation: if you are measuring like at the tree level and you think that temperature is actually a factor that is changing, I strongly advise you to look at the stomatal conductivity and look at the electrical conductivity also of the leaves, because I think those are changing when the infestation is going on. Thank you.
Okay, maybe we can discuss it later. Thank you very much.
So thank you very much, and we don't have time to have the second question. Sorry for that, and the last talk we will have it now.
Yes, we'll have more questions at the end. Now we will move to the last presentation, which will be given by Bronnie Taylor from UK, and the title is Using Earth Observation to Improve Decision Support in Pest Management.
Thank you, and hi everybody. I'm Bronnie Taylor, and I work for CABI, and I'm the Head of Data Science and Modelling in the UK, and I'm representing quite a broad range of partners and projects here, but really just to show how we're approaching the use of Earth observation in pest decision support and how we can use different approaches to do that. So first, a bit about CABI. We're an international intergovernmental organisation, and we have over 500 employees now, and we have 48 member countries. So we really take our directive from the member countries, and the science and information that we deliver has their interests at their core. So I'm here to talk about pests and diseases and weeds and invertebrates, and it's something that's not really been mentioned very much this week, but before you get to your yields, often there's about 20 to 40% of your crop are lost due to pests and diseases, and it's a very important factor that we need to concentrate on. And so those pests can take many different forms. They can be invasive, which means that they move from one territory to another and cause devastation and large impacts. And with the changing climates, this is being exacerbated. Species ranges are expanding. They can be eruptive, like locusts, so they happen in cycles, are very much driven by the environment that the locusts are in, or they could be indigenous pests that farmers face year on year, and they need to make those pest management decisions of how they're going to prevent those losses. And really, the pests, diseases, weeds, they have impact on livelihoods and biodiversity. But this is the problem. Once you see the pest and the damage, quite often the damage has been done, and we need to move that decision-making into a preventative space. So how do we do that, and how do we integrate Earth observation into that decision-making and turn it into a risk framework that allows us to implement prevention and that crucial first step of integrated pest management? So when we think about using Earth observation, quite often people say, well, you're just going to detect the pest on the crop, but there's many different ways that we can integrate the use of Earth observation data. Sorry, there we go, new slide, thank you. So yeah, there's many different ways that we can integrate Earth observation data. So we can look at the habitats and the environment in which the insects are persisting, and the development of insect populations is strongly driven by temperature, and pathogens, fungal pathogens, strongly linked to leaf wetness, humidity, and temperature. So these environmental conditions, but also the heterogeneity of the crop plants and the general landscape. And there's another application that we're looking at where if you are using detection, it's very important in biosecurity and how we can use this to map and predict where transboundary pests can go. and put multiple layers of information together from different sources to improve this risk framework that practitioners are using to make decisions on where to survey for pests. And we're looking at where the pests are now, where can they go in the future, who needs to know this information, and how is that going to make a change in their decision-making, prevention and surveillance. So the first project I'm going to talk about is the Pest Risk Information Service, which was funded by the UK Space Agency under the International Partnerships Programme. And this brought together a really wide consortium of actors really looking at how we can use Earth observation data to inform pest risk. And we're working with partners in the UK as similar, who provided the Earth observation expertise. But we were using lots of different data sources collected through in-country research partners in Kenya, Ghana, Zambia, and Malawi, and then taking it right through to the extension services, where we were looking at how we can extend that information into existing systems. So this is an overview of the Pest Risk Information Service. What it provides to a farmer is a time to act against a pest. So when is the best time for you to make an action if you're resource limited? And so we build the pest models with the in-country partners, we collect the data, and we put that information into a data cube, which is driven by ERA 5 temperature data, and we have Copernicus crop masks in there, and that's converted into geo-specific information that is provided in various ways for third-party disseminators on the right-hand side of the diagram to ingest that information. So the various ways that we've been disseminating this is through extension workers, through our PlantWise Plus program at CABI as bulletins, but also through SMS delivery schedules. And we've been doing monitoring and evaluation studies to really look at what impact that messaging is having. And we see that this information is linked with increased yields, increased income, and very importantly, an adoption of integrated pest management practices, which is linked to a reduction in pesticide spraying. So this is one of the papers we've published here on the QR code, and then we have more in the pipeline. But we've reached over 2 million smallholder farmers to date, and we're continuing to support that through our PlantWise Plus program at the moment. So I talked about biosecurity before, and I'm moving on to this more spatial modeling now. So rather than when do I need to make an action, where do I need to see the pest, and what is going to be the risk of that pest in that location? And the way that this is done in the pest modeling community is through species distribution modeling, but the data sources that support that modeling are fairly static and based on climatologies. And with changing climates, changing irrigation use, actually what you have coming out of the pest models probably isn't the most up-to-date information that was useful for a practitioner. So we've been working with Assimilar again and Cervantes Agritech, who are based in Australia, and are linked with the Climex software, which is a species distribution model, to look at how we can improve data sets such as irrigation, protect the presence of protected agriculture, and canopy data sets to see how we can integrate Earth observation supported data into a pest modeling framework. So this is an example from one of our proof of concepts that we did. If you look at the graph on the map on the bottom right-hand side, this is what comes out of Climex at the moment, and that is supported with the global map of irrigated areas, which is based on the presence of equipment and the country reporting irrigation. And the darker dots are where it's highly suitable for a pest to be located. And as you can see, we've got some dark dots, a lot more dark dots on that graph there. But if you look at the bottom left in B, which is using the Earth observation supported irrigation data set, which is much more up to date and temporally relevant, we remove those high risk areas, which is really important if you're a practitioner surveying for a pest, knowing where you're going to deploy your staff to look for risk, especially for pest incursions. And we're looking at how we can integrate that into modeling. So we're using our international networks through CABI to help collect irrigation data and validate some of the irrigation data sets. So we're doing that in Pakistan, Kenya, and in Brazil through our Brazil offices at the moment. And we're also linking in with the International Pest Research Community, which is the International Pest Risk Research Group. So we're taking the outcomes of that project and the Earth observation supported changes it can make to pest models, and taking it in a side session in a conference that they're having in September to get feedback from the pest modeling community on how useful these data sets are. And I would encourage people from the Earth observation community to sign up for this and learn more about pest risk research. I won't dwell too much on this, but again, this is using that framework, and we're layering risk here to look at how pathogen wheat blasts can move from where it's been found in Bangladesh, and look at how it could travel across the region. We're using layers of where, when and where the wheat is coming into a susceptible stage, climatic suitability niche models, which are looking at when an infection can occur and we can detect an infection event. And then we have this layer of risk information that tells us which areas are at high risk. And then we're working with partners who are collecting hyperspectral data from drones and linking it up to the hyperspectral data from satellites to see if we can detect when the disease is present. And so when this is a high biosecurity threat, especially of interest to Australia, so we want to map whether that is moving and what the risk is. We want to work with we're working with stakeholders to work out how we can convey that information through to them, what information they need, and what we can do to make the best so they can prepare themselves for these incursions. And then the final project that I will talk about today is global burden of crop loss. And this is where we're looking at, we have an attainable yield, and then we have an actual yield, and there is a loss envelope. And that is from abiotic losses, but also biotic losses. And we have a poster in there that explains this in much more detail. But the sense I get from the community this week is there's a lot of work going on in this top left of this diagram, which is looking at attainable yields. But I think there's a real potential in the top right of our diagram when we're looking at attribution to biotic pests for Earth observation data to be used in the presentation beforehand shows that how that detection can be integrated into these frameworks. So my final slide, and thanks for listening today, is don't forget about the biotic stresses. Pests and diseases are very important, especially when they're on the leading edge of an invasion. Invasive species can cause up to 100% losses when they come into a country and a country is not prepared. So it's a really, really important area, and I think there's a lot of potential for the Earth observation community to get involved. And hopefully I've shown you how some of the pest risk mapping approaches can integrate these data. And also the importance of having multi-sector, multi-focus consortia, which includes socioeconomists, Earth observation experts, pest risk modelers, in-country partners, and that is how we get to impact and how we improve those yields and incomes. So yeah, thank you very much for having me today. Oh, and thanks to our donors.
Thank you. We have time for questions.
Thank you for your presentation. My question is, within different value chains, for example, in Kenya, how does the biosecurity metric work? Thank you.
So we are working with the mixed maize growing system in Kenya. So that is across maize, bean and tomatoes. And that was done under consultation with the in-country partners at the outset of the project. And we decided which value chains that we would work on. So the smallholder value chain was the most important. And then we integrate into those value chains through the sort of, different dissemination mechanisms. So the farmers are receiving the information on extension anyway, and the idea is that this pest risk information is integrated into the existing ways that they're receiving information. So the prize alerts have been embedded into the CALRO, Kenya Agricultural Livestock Research Organisation, big data platform, and they have 6 million farmers on their books, and the prize alerts are being sent out to those farmers. We reached 700,000 last year. We expect it to be much more this year as they expand that service. So hopefully that answers your question. Thanks.
More questions? No? I have one question because I think you have not been very explicit on what kind of Earth observation data are you using. So
Yeah.
can you be a little more explicit on what data are using all the different projects?
Yeah, and so we have our colleagues here from Asimila who are the experts on that, and I deliberately didn't go into detail on the Earth observation data side of things because I think it's quite important to keep the context of how it can be used. But in the irrigation data sets, I think they're using leaf area index and rainfall metrics to really, all we need to know is presence, absence of irrigation, and anything more sophisticated than that is not, we don't need that for our use cases. In the prize system, it's ERA5 land and Copernicus land cover masks. In the wheat blast, the hyperspectral data that they're looking at is from PlanetScope and Maxar. So yeah, unfortunately I'm an entomologist and that's not my area of expertise, but there are people here who know much more than that.
Okay. We can then move to the general discussion because the idea was to keep at least 5 minutes at the end for a more general discussion or questions to all the speakers. So I don't know if you have some questions or comments or recommendations, because there were some recommendations, but actually not so many. So maybe we can have more recommendations or more explicit recommendations now at the end.
Okay, as for me, I have realized that there's the common question for all of us is what is the crowd data, in-situ data, reference data, and how to quantify the data, and in order to understand why and to have the action. Yeah, and for example, in one paper you talk about crop failures. Crop failures, what is it? Is it you cannot harvest or the yield decrease? Pest impact, impact or not impact, how many percentage of the trees or of the crops is impacted? And the crop loss is, I understand that the zero yield, something like that. And also to understand why we don't go to the understanding by biophysical parameters like stomach openings and things like that. And so now can we talk about that, how to quantify the impact of the pest or of the stressor in order for us to understand more and to go to the action. Otherwise, the action should be to put the chemical and etc. So somebody has ideas? No? Yes.
Okay, this is Belén from the University of Valencia. I think for crop stress, mainly what we really need, and I think it's uncommon, it's especially like a good frequency of thermal measurements at high spatial resolution. So it's very challenging because like the LSTM, that it's the upcoming mission, maybe like the spatial resolution that we might require for some applications might not be like so good maybe for agriculture. Also flex that will come as well. The spatial resolution for like pest control, maybe it's too coarse. So I would say that when we're working on stressors, first we want to be rapid, like detect it as soon as possible, but also like agriculture associations, they also like to know like how it's evolving within the field, even within the field, that it's very, very challenging. So we have like the two different requirements. First, time, and also like frequent measurements early as possible, and then also spatial resolution to see how much of the parcel is impact or might be having an impact. So for sure, like also the data,
So
like
it's-
defining like that. I think it's okay.
Yes, I fully agree. I think everybody is saying that we need a high frequency, high temporal frequency, and very high spatial resolution for these applications. But I was about to put a question for several of the speakers, and maybe I can put a question at the end for all the speakers, because when we meet like in this conference and we make recommendations, then later on, some of these recommendations has been implemented by ESA. And in discussions many years ago, one of the recommendations was that in order to have this kind of application for stress or pest monitoring, more precise characterization of vegetation, if you want to talk like this, then we need additional information, like, for instance, the red edge bands in the Sentinel-2. And the Sentinel-2 was, the red edge bands in Sentinel-2 were incorporated just to look at these kind of things. And I was surprised that nobody has used, and I think nobody in the whole conference, until now, has been using the red edge bands, which are already in Sentinel-2. So it's a question for all the speakers. In the study they use red band, near infrared, and all the people use NDVI, or the people use, but there are information which is already available in Sentinel-2, which is operational, high frequency, high spatial resolution, but why people are still using NDVI, and why people are not using the spectral bands that were especially allocated for this kind of applications? Because I think we have to, if we really ask for this information, then we have to use the information somehow. And I don't know what is the reason for not using this information for these applications.
Could I reply? Good morning. Well, we tried to use them in EO for Explorers in Africa Forecast project for detecting rust on wheat in Africa. But unfortunately, we ran onto the rainy season, so there were no cloud-free images, and we decided on Landsat and Planet. So it has to do also with the growing season. So it is not only of availability of the red edge band, it's also of the of the special characteristics of the crop itself. Also, we have tried to use the other type of indices, for example, the anthocyanin reflectance index or the carotenoid reflectance index, which are also the pigments reflect stress on crops. But these also are on a research stage, let's say. So yes, I think that other researchers as well have used the red edge band, but we need to respect the time of the development of the crop.
Thank you very much, Jose. I think I agree with what was said by the other colleague. The availability of the data, of course, is a major problem in the cloud. And the cloud is actually a major issue. But also, perhaps, what is important is that red edge bands are important. But not everything, not all the pests and disease are related to the red edge band. So basically, well, the disease or pests which are affecting some pigments, maybe chlorophyll, nitrogen, perhaps, or to some extent biomass, they have been shown to be related to the red edge bands. But not all the disease and pests will cause actually these changes. The first changes that, for example, is caused some pests is the reduction in the leaf area, for example. So it depends on the type of pest and disease which is studied. So it's not red edge bands necessarily is the first bands that should pop up. And the second thing is that, of course, the red edge bands which are located in Sentinel-2, for example, are not really covering, well, they are very good, but it does not cover the whole red edge region. And in some studies I have, for example, compared that when you use hyperspectral data and when you use the red edge bands from Sentinel, well, the closest red edge bands which is in Sentinel exist actually will pop up, but the red edge bands which was identified as the most important band was something else in using hyperspectral data. But of course, when you limit and the data to Sentinel-2, of course, the closest will pop up. But what I want to say is that there's limited red edge bands, of course, and not everything is related to the red edge. It depends on the destruction in the canopy, which is caused by the pest and disease.
Just following your idea, in fact, we tested with all Sentinel-2 bands, but we just found interesting results in the bands that I showed. And maybe it's also because of the resolution of the red edge, because when we are studying small fields, our study zone is located in Valencia, so fields are really small. 10 meters could be good, but 20 meters maybe is too coarse. So with that and with the relation with the biophysical parameters that you were talking, we couldn't use the red edge.
Yes, but I think what we have now is a much better conclusion than my initial comment, because the conclusion now is that we have been looking at this. Maybe this is not the best information, and it's not, I agree that it's not everything is there, but my message was that if we ask for additional information or additional spectral bands, now we have the discussion for Sentinel-2 next generation, where there will be additional bands, but the same is true for all the satellites. Then we have to show if this information was useful or not, and was used. So my understanding now is that people have been using those bands. Maybe they are not so useful for this particular application, but at least we can show that we are using that. I'm sorry because we are running out of time, and the discussion was very interesting, but anyway, unless there is a comment, a critical comment.
I have more general comments about the use of such a sensor. I am used to be in the radar communities, and in that communities, very few people using optical data, and now during this workshop, most researchers use optical data, and where there are possibility to use Sentinel-1 for drought, water stress, etc., and no one have tested something like that. And this is because of the communities is based on a lot of knowledge in optical data. So in the future, when we will have all the satellite data available, so why not to use them all to take the best of each kind of data? Yeah.
Probably people want to go for the coffee, so we can continue the discussion during the coffee break. Thank you.
Okay.
So we can resume this morning session. If you want to take a seat, thank you. Okay, so we can start with this session number 10 about climate adaptation. And just to introduce myself, my name is Lara Congiu and I work at the European Commission, specifically at the Research Executive Agency, where we coordinate, evaluate, and assess the implementation of environmental observation projects contributing to the Green Deal priorities and the Green Deal. And I will co-chair this session with Professor De Fourny.
Good morning, Pierre De Fourny from UC Louvain. I'm leading a research lab much involved in remote sensing for agriculture and land cover. And today we have the pleasure to have a second session which is related to another pressure. Maybe you can continue.
We will tackle the physical pressure on agriculture and so climate change and specifically climate adaptation. And we will start with the first presentation. And
I will be Lorenzo Simone from FAO. We will have several presentations related to FAO. And Lorenzo will talk about enhancing agriculture productivity assessment through integrated Earth observation and crop suitability analysis. You have the floor.
Thank you very much. Good morning again. So I have many things I would like to talk about because as the event is unfolding, I've seen many interesting things and many ideas, but I'll try to focus on two topics. Agricultural productivity in general is the result of the interactions between site-specific conditions that allow the plant to grow. And of course, we have in the picture the farmer activities, the management. So the definition of agricultural productivity, let's say in theory, is that of the total factor productivity. So the outputs, which can be livestock, crops, and other products produced on the denominator divided by the input, which is a combination of resources like land, labor, capital, material, and so on. And we have SDGs who try to monitor agricultural productivity, the sustainability. However, when we want to monitor this productivity from space, eventually, we will focus on the crop yield, which means tons of products over an area. And as we know, we have three main approaches that are established. The most antique ones is the statistics regressions. The first studies were dated in 1992, where essentially we establish a regression between the variable of interest, the yield, and the independent and the predictors, which come from remote sensing, the NDVI, and other with more or less sophisticated methods. But the limitation of this, of course, is that it's difficult to extrapolate in other areas. It's very difficult to adapt this to other type of climatic situations. On the other spectrum, we have process-based models, which instead they try to understand the relationship between the soil, plant, atmosphere, the cycles of nutrients. And so they're very much able to understand the response of the crop on a daily basis with the daily inputs. And it's very site-specific. The problem is that it requires a lot of training data, and most importantly, local data. And then in the middle, we have machine learning, which is the new age. Essentially, we give data to the model. We ask the model to understand relationship and to predict. And the problem there is, of course, they're not necessarily easy to understand. They might be black boxes, and they need a lot of training data. So there is always a compromise. I'll be focusing a bit on process-based models, which is the one that we are using mostly to support countries to establish their monitoring system at the country level. Of course, crop models can be very complex, and there is a variety of information that go within the crop model. For example, we have weather, we have management, biotic interactions, and so on. But many of those information can come from remote sensing. So we can feed Earth observation data into a process-based crop model, and then we can leverage also on existing Earth observation big data platform to start to combine the process-based models with Earth observation data and start to see results. So this is an example of an architecture that is used currently in Ecuador, in Peru, and Colombia. We are supporting the Ministry of Agriculture there in the National Statistics Office, and essentially we have a front-end application in Google Earth Engine, and then we have a Google Compute, where we run basically the predictions and we update the baselines. We have a Google Cloud Storage where we store climate, soil, yield, crop management data. And then we have a virtual machine in Kubernetes, essentially where the Salus is running the simulation and is providing back the crop yield. So this is probably not new to you, but what is interesting in my view is the fact that now we can combine together data coming from national data set, data coming from global data set, or data coming from in situ data, depending on the relationship with the country and the availability of this data. And of course, it's a joint work. And this allows us already, to provide enough inputs to the model to provide us with a crop yield in time. So this is just some of the data that we use when we don't have weather stations. So we use temperature and solar radiation from the Weather Forecast System version 2. The CHIRPS data, who doesn't know it? So it's very familiar. And this is just an image of the rainfall millimeters per year. And then, for instance, this is an example of a soil map for the Guayas region of Ecuador. Essentially, the country can use their own soil map to increase the granularity of the overall product, and so the overall quality. Or they can also use global maps coming from one land map, soil grids, harmonized water soil database, and so on. Of course, crop maps are still necessary. We want to know where are the crops. Many countries, especially in this area of the world, they are producing their own crop type maps, or they can use available toolbox, Send4Stat, for instance, Crop Mapper, and so on, to produce their own masks, crop masks. And finally, using always geostatistics approaches, once we collect the data on cultivar, fertilization, irrigation, planting dates, density, then we can start to produce farm management maps, which inform on how those variables are spatially distributed. All of this together provides us finally with the simulation, so the expected crop yield. Of course, these simulations, they can be backcasting, so they can run historically, and we can compare them with the observed yields, and you can see how the model is able to predict quite nicely. It's quite well aligned. But the most important thing is that the model is able to predict also considering future scenarios, future climatic scenarios, which then starts to inform us on what's going to happen to the yield of the current crops. If the management remains the same and the cultivar remains the same, what's going to happen in 5 years if we have these anomalies in weather, for instance, in temperature or available water. The future, of course, forecasting comes with uncertainty, so we have to be aware of that. This is an example where we have simulated until 2022, and now we are forecasting for 2023, and we can consider different type of climatic scenarios. Those are comparison between simulated and measured yields in different districts of Ecuador. The same has been done for Cameroon, so we can see maize, sorghum, rice, and cassava, and of course, analysis and investigation is required to understand when we have departure, what could be the reason to do that? Is it a problem of the data? Is it a problem of the model? So one of the backdraws of this type of modeling is that it requires a lot of fine-tuning. We can see then that the yields in time, as we saw before. So here we have the yields for rice 2021, for sorghum 2021, 2012, and so on. 2011, sorry, 2012, and so on, for all of the years for which we were able to train the model. This allows us then to build us our time series and then to see areas where the yield is stable, areas where the yield instead is more variable, and also trends, of course, which is important information for decision making. The tool has been set up in Google as Earth Engine, as we mentioned earlier, and now it's been further evolved. So essentially it allows for simulation. So we can provide a point location, we can provide information regarding the soils, either using soil grids or providing information on generic information about soil types, and then the management information, tillage, no tillage, the number of rows, and so on. And this can provide then, a response. The response can come on a local scale or it can come on a regional scale. And we can decide which type of scenario we want to use. And finally, we visualize the results. So we have the commodity, the year, the season, and the climatic scenario. Of course, we also provide some statistics information on the accuracy, on the departure from the, the difference between the simulated and the observed yields. And this tool can also be useful to actually map the management information. So it's a kind of data mining tool. For example, we want to have discrete data filtered by region. For instance, we can visualize crops or application of nitrogen, density, and so on. So this is all regarding the physical-based model. I want to see how much time I've left. How much? Okay, so very, very, very fast. So the other thing we're thinking is, okay, what if we don't have data, but we still want to model what is the crop potential in an area, given that we know that plants have specific requirements, so we know absolute means, absolute maximum, and optimum ranges across the let's say, the key inputs, which is the soil, temperature, availability of water. So we've been working on the crop productivity index, putting together those this information from Earth observation data, reclassifying this with respect to specific crop requirements, which are cataloged by FAO in the eco-crop database. We have more than 2,000 records. And essentially, we are able to identify the ranges, optimum and the absolute minimum and maximum for the key variables. I will not go through them because I have no time, but basically they are coming from mainly, we have MODIS data here, and then we have open land map for the soil. And essentially, when we put this information together, we need, of course, the crop mask. We need to know about the crop calendar. We need to have more information, let's say, on the seasonality and the requirements. Essentially, then we can start to model the crop productivity index on a specific crop on a yearly basis. And this allows us to build essentially a time series and allows us to see how is this changing in time. So is my crop, does it have the same potential in time, in the years? Do we have areas where the potential is more stable? Do we have areas instead where this is changing as an impact of climate change? This is the workflow essentially of the CPI, but I want to go to the last, yes. So this is a slide that is showing the wheat crop potential in Pakistan from 2019 through 2023. And essentially, when we put together a time series of maps, then we can see the change across time, and then we can start to do further analysis and identify areas where you have a more stable potential, and areas instead where it's more, let's say, variable, and that can be, let's say, a first information regarding the resilience of that crop in time. So I will stop here. Thank you.
Thank you very much, Lorenzo, for keeping the time. We have time for one question. Okay, maybe, I don't know.
The microphone is arriving.
There are two burning questions.
Thank you for the presentation. My question is the crop productivity index replicable within the horticultural value chain?
Can you repeat, please? Is it replicable in the horticulture?
Yes, please.
Okay, so the CPI is excluding farm management. Okay, we're just looking at agroecological condition. So soil, temperature, availability of water, which of course depends from the soil characteristics as well, but also the available water from precipitation. So in the horticulture, at the moment where you start to have inputs like irrigation or greenhouses, that is not applicable anymore, of course, because we don't take that into account. But it's more of a tool, let's say, to use at large scale, when you want to compare between countries, or you want to compare how the suitability is shifting in your country, for instance. Thank you.
Thank you. Maybe a last question.
Yes, very, very quick. How were you able to obtain the observed measurements for yield?
Okay, so
how many was it required in order to go to?
Yes. So through the Minagri, for instance, in Ecuador, through a partnership which has started 4 years ago. So we started receiving data first at national and administrative level, 20 years time series. Then they send us another file with the crop plots. And then this has been, let's say, it has commenced to be more regular because they do the crop cuts. This is not the case in every country. So for example, when we've been working in Cameroon, now we are collecting data finally after 3 years. At the beginning, we had to calibrate the model with FAUSTAT data, which is of course coming at national level. So the thing is that the barrier of represented by the scarcity of in situ data of adequate quality should not stop the approach, because we can get there, but you need time. So
Money.
Money, but for instance,
to run this campaign in order to get the data.
Yesterday,
I'm afraid we should stop.
Sorry.
Yeah. You can continue later on, maybe
Now we go to the next presentation indeed. If the title is FAO Plan T, Enhancing Climate Adaptation for Maize Cultivation Through Advanced Methodologies and Tools for Improved Decision Making. And the presentation is by Ramiro Marco Figuera, or?
Ramiro, yes.
Okay.
But good morning, everyone. I am Sandra Corsi from the FAO Office for Climate, Biodiversity and Environment. And I'm very happy to be here today to present, together with Ramiro, the work that is being developed as part of the cooperation with ESA that has led to working closely for the last couple of years with Sistema. And the reason I'm very pleased is that this line of work is very valuable for us. It's directly related to our mandate, and it helps us delivering effectively to our member countries. Specifically, the work that Ramiro is going to present today has been developed following a request we received back in 2017 from Zambia, that wanted to receive support to up the productivity of their staple crop, maize. And then we started the assessments at the national level, and we identified that the main causes for the low productivity in Zambia were related to a mismatch between the varieties used and the location in which they were planted, and the difficulty of farmers to access reliable weather information, to understand when the crop season, the agronomic season, would actually start. And that would cause crop failures and losses in their investments in seeds, fertilizers, and labor. And so what we've done together was to bundle together all the data available, from observed historical climate data, near real-time climate data, weather forecast, variety-specific information, soil data, to provide information that's actionable by farmers to support them in the most critical part of the planting operation, which is of the production operation, which is the seeding operation. And the reason this information is so relevant is that traditionally, in the countries we support, the advisory service doesn't have access or uses outdated climate information. And so I think it's interesting now to listen from Ramiro how we've developed the approach to support the country. Please.
Hello, thank you, Sandra, for the introduction. So I will talk a little bit more on the methodology, how we achieve what Sandra just introduced. Let me just see. So we can break down the methodology in 3 steps. The first step is the crop seasonality assessment. So basically what we do is we integrate methodological data, agronomic data, satellite data, and we assess the seasonality of the different maize varieties. On the next step, what we do is the crop yield estimation. So for the crop yield estimation, we run the AgroCrop model, and we improve the accuracy of the crop yield estimation per maize variety. And the last step is to identify the optimal planting date. So in this step, we determine whether if the day that we select it's the right day to plant to seed the specific maize variety for that specific location. Let me go a little bit more into detail. So for the first step, the crop seasonality assessment, what we do is we compute the start of the rainy season length based on a condition of the rainfall of the 10 consecutive days and the ETC. Then we compute the end of the growing season length by also checking the rainfall of the 10 consecutive days plus the days of the thaw and the depletion factor. And at the end, what we do is we compute the whole growing season length. And to finalize, we compute the sum of all the daily rainfall between the start and the end of the season length. Those are some preliminary results that we just computed that shows the start of the growing season length in the day of the year for PAN 53 maize variety and the end over Zambia for that maize variety. Once we have these, we go to the next step. So the second step is basically trying to answer this question, which varieties perform best in each pixel. So this is a pixel-based analysis. For that, we also break it down in different steps. So the first thing we do is to check at the phenological stages computed on a pixel-based. Then we check at the salinity stress for that specific location and that specific maize variety. And finally, we check the response of the fertility stress, again for that specific location and that specific variety. Once we have this information, then we feed the AgroCrop model with that data, the data from the first step, the crop parameters that we just computed, soil data, electrical conductivity, and then climate data such as evapotranspiration, precipitation, and temperature. Once we run the model, then we validate or recalibrate the model with, if possible, field data. So we validate the model against randomized block control trial data. If it needs to be recalibrated, the model, we search for the optimal hyperparameters. If not, we go ahead. And then the last step is checking at the physiological response of each of the stressors that we identify. So basically, we check at temperature fluctuations and water availability, and we define a set of different climate stressors. And then we check each of the maize varieties, which is the one that adapt better or are more affected actually by those climate stressors. So all those steps that I've been talking about are done, are pre-computed. So we do a huge pre-computation process, and then we do a live check, which is when should we plant, okay? So here the user, I will explain a little bit better later how we do this via web app, but the user basically goes through a very simple conditional algorithm that checks at water availability for that specific variety, and then if it fulfills the condition, then we consider that this is the right day to plant. If not, we will check also at the forecast from ECMWF, precipitation, and then if it fulfills the condition, then we plant it. And if not, we will repeat the process until the end of the growing season length, right? How do we do that? So the user, in this case farmers or stakeholders, have access to this data via a web application. So we're developing a web application which is super friendly, user-friendly, sorry, and it can work in desktop and portable devices, so the farmer can actually check on their phone and run the whole assessment. So a few features about it, it's like you can select a specific site just by clicking over a map, and then we collect the coordinates of that specific location. You can check at the soil chemical parameters of that specific location, and then it will give you a ranking, let's say, of which is the best maize variety based on the climate stressors and the locations for that specific region. And then it's up to the farmer, giving like kind of a color-based, let's say, go ahead or no, or consider another maize variety, to just run the last step, which is checking at the date at that specific location and then saying like, okay, that's the best moment to plant it, or maybe you should wait for the next 10 days or for the next 10 days or until the end of the growing season left. So just to wrap it up, everything, and not to take too much time, benefits of this framework is that you have informed decision-making for climate adaptation. So it provides valuable insights into the suitability, planting dates, and potential crop productivity of each of the maize varieties. And then it enhances the usability. So we integrate all these tools and all these methodologies into the platform, and it supports the agricultural practices amidst of the climatic changing conditions. I think that's everything from our side.
Thank you very much. We have time now for a question. Here. There.
Please go ahead.
She has no microphone, so.
It's a quick question.
Okay.
Where do you get the soil properties from? Which database? Or do you expect the user to provide the...
At the moment we get it from a database that it's, so this part of the project is run by one of our partners, so I don't know exactly the database they're using, but I know they're taking it from a database. At some point we can also consider the user to provide their own soil parameters, actually.
Okay, so if the user chooses a wider area, from which soil properties will you use then? Because you said the user is allowed to choose only the field, the parcel, or a wider area?
No, it's point-based.
Point-based?
It's point-based, only point-based.
And from the aquacrop, when you run the aquacrop, where did you get the soil properties from?
This is what is run from one of our partners, and I cannot really answer to you.
Okay, thank you.
We can discuss later. If you want, I can give you the contact.
Hello, hi, Sheila again. So I have a question about methods and a question about adoption, especially because this is an FAO project. Are you working with like the country office of, did you say Zambia as the?
Yeah.
Okay. And then who are the end users really of this project? I guess I'm wondering, is it like an extension agent who can provide advice to farmers, or is it farmers themselves who have smartphones and can look at the web app?
Yes, so thank you for the questions. So the idea, back on the soils, right now we're using ISRIC data essentially for some of the layers of the methodology, and the idea is to use data that will be collected as part of another project that is going to do data collection, remapping the soil for Zambia and Kenya. It's in 4 years' time. So we have developed this methodology in a way that it can be updated with up-to-date information without having to go back and change the methodology. Okay. So on that question, we're working with the Zambian Agriculture Research Institute and University of Zambia. That has done some of the profiling of the phenological stages of the varieties that have been selected with the farmers. And the Zambian Agricultural Research Institute has done and is going to further continue the randomized block control trials to further validate and recalibrate iteratively the predictivity of the model. What was the end users? So the first, we are developing this especially to provide support to the extension services, national extension services, who are to reach out to farmers, because they really lack up-to-date actionable information, and they are constrained by lack of resources to reach out to many farmers. So the idea is to work with the blocks. In Zambia, we have this structure. Farmers are organized in blocks, or the lowest administrative level is that, and there are chiefs. And so the idea is to be able to provide support to the extension officers and further reach out to the farmers through the social structure that is in place in the country, which is this lead farmer or chief-based outreach to the farmers when it comes to making decisions on planting and agriculture in general. So this is, there are many features we would like to, once the proof of concept is being tested, we would like to implement. And one of these is to move from the web-based application to a mobile phone level application, because the penetration of mobile phones in some countries is quite high and the reception is excellent, and that's a great way to reach out directly to farmers, which will further need to have a very user-friendly interface and still be able to keep the detail that this web-based application is providing.
Thank you very much.
We will move on now with Leonid Chumilio from University of Maryland, introducing us to the special change of winter wheat production under changing climate, thanks to the climate velocity principle.
Thank you very much. My name is Leonid Chumilio. I'm from University of Maryland. So I would like to present our work, Special Changes of Winter Cropland Under Changing Climate. So I want to start with problematics. So major winter crops like winter wheat, winter barley, and winter rapeseed are essential commodities for the food security, and they will be very impacted by the climate change. The increase of temperature of 1 to 2 Celsius degrees can cause the 4.7 reduction of wheat production. And if we're talking about crop growth models of the new generation, they're indicating that until 2099 we can expect 15% drop in cereals production, and a lot of winter crops will have significant shift to the northern or like dependently southern latitudes, and it will be caused by the adaptation to the climate change through the migration of the cropland as a response to the climate change. To study how climate change impacted by the winter crop impacted by the climate change and what processes are going on right now and were going on in the past, we produced a continent-level winter cropland maps. For this purpose, we used crop masks produced by Potapov et al. And based on the MODIS NDVI phenological features, we applied Gaussian mixture model-based approach developed by Sergei Skakun for a large area winter cropland mapping. And it allowed us to build continent-level winter cropland maps for on the grid 200 by 200 kilometers. And after this, to get the extent of winter cropland, we combined these maps into the 4 years interval based on the common crop rotation cycle for majority of winter crops, as well as FAO definition of the cropland. We stratified these maps into the 5 classes of second stage of stratification. It's other crops, other classes, winter crops stable, winter crops gain, and winter crop loss. And we, after this,
analysis, downscaled it into the 10 by 10 kilometers grid to get the 4 classes of intercropland density. Its height stratum 73% and more, medium stratum is more than 47%, low stratum is more than 20%, and very low stratum is less than 20%. We excluded all cells that has less than 5% of cropland, and in this way we covering more than 99.99% of the winter cropland in the Europe. For each of the strata we generated in total 70 samples. It's 20 samples for the high, medium, and low strata, and 10 samples for very low strata. For each sample of the our first stage stratum, we produced 20 points of second stage, producing in total 1,400 points. We, after this, conducted analysis of time series of historical MODIS, Sentinel, Landsat data to conduct analysis and by photo interpretation and time series of vegetation indexes, separate winter crop from spring and summer crop, and use it for area estimation. Sample-based area estimation allowed us to get a total area of winter cropland for different time periods, as well as estimate the gridded 10 by 10 kilometers density maps of the winter cropland fraction, as well as evaluate standard errors and variation for each cell specially and for total area of our research. We used maps for 2000 and maps for 2019 to estimate the total change between these time periods. And if we're talking about winter cropland and cropland at all, it's not only interesting to see how fraction of area changed, like in absolute numbers, but more important also to study the proportion between winter cropland and cropland to understand how expansion of winter cropland is looking spatially. For this purpose, we we conduct map-based stratified random sampling estimation of winter cropland and cropland over our produced maps, and we estimate proportion between winter cropland and total cropland. We also estimate and standard errors for each maps to get a special distribution of errors, and produced maps from 2000 to 2018. This is combined, for instance, map of fraction of winter cropland over total cropland from 2016 to 2018. So after this, we get that winter cropland area increased for 49,763 hectares from 2000 to 2019, and in relative it is 15% conversion of the cropland into the new winter cropland from 2000 to 2018. The special two-stage approach allowed us to conduct analysis of winter cropland change not only in total numbers but also spatially and in dependence with latitude, and estimate not only areas but the areas of the changes. And here, why we also studying the proportion between winter cropland and total cropland. So majority of cropland in the Europe located from 45 to 55 latitude. And in this area, we see as well as a large winter cropland area and as well as very large like absolute numbers of changes. However, if we are gonna study proportion between winter cropland and cropland, we see that in the relative numbers, the changes on the northern latitudes actually are much higher than on the latitudes where we see majority of winter cropland. And it can indicate in the large expansion of the cropland to the northern latitudes, but not just increase of total winter cropland area. It can be related to the climate change. the global warming increasing the growing degree days for winter and spring season that allowing for winter cropland develop better and faster. And it's the positive trend of growing degree days and accumulative biologically active temperature on the northern coordinates, allowing to expand practice of the winter cropland planting and allowing them not only plant only spring or summer crops, but also adopt winter cropland production. The winter cropland fraction change has moderate correlation, 55% with trend of the temperature, but at the same time, if we will use trend of the temperature with the accumulative temperature for 2000, it is possible to build predictive model of the winter cropland fraction change with R square equal 0.59. Obviously, climate change is not a main indicator for the forecasting of the winter cropland change. It's impacted by policies, it's impacted by market, it's impacted by commodity needs and requirements, but it's evident that climate change and the increase in the growing degree days, it's one of the essential factors in this process. So in conclusion, we observe significant increase of winter cropland area and fraction in the Europe. Area increase has patterns of the expansion to the north. Fraction of the winter cropland over total cropland area shows that northern latitudes have much higher rates of the winter cropland expansion than southern, and dependence between winter cropland fraction change and trend of accumulative biological active temperature for winter spring seasons, indicating that climate change is one of the drivers of this expansion. If we're talking about recommendation to the Euro Commission and ESA, will be nice if we will continue improving temporal resolution of the Earth emissions. We used MODIS data for our research because we need very high temporal resolution. If we will have very high temporal and spatial resolution of historical data for large period of time, it will be amazing opportunity for future studies. Analysis of climate change impact on agriculture require high-resolution climatic data with large area coverage. And if it is possible to expand pan-European services and pan-European climatic models to the larger scale, at least to European continent or to the global, it will open a lot of possibilities for future studies in the agriculture and dependency between agriculture and climate change. And winter crops and summer crops, varieties of the same crops are differ in the protein content, yield, properties, and use. So in the special products like crop maps and points, they always should be separated as different classes. Thank you very much. Any questions? Thank you, Leonid. Do we have any question in the audience? Yeah, Christophe.
With respect to that last point, is that something that should already be solved in the crop type maps, or is it something that you could also do by looking, for example, at temperature regimes or phenology? Is this a separation that still can be done afterwards?
Mm-hmm. Yeah, but if we're talking about ground truth data, I saw a lot of data sets that also hosted and produced by European Space Agency and GRC. Some data sets are not separate winter wheat and summer wheat and spring wheat. Of course, it's possible to do phenological analysis of the samples, but in this way, it's not possible to claim that it's ground truth data because it's still reanalysis based on the expert opinion. And if there will be very homogeneous data sets with different classes and different seasons, it will be the perfect solution for any studies, and it will help a lot.
But I think the recommendation is also important as a community, I think, to really have the definition right of this winter and spring cereals, because in some data sets, in some countries, this separation is done purely on seasonality, sometimes it's on the variety, and harmonizing data, this is really a hard thing to do. And if you mix it up, then you claim that you have the spring and winter separated, but in the end, it's not going to be.
Yeah, I'm fully understanding. I'm fully committed. Like taxonomy problem in definition, and harmonization definition. It's a high, like very important topic in GEOGLAM, in all communities, in Geo community. But if we're talking about Euro Commission, there's existing definition that Euro Commission using for winter crops, and at least following this definition, it's possible to provide information based on this definition.
Thank you very much. I propose to move on with the next speaker. Yes, so we go to the next presentation. That is quantifying rice adaptation to climate stressors in Senegal using time-dependent deep learning with the TAPAS platform. Presentation by Dualta Funagan from the University of Galway.
Thank you. Hello, everybody. So in the next few minutes, I want to talk to you a bit about TAPAS, so it's Tracking Adaptation Progress in Agricultural Systems. And so this was a project funded by the Science Foundation Ireland for their AI for Societal Good program. Firstly, I just wanted to point out some of my collaborators and colleagues. It's not just me, obviously. So not possible without all of these, this great team. So some context. I'm going to talk about two things, both focused on the same region. And the first thing is basically about a large-scale intervention in the Senegal River Valley. Essentially, USAID spent a lot of money in the region trying to maintain and upgrade rice productivity. This was carried out by the Millennium Challenge Corporation. For irrigation systems, they spent about $150 million. In total, the impact was somewhere near $500 million. And this primarily took place in the red region here, outlined in the bottom of the Senegal River Valley. The other regions we used as kind of control regions to see if they behaved differently. And this intervention took place from 2011 to 2015. Additional context is like Senegal is very dependent on rice. It's one of the major nutritional crops in the country, but they are not self-sufficient in rice production and import a lot of it. And an aim of the government for, I think, almost 20 years has become self-sufficient in rice production, and they still have not achieved that. So the Millennium Challenge Corporation had three main goals when it came to increasing rice productivity. The first one was to increase the amount of rice area cropped. The second was to increase the cropping intensity, so a lot of the crop would have been just late season crop. They wanted to double crop across the entire valley. They also wanted to add a third crop of tomatoes and onions, which was pretty much a failure, didn't end up working. So we don't focus on that here. And then the last one is just general maintenance of the irrigation network over longer timescales to last past the intervention time period. And so I don't have a huge amount of time to talk about the methods for this. Basically, we used an XGBoost classifier to select out rice masks. We tried using open source rice masks, but they didn't have the seasonality in there, and they were usually only every couple of years. We use XGBoost and a hidden Markov model to come up with classified rice in the region. And then that is an annual mask. And then from there, we use EVI, NDYI, and radar data in the VH backscatter to do a time series to image transformation. So that's the granular angular imaging. And then we put that through a CNN to classify between single cropped, double cropped, or not cropped in that year. And these are just some of the results. So in the top left is the rice mask, and rice is shown in red. yeah, we can see the other classes that we wanted to just identify and remove. Urban areas are removed out of this and all of that. So you can see a lot of it is just bare soil or sand, and we have wetlands and water there as well. And then the results of the cropping intensity on the right, you can see the distribution of the different types of cropping method there. So like even though that region in the south is well within the intervention area, it, for this particular year, didn't crop twice. It only cropped in the rainy season later on in the year. And then these are just the aggregated results then. So each of these lines represents one of the regions of interest there. The intervention part of the delta is in green on the left, in the top left plot. It's hard to distinguish trends here just based off of area because they're all different sizes, but in the bottom right, it's normalized to 2015. The reason we only go to 2015 is because the Sentinel data for only goes back that far. But you can see that the public-private partnership, which was neighboring and not part of the intervention, outperformed the intervention delta massively. So that's an interesting result. And then in terms of the irrigation network water management, this is just, we take a SAR water index across the entire delta and split it up. We identify all of the water, all of the different water sections, basically using OpenStreetMaps, which is fairly comprehensive, and then delineate those by man-made versus natural. And you can see since the end of the intervention, the amount of water in these waterways is decreasing, which is of concern. And then some context in the bottom right. This is just a plot of evapotranspiration and precipitation, and showing labeled droughts. I think it's from FuseNet over the last, back to the 80s. So the plot on the top left is just the last couple of points there on the right. So yeah, then in terms of trying to measure adaptation to climate change, we use a model where we apply what we just showed there to define a rice mask over the different years. And then this is, we use this then to select out MODIS data going back to the year 2000. And we train a model that's a combination of a CNN and LSTM to learn about 15 years of trends. And then we use that to synthesize more recent NDVI data. And so this model assumes that the climate is changing relatively slowly, so on the scale of years rather than months. And also, this morning there was talk of like biotic and abiotic factors. Like we don't distinguish between any of that. We just put all the data in and let the model figure it out, essentially. And so the output is that we have this blue line, a predicted value, and we can compare that then to observed values for every pixel and decide if an area is doing better or worse than it should be relative to 20 years ago. And so here's some results. This is actually for the public-private partnership region that we highlighted earlier. The plot on the left shows the observed NDVI for that region, and that's MODIS resolution. The plot in the center is the forecasted or the synthesized value, and then the difference on the right. So it shows just how we relate the predicted value and the observed value and get a result out. This could be useful at this level for identifying hotspots of degradation due to some factor, but we think it's a little bit noisy and possibly better to aggregate over regions of interest rather than individual pixels. We haven't really decided on what scale it works best at yet, so this is just an example of how you would aggregate. You just take all those differences over all those pixels, and you can show what regions might need more attention than others. And so these are some actual results. I forgot to put the color bar here, but it's essentially red is bad and blue is good, and it goes from, I think it's -2 to +2. And these are divided up into subregions compared to earlier, just to give a bit more granularity. But again, this could be scaled up or down depending on your scale of interest. And then just to show the complexity, even at that scale, these are all those regions and the trends over the years we analyzed. And you can see it's quite noisy. But there are some indications that there's a trend downwards, which is obviously of concern as well. So in terms of concluding, that intervention was largely a failure in the long term, and this is like maybe a weakness of interventions in general, is that they are conducted over a certain time period, and then an assessment is done post-intervention, and this can be 5 or 10 years later, when it's like too late to actually put the money to where it needs to go. And they also conclude that in their internal report, where they have a very low economic rate of return on the total investment. The purpose of the TAPAS project was to see how far you could go in assessing these entirely remotely. And the benefit of that method that I showed is that it's comparative between the same location 20 years ago and now, so it's like a percentage change, essentially. Yeah, and then I think recommendations, just like continuous integration of Earth observation data and technologies in intervention and aid strategies. A lot of it is done a long time after the intervention has happened. It should be happening from the day one of the intervention. Yeah, and then in terms of in situ data, we did try to work with some in situ data. It's extremely difficult and sparse, especially in these regions. So some collaboration between interventions and national bodies to try and put in situ data in place would also be very useful. So I'll stop there. Thank you.
Thank you very much. Any question from the public? Over there.
Hi, Gina from Potsdam Institute for Climate. Thank you a lot for the presentation. Maybe you could further elaborate on what you quantified as adaptation, because I guess
yes,
you covered a lot of things, but maybe just how you...
Yeah, so when we, the output of our model is the NDVI over a certain time period of interest. It could be last year or the last 3 years. For the time, this is actually something we're currently working on and constantly refining. But for the time being, it's essentially any difference in NDVI integrated between the curves for above a certain value. So at the minute, we threshold at like 0.2 NDVI. Anything above that is considered a good crop. And then the difference between the curves is essentially what we're using to quantify the adaptation. So it's entirely numerical in that sense, and more an indicator of maybe biomass than anything else.
It's implicit. It's implicit. Thank you.
Thank you. No other questions, so we can go to the next presentation.
Okay, let's move on then with Thuy Lotoan from CESBio in France, who will introduce us to the Vietsco project related to rice monitoring and climate adaptation in Vietnam.
Good morning again. So my talk is about rice, and I am presenting the talk on behalf of my colleagues from France, Vietnam, and Thailand. And here you have on the name of the co-author. The last one are from Thailand. They are in the room. The Mekong Delta, the scope of my talk is Mekong Delta. It's like all the major rice production deltas in the world is facing big change caused by climate and human activity. There's climate for flood, subsidence, sun water intrusion, drought. On this lowland, okay, it's go very fast. On this lowland, and exacerbate the impacts are exacerbated by human activity like hydropower dams, groundwater extraction, and sun mining. So it's a cascading effect of the impact. And to give some element to answer to the question of the workshop, the role of EO for supporting decisions for improving food security at national and global scale. So for that, this talk is about the objective is to provide the mapping information of climate and human-related risks impacting rice land using in situ and satellite observation for the present time and model-based projection for the future for impact assessment and for taking measure of adaptation and mitigation. So for this work, we make use of R&D results from the heritage of rice land monitoring using EO data is mainly Sentinel-1 for this tropical site. We have rice map, phenology, cropping density, flood map regularly since 2016. And we have scientific results on salinity intrusion, land submersion, crop yield using EO and models. And we have also climate projection for Southeast Asia. The ongoing work is on methane emission from rice field using ALOS PANSAR and Sentinel-1 and in situ IoT. And this one, the last one is from Asia Rice CH4 project and the CNES Mérimée project and the GISDA Airbus TEOS 2 project. So from this bunch of data and maps, we have a multi-year observation of the impacts, and then it can help to understand the cause of the impacts. This one is for the flood damage of the rice on the right. Every year, the flood, the flood water come to the Delta Mekong, and the Mekong Delta, and the farmer used to avoid the flood season by planting the rice before and after that. But now, at the bottom, you can see that the annual variability of flood extent and timing, every year it changes. Importantly, the timing can change. And why the timing can change? Because one of the reasons is also the hydropower dams upstream that can release the water anytime. So this unpredictable flood extent and timing damage the rice crop downstream, the red pixel that you can see there. And the other example is for salinity intrusion. The map is on the yellow pixel is on the rice. Why we cannot grow rice everywhere? The farmers want to grow rice, but they cannot grow everywhere. And then we compare with our salinity isoline map here, and we can see the statistic that the 95% of the rice could be harvested when the salinity is less than 2 per 1,000. When you plant the rice, sometimes the salinity come in, and then you lose the harvest. And so we know now that we need the salinity less than 2 per 1,000. And then for the future projection, so colleagues in the Netherlands, they do the projection here, different climate scenario, RCP 2.6, 4.5, 8.5, and C11 rise, 25 centimeters, 50, 60 centimeters. And we look at the effect of climate alone, the first line of the table, and the effect by human activity, subsidence caused by water, groundwater exploitation, and riverbed level incision caused by sand mining. And so we have the map of future salinity, and we can calculate the loss of rice land. And so the loss of rice land suitable for rice because of salinity, because of the subsidence, and it's much more than the project rice yield. We did the rice yield with Horizon modern, and it's less than 7–10%. And then many examples like this, and we put together and to have to derive options for adaptation and mitigation. For the flood, for example, we adapt the crop calendar, salinity intrusion, reduce cropping density, not to grow rice where there are salinity or with the dry season, adapt the crop calendar or conversion of this land to other land use. And now when we put everything together, we have a multi-stressor mitigation, like regulation from upstream dams is outside our possibilities. And reducing cropping density is like an example. When you reduce because upstream there are 2 crops a year, because of the people put dike to grow crops during the food season, and then if they don't they don't grow crops during the wet season, they store the water there, and during the dry season, the water can be released to wash out the salinity downstream. So a lot of the cascading, somebody talked about this, cascading effect. Okay, and the most important, reducing human impact, sand and groundwater extraction. And the other one important for the rice is the methane emission. And we can use remote sensing to estimate the carbon emission from rice land for the country or globally, because rice paddy fields are one of the most important sources of atmospheric methane. And the most effective mitigation approach is to practice intermittent drainage. You need to drain the field. You don't need to have continuously float the field. And for that, we have the advanced SAR data to penetrate into the rice canopy in order to detect the water, underlying water. And for example, this image is an advanced SAR image, and we use, we test polarimetric SAR, scan SAR, everything, and we could, the scan SAR can give you a map of floated, non-floated rice under the vegetation. And this is our current work on methodology development. And we use the IoT for crowd data because in order to see where the water, the field with water or without water, is very time-consuming. We have manual assessment, but also automatic water level station. We put 30 of them in the field, and then you can see that we can follow by my phone the station, the water level of the station. The first case is they practice wetting and drying, and the second case, continuous floating. And then the low-cost methane emission measurement device that we are under development for our use soon. And here, interesting, we've worked with Thailand colleagues, the use of one dashboard, and this is developed with GISDA and Airbus. And here we have the map of methane emission from some district, few districts, because the view should be global or regional, but the action should be local. And so with this one, we have the map of rice phenology recon stage and the map of inundation status by Alois Pansar. And then we put them together in a model, and we have the here the emission factor from IPCC. We calculate the methane emission. So, meaning that here we have, if the continuous flooding in blue, CH4 amount, is higher than the drainage, the non-inundated. Okay, and we have also the water consumption, And the cost is important because people can have carbon credit as well. And then we take the action. Action here is if we make 70% of the fin with drainage and 30 without drainage, because traditionally all the fin are continuously flooding. And then we can gain how much? Here the issue is the present time, and right hand is action plan with more fin to be drained, and then the methane emission will be less, and water consumption less, and the cost also less. And so this kind of dashboard that the user want to play with in order to see which kind of district and which kind of fin, and people can play for their fin as well. And so, the final question, how to transfer EO science result into mitigation measure and alternative management tools? So first, close collaboration with national teams for co-development, user workshop and scientific training targeting young scientists, and information to decision makers. So this is an example, because we know that the decision makers, they don't read a scientific article. So in the project, we wrote a big book like this, and we handed to the authority, Vietnamese authority, during the COP26 and COP27. And here is what I have presented, some of the results there in the book. And now the most interesting thing is the Vietnam decided for 1 million of low emission, high quality rice. They advocate to have less rice and higher quality, lower emission, etc. And so many of the details are in agreement with what we have written. So we are very, very happy. And the last one, recommendation, EO data. The SAR data are well adapted to tropical region. So you can use it instead, in complement instead of your optical data. For example, we have demonstrated that the ratio of polarization could be used instead of NDVI, for example. And so long light to Sentinel-1 and NG data, and harmonize the C and N band ROSE and NISA alerts will be a must for global assessment of methane emission from rice and from wetland. Methodology, raw data collection investment is the key point, because anything could be done cannot be done without raw data. And IoT is something that you can use if the value, the measurement is physical. And also integrate observation of impacts by multiple sensors. Sometimes people use one impact, and have the measure of attenuation and mitigation, but it's the cascading effect. You need to have the whole picture. And the tool for stakeholder for testing different scenarios, okay? And how to go from R&D to operation, again, user uptake and partnership to co-develop methodology and tools for long-term operation and use. And this methodology can be adapted to the major rice-growing delta in Southeast Asia and worldwide. So thank you very much.
Thank you very much, Thuy. Would you have any question to Thuy? Yes, please. Can we have the mic over there?
Thank you very much for your presentation. You mentioned about carbon credits. What are the opportunities for EO on carbon credit mapping, and what will be the challenges? Thank you.
Okay. Then the carbon credit is when the country or the farmer or the district demonstrate that they have lowered the greenhouse gas by some means, by not cutting the trees, here not to reduce methane emission of the rice field. There will be an amount of money, but I'm not in the economic things. My colleagues in Thailand, they say, oh, you need to add this because there's a cost of that. How much if you reduce emission, greenhouse gas emission? And this is another canon. Yeah.
The question over there.
Yeah, great talk. I agree with what you said earlier in the last session that SAR is actually going to be like some major jumps in agricultural monitoring there. I was just wondering with the L-band, how confident are you that the L-band is detecting water beneath the canopy and not moisture in the leaves? And are you going to develop methods to use the biomass mission and P-band radar?
Okay, so I don't talk about biomass mission because biomass mission is a P-band is a 70 centimeters wavelength, and so you cannot see the scatterers very small like a leaf or a stem of the plant, and so it's penetrated, but we penetrate into the floating rice field. The rice will not be seen. But how low is the signal? Because you cannot, whether it's beyond the sensitivity of the thermal noise or something like that, yeah. So we need to check it after the launch, which will be in 1 year and 1 year from now, 1 year and a half. So prevent, thanks.
Thank you very much. I think that now this session is closed, but before closing, we would like to ask the audience if you have additional recommendations concerning this topic of agriculture under pressure and climate adaptation. But very quickly, because we have the next session just starting after. So yes, please.
So thanks again, Toy, for this excellent presentation. And I found it so important what you showed here. I think you started your work in the 90s, right? And it was ESA project funding at the beginning, and now you see you are going to an operational service. Excellent, yeah, with the methane emissions, wonderful. But could you give advice? How can we achieve this? That we really come from science to an operational service? Is there a secret that you learned? Can you give advice to that?
The secret is the co-development with people. Then I have a PhD student going back to Vietnam, for example, and for the development in Thailand, I just go and work with them. Our team work with them, develop together. Before we work together, there are no result, but now it's the team running everything. And in Vietnam, the team also running, giving one rice map a month to the ministry. So it's that you cannot from outside do something, you create the opportunity, but the co-development and for the people to do themselves. Yeah, thanks.
Thank you. Other recommendations from the audience? Suggestions?
If there is no more recommendation, maybe a few words to conclude. What we heard in this session is actually several presentations introducing very different nice applications for climate adaptation. And this could be an answer to the question we heard on Tuesday about, and what Heike mentioned, how can we get the uptake in a better way by decision maker or policy maker. And actually what we have seen here is really a way to do it, is actually to enrich the EO product with ancillary data. We have seen many soil, climate variables and so on, and also modeling, several kinds of models, which allow to go much further than EO product to get actually an impact to the policy maker or the decision process. But to do so, probably, we have to be careful. This does not prevent us to check the fitness of use of the EO product for that kind of application. Because further we go to the downstream, let's say, demonstration, less we pay attention to the EO product quality. And therefore, a key question for us is, please, we should check the fitness of use, to use, to make sure that we use the right EO product through the right decision process. This is one first question, one first recommendation. Another recommendation, as we have seen in the presentation, is to team up, like we saw from the FAO, teams up with other partners than remote sensing partner to make sure that what we are doing is relevant to user. And this was very clear in several presentations. And the example of Thuy Le Thuan about the uptake by the Vietnamese and the Thai government are related to the co-development with EO partner and non-EO partner. This is probably the secret for the uptake. And therefore, we can close this session, and then we would like to thank the speaker to have kept the time and to catch up the delay we have this morning. Thank you very much. There is a session coming on data integration, which is very natural transition because we just mentioned many ancillary data. We leave the floor to Marijn and colleagues. And Linda, sorry.
Okay, we're going to start this session on data integration. My name is Linda C. I work at the International Institute for Applied Systems Analysis, and I'm excited to chair this very interesting topic. And Marijn is going to introduce the first speaker.
Yeah, hello. Don't run away. I know we're keeping you from lunch, but you're not allowed to go to the Mensa, so stay here. So my name is Marijn van der Velde. I'm working at the Joint Research Center in the Food Security Unit. And we have a session here on data integration. And of course, with data integration comes observations across scales. And we have here presentations that are going to go from in situ photos to drones to very high resolution and high resolution observations, along with actual observations in the field to big administrative data. But we're going to start off with a presentation by Vito, by Laurens Tits from Vito, on actually the use of drones and drone sampling to increase the efficiency of drone surveys for agricultural applications. Please, Laurent, the floor is yours.
Okay, thank you very much for the introduction. Well, good morning, afternoon, everybody. So a bit of a different topic as we've seen so far, but there will be a link with satellites coming later on, I promise. So at Vito, we don't only work with satellites in agriculture, we also have a few people working on drones, and we're currently working on a new approach that we would like to share with you, as it has, according to us, quite a high potential of also increasing monitoring capabilities with satellites. So if we see how drones are currently being used in agriculture, there are various applications, and there's always this discussion on cost-benefit because it's quite costly, so when does it actually pay off to use drones? Then you see that the high-value cases, the cases where there's a lot of money going around, usually there could be a benefit by using drones. And there's a few examples shown here. But nevertheless, we see that sometimes there's still an issue in the uptake and the operationalization of it. And it has to do with a few factors. For example, if you look at the slow uptake by farmers for the variable rate application, like we can make all the fancy maps that you want, but farmers still struggle a bit to use it The machinery is not always equipped. You have data formats between different brands of machines that are not compatible, and so on and so on. So you see that the uptake itself is not that high. If you look from a more legal point of view, drones can stay in the air longer and longer. They can cover more and more area, but you have the regulation that you have to be able to see your drone at all times. So that restricts, again, the area you can cover in one flight, which is also sometimes a burden and more costly. And of course, there's also the increased availability of high-resolution satellite data, which covers kind of some of the needs for which drones are used and make them no longer applicable. But still, drones play their part, especially in those cases where you either need very high resolution, so really at a centimeter or even a millimeter resolution, or if you need high flexibility, if the timing of your flight is really important, if you cannot wait 1 or 2 days longer, you really need it now, then the drones can still play an important role. So just a few examples here for the high resolution. And you think about, for example, flowering count. You don't flower the plants don't flower that long, so it's really time restricted when you need that data. If we then look in Europe, there's finally a regulation to tell you for which types of drones you have to comply with which type of regulation. And you see that the commercial drones currently mainly being used are more at the lower end, so the heavy systems, for which a lot of regulations apply. You need to have a pilot license. You cannot fly in all the regions. You need to get permissions. So it's quite cumbersome to use them. And usually the users of the data cannot operate their drones themselves. So usually they have to hire people to do so, which again is more costly and less flexible. But if you look at the top end of that table, you see that the lightweight drones, the toys, if you like, what kids are buying nowadays to just play with in the garden, they're becoming more and more performant. The camera systems on top of them are more performant. The battery life is increasing, and they are very less restricted in how you use them. You don't need a pilot license to use them, for example. Anyone can use them. The farmers can use them themselves. So it's quite an easy tool. But they have some restrictions as well. So instead of using one large flight campaign with a big drone, you can also do multiple smaller flight campaigns with a small drone. And that's a bit what I want to talk about. It's a new approach that we are testing. And if you then look what the implications are in your actual data collection, traditionally, if you fly over a field, you need to collect a lot of images, and these images need to overlap quite a bit in order to make your orthomosaic and to get the stitching right. That's not possible with these small systems. The battery life is not good enough to do that. So we propose to go to a sampling strategy instead. So instead of flying over the whole field, just do a sampling strategy, measure some crucial areas only, and then process the data for these specific areas. So much more efficient, but again, it has some implications on your processing. Normally, you use the overlap between images. It's crucial to do your processing. So what we did here was fly over the field the traditional way, the normal way, with a lot of overlap. And then we flew over it again with barely or no overlap, and then see to what extent we can get the images to the same quality, to the extent that we can get the same amount of information out of them. But it has a lot of impact on the processing. You need a completely different approach, and so you need a completely different processing workflow for your data. That's something that's now ready. We have it. We have a drone processing software and tool available for different users that they are currently using. We now have this sampling strategy in there as well. So you no longer need to fly with high overlap. We can process individual images as well and get all the data out as you like. Just to give you a small example, so we did the test where we flew the same field in the two ways, traditionally and sampling. And just to give you some numbers, so the system we used for the flight on the left, it's 70K in total. The ones we used on the right, it's only 500 euros. So in terms of the cost for the material, it's already a big difference. If you then look at the flight time, instead of almost an hour that you need to fly, it's reduced to 12 minutes, and the data volume is also only a fraction of what you normally have. So it's quite a more efficient way of collecting data in the field. And what we have, so we have now the system, we have the ID, But of course, we want to see it's actually still useful for the different types of user of drone data. Because there is some loss of data, you cannot do all the same things. For example, if you have no overlap, you don't have any height information on your crops anymore. So we wanted to see, okay, to what extent is this still useful? And we're currently testing it out with a lot of different users. So for example, with the farmers themselves, if they go to the field, they need to do some actions. In the meantime, the drone is collecting the data. We're working with insurance companies to do damage assessments. And then, of course, the whole phenotyping environment with seed breeders and input suppliers. They use a lot of drone data. It's quite costly sometimes. So is this a gain in efficiency for them, yes or no? But not only for the industry, if you look at researchers as well, we collaborate with a lot of universities for drone data collection. It's always very difficult for them. And now if a researcher has to go to the field, that person can just take a small drone with him or her, collect the data while he's doing other data collections, and he has more information. So this is an example we did with a student, barely no training, and that person could collect the data as on the fly, and he could get information on the presence and the persistence of a very annoying weed that we have now in Belgium. And then maybe, like I said, I promised you a connection with the EO data. Once we start collecting drone data like this, and we can centralize it and make it available, publicly available, you can get a lot of data from that as well, and then you can start looking more towards the CalVal activities for EO data as well. There's some very interesting products you can get out of it. There's an example we did a long time ago with FCover on 5-meter resolution satellite data, where we try to do the link between the two. If you have this type of data, you can make it publicly available somewhere centralized. It can be used by the broader community as well, and it can become a very valuable source of information. So that's the end of my presentation. So some further recommendations. I think if you look at really the research side, it's a new idea. Like I mentioned, the sampling we showed is just a regular grid, but there are many other ways you can sample the field. So that's something that you can look at. Like I mentioned, the validation of certain EO products is definitely something to look. Also in support of the new satellite missions, I think there's quite a bit of potential. But what it will be really important is the way we handle that data. If it's a bit the same with all the in situ data, the discussions we had yesterday as well. A lot of people are collecting in situ data. They want to share it, they want to make it publicly available, but where do they need to do this? Currently, there's not really a place to do so. I think it's the same if we would go, or if this would become a thing, we will need that centralized place as well. Look at, for example, CDSE for satellites. You can think of something similar for drones as well, where you put the raw data and people can compute their own products from it. It's publicly available. You can connect easy to the satellites and so on. So I think that's definitely something to look at. So with this, I conclude my presentation. If you have any questions.
Thanks a lot, Laurent. Questions from the audience, please? Do we have a mic?
Thank you. For the comparison between drone-derived images and satellite imagery, what vegetation indexes do you use, and how much was the correlation between the two, let's say, sources? Thank you.
The example I showed is one from a while ago, just because we haven't been doing it right now. I think I just want to make the point that if you are starting to collect this data, this is something that we could be doing. We specifically did it for the FCover, but to be honest, yeah, it's 10 years ago. I can't remember we mainly did on FCover, but I can't remember the figures anymore, sorry. But if you want, I can look it up for you.
Very good. Yeah, we had another question here. Yeah.
Thank you very much, Lorenzo. Nice presentation, nice work. Maybe I missed this information, but I had some. My question was about the spectral setting of the drone that you use. So, what was this the sensor? Is it a multispectral sensor? Is it a hyperspectral sensor? because we have a hyperspectral sensor that we have a lot of difficulty on putting it on a drone. So I wonder what is that sensor that you're using and how that spectral bands of that sensor is actually correspond to the existing bandwidth of the, for example, Sentinel-2. Thank you.
Okay, excellent question. As I mentioned, we mainly work with the existing new systems like DJI, so it's RGB cameras already mounted on top of it. They don't have that flexibility of you buy a platform, you buy a camera, and you have to mount and integrate it. So for now, it's an RGB story. There's no hyperspectral, multispectral dimension, because we're really working on the concept of what could be the advantage of the sampling strategy and so on. And our users, like farmers, do they see a benefit in working this way or not? Once I think it becomes more operational, you could be looking at also including other types of cameras. But of course, they need to be available on these small commercial systems. It's not that easy. And then maybe regarding your question on the reflectance bands and how they correlate, that's also why we mentioned that you have the type of what we're doing right now, we don't do it at the reflectance level, also because compared to the bigger systems, you cannot really regulate the settings that well. And you have less control in your post-processing as well on the reflectances. So that's why it's mainly for the F-cover, like the derived products from your image that you can do the Calval activities. But not on the radiometric level, it's not suitable for that.
Okay, thanks very much. If we can move on to our next speaker. Thanks again for the presentation. Okay, we're now going to hear from Laura Martina Sanchez, and she's going to talk about integration between remote sensing and in situ photographs.
Hi everybody. So just to give you a context of my talk today, we all know that land cover information is really important. It's key for, thank you, for environmental monitoring. But if we focus on the talk that we are doing these days in this workshop, that is agriculture, is really important and key for planning, assessing, and monitoring. But we also learned that to generate these maps and other kinds of maps, we really require a lot of effort in kind of the information that we have, how we manage this information, and specifically to assess this information, we need in situ data. We know that in situ data and surveys especially are generally regarded as a reliable source of information for this kind of assessments. But we think also that the street level imagery, especially georeferenced street level imagery, can be a key component on the future assessment of these land cover products. And because of that, in this presentation, we will focus in 2 points. The first point will be, can we classify land cover from street level imagery using computer vision techniques? And once we do that, can we bridge the gap that exists actually between what we see in the street level imagery and what we see in the Earth observation land cover products? So first of all, I would like to talk to you about the data set that we are using that is called Lucas. I'm not going to enter much because I think all of us, we know a bit what it is, but mainly is a 2-grid sample, and in this 2-grid sample, they do a triennial in situ surveys where they select stratified samples from this grid, and after they do that, apart from other microdata, they go on field, they classify the land cover and land use, and they take images. Specifically, they take 5 images. The point image, so where the actual theoretical point GPS is, and then the cardinal directions, north, east, south, and west. So having this in mind, to implement our pipeline, what we did is mainly from these images, specifically Lucas 2018 images, what we did is select, first of all, a meaningful sample of these land cover classes all over Europe by biomes and by classes for sure. The second step, the second step that we did, it was to use these images and semantically segment them using a data set that is called AD20K, developed at MIT. We did this on inference mode, so we didn't train the algorithm, we just inference on that. And why do we do that? Because we need an abstraction layer of those images. Pixel here in RGB, it doesn't mean much, but if we have objects, the presence and absence of objects, and the abundance of those objects in an image, maybe using a random forest, what we can do is arrive to a conclusion of a proper land cover. So what we did is this, and here you can see just basic results. If you want to see more results, please just refer to our paper. But we can see that we actually have really good results, for sure for artificial land, but that's kind of an easy one. But generally, we get really reliable results. The ones that get a lower accuracy are the wetlands, and it's because mainly it is a really, really dynamic land cover class, so we cannot rely on the objects that are present on the image. We can rely on those objects maybe plus the geo-reference location of those pictures and maybe arrive to a conclusion. And also the second thing that I wanted to say is that using random forest help us to also understand what are the presence and absence of objects and the abundance of those arriving to a specific land cover class. So it gives you explainability on how one land cover class is what it is, right? So once we achieve this goal, the second thing that we wanted to do is to link this information back to the satellite, and because we are using Lucas and we have ground truth data also about these land covers, and we have this abstraction of objects, we wanted to explore what is the gap of the information between this in situ information regarding street level imagery and the Earth observation land cover products. So for that, what we did is to analyze Dynamic World, S3 and ESA World Cover 2020. I know there is a gap of 2 years, but this is the closest that we can get, and we thought that the land cover classes will mainly remain stable, but also to arrive to a reliable way of relating these two sources, street level imagery and Earth observation, we need to understand what are the minimum mapping unit that in Earth observation is kind of easy, it's 10 meters, but what is the observation window that we have? And in this case, in Lucas, we have 2 observation windows to assess this land cover. We first have one of 3 meters, that if it's homogeneous, this will be the main one, but if it's an heterogeneous land cover, then we will increase this extended observation to 10 meters. This is for Lucas, but this can be also done with general images like Mapillary has been shown before in previous presentations, just by calculating pseudo fields of view. So we can do this relationship on what we see in the street level imagery and what we see on the Earth observation. So first of all, to be able to compare, for sure, we did a land cover harmonization that I'm not going to enter much. But what I wanted to show you a bit is the results that we get. So in the y-axis, we can see the land cover classes from Lucas, and in the x-axis, we can see, first of all, dynamic world, then we see Esri, and then we see land cover, the world cover from ESA. So the darker colors that we see in the diagonal of the matrices, of the 3 matrices, are showing the best agreement, and we can see that there is a really nice agreement cohesively in the 3 products with artificial land, cropland, and woodland. That actually makes sense because those are land covers that tend to be big, generally speaking. And we can see that we also have consistency in the errors, no? For example, well, in the errors, no, in the disagreements, I would say. For example, we can see that, as we said before, wetlands is not really well behaved in this sense, and it's because it's a dynamic land cover, but we can also see specific cases where, for example, Esri has some problems on detecting properly grassland, where mainly all grasslands falls on cropland, or where world cover has also some issues detecting shrublands. And in general, we see that we have issues detecting bare soil. So just to go a bit on the visual information, here I'm showing you what is the relationship between the objects that we have in the images and the different products. And we can see bare soil actually cannot be maybe a reliable sort of in situ data and street level imagery because of the acquisition times. Because maybe the time that was acquired this image has nothing to do with the time that this product was created. So it makes sense that bare soil can fall on cropland or back again to bare soil. Here I'm going to show you these specific problems that we had before that I explained, where Esri, we can see that it really has problems detecting grasslands compared to the other 2 products, but we can see that the images that we have, it's really easy. It's almost 70% of the image is grass. So street level imagery is a key component to help maybe in the future validate these products and make them more accurate. And we see the same example with shrublands. Shrublands, we can see in the 3 maps in general that is a conflictive class. Even though dynamic world has a good behavior, we can see the Esri overestimates, and the ESA world cover actually doesn't even detect it. But when we see the distribution of the objects in our street level imagery is really easy. It's shrubs and stones and earth. So just having these three components, we know that in this area, in this pseudo field of view, we have a shrubland. So actually, this can be a reliable source of information, then again, for future accuracy of land cover maps. And lastly, I wanted to show you also the water body class. So sometimes we have water bodies, especially rivers that are big or ditches that are small, that are obstructed or they cannot be seen by the satellite. But specifically to the first example, I would like to tell you that this river actually is obstructed by the trees, but it can be fully mapped because it's big enough to be mapped, but it's not has been mapped by the three products. And here, then again, the street level imagery is showing you that it's really easy to see these objects and maybe relate it back again and maybe help for the future accuracy of those data and not rely only on in situ surveys that they tend to be really expensive. So having said that, I just want to arrive to my conclusions. So we think that the in situ surveys are key, as we said, for satellite products validation. They can detect areas or biomes where their products are failing, but they also can help to see objects that we are not able to fully map or directly map directly from the Earth observations. And my recommendation will be not to ESA, but in generally, to try to keep the temporal stability on these situ products, because sometimes we have products that they are every 3 years and suddenly they disappear and we feel a little bit orphan because we just lost this data. And then I would like to also put attention on the street level imagery and semantic segmentation as we did here, that it was full in inference, because it's really used on urban planning and it's really used on urban planning related back to Earth observation. So this is really exploit, this is kind of images for monitoring urban planning and things like that. But the problem is, for agriculture, we do not have proper definitions of objects related to those images. And because of that, we created a data set, a semantic segmentation data set with objects that are focused on agriculture. And if you are interested, it's open, it's free, and everybody can access. And yeah, that would be all.
Thanks very much. 10 seconds over. That's impressive. Yes. Okay, do we have any questions for Laura?
That's good. Oh,
yep.
There's a hand.
Sure.
There's another one there.
Could you comment on the proportion of street view that you can classify out of the one you cannot classify, and what is the reliability of this classification?
The reliability of this classification is good, but if we compare back to the Earth observation, we really have to rely on the metadata of the images, because we need to understand the pseudo field of view. In this case with Lucas, it was easy because we have a window of observation, so that was easy to derive. But if we move outside Lucas, will be really reliable information if we use the metadata of these images that right now we always have metadata. And sorry, I missed the second question. See, the classification, we try it and we test it and it's really good. The only problems that we might have, and actually I have a second slide, is when we have topography problems, right? When we have big hills or when we have, like in this down part below, objects that are obstructed. Therefore, the image here might not be really reliable from the in situ ground truth that we get. But if we say here that this is a shrubland, actually it's shrubland in this area. But then again, to relate back to Earth observation, we need this minimum mapping unit towards the observation. So I will go for the metadata and the pseudo field of view of calculation, yeah.
Okay, thanks. There was a second question. We still have time.
Very quickly, did you test the performance of the method with other products, not based on Earth observation? I'm thinking, in the case of Spain, the CIOSE project that is more detailed.
No, we didn't, but actually it will be really nice because then we can see if we can actually get even more resolution since we have small windows of observation of 2 meters. So yeah, maybe we can talk later and you can give me the source, what are the sources, and we can give it a go, yeah, for sure. Thank you. Okay, thank you.
Okay, great. Thank you very much, Laura.
Okay, thanks a lot. We move to the third presentation, and we have the pleasure to listen to Stefan Fritz from YASA, and he's going to talk to us about a new high-quality global hybrid herbaceous annual cropland map for the year 2019.
Yeah, thank you very much. I have to be really fast, so I will also look at this watch. This work was done in collaboration with the Joint Research Center, and the final output of the map is being used in the JRC's operational anomaly detection system, ASAP. So just for information on, thanks all the co-authors for having contributed a lot, and also the colleagues in the JRC. There is exciting news. The current cropland products we are getting are converging. Here we are talking about herbaceous cropland. Also the definitions, luckily, are similar, not the same. The two latest products, UMD cropland, or also called GLAD cropland. This is the latest product which provides time series starting from the year 2020. It though includes forage and also it includes fallow. It is 30-meter resolution. Then we have a latest product, also single thematic product, World Cereal. It was made for the year 2020, also for the year 2021. It happens that for the year 2021, the quality is actually better. It is mapping active, so-called active cropland. There are some exceptions. It excludes fallow, and this is a big difference between the other UMD product and makes it more difficult also for the integration. It is, though, a 10-meter product. In order to then combine the two, we aggregated to 500 meter, and 500 meter is good enough for early warning kind of application. So that was the motivation to do that. When you compare the two products, and this is again the good news, there is a lot of convergence. So 73% full agreement on when you even look at presence and absence. So if you look at if the 500 meter pixel has any cropland in it, and the other product has no cropland, then there is only 17% disagreement. So that is really good news. If you compare these products with other land cover products, there's much more disagreement on the cropland side. You can also do this by comparing pixel frequencies in these two products, in putting these 500 meter pixels into bins and looking how many pixels have these percentages. And what you will see is that between 10% and 90%, there's a lot of agreement between these two, but the disagreement happens really in the lower and in the very high percentages. There's one explanation actually that World Cereal picks up, especially in Africa, a lot of cropland which is between this 0 and 10%, so it's not very dense cropland. There's here and there some cropland happening, and that is much better picked up, especially in Africa, by World Cereal, but it's not so well picked up in GLAD croplands, and I can show you this later. One way of combining these two products is to look at the regional differences and the regional accuracies, and then pick the best product based on this regional accuracy assessment. Can't go here into detail, but what you can then do is, based on this information, you pick which product is better, and it happens that GLAD cropland is better in the US and in Asia, and World Cereal is, according to the internal validation being done by these products better in Europe, Africa, Australia, and Latin and South America. What you can then do, so you can then, based on that, do some initial integration. But what you can then also do is you can look at disagreement between these maps and look where one product has more predominance of cropland versus the other, and focus on those areas. For that, you need to aggregate on a coarser grid. We did 20 by 20 kilometers, and then count the pixels which are disagreeing based on different criteria. We applied so-called density disagreement, density disagreeing being defined as more than 80% of within this 500-meter pixels disagreeing, and once you identify disagreeing, you count the number of pixels in the 20 by 20 kilometer boxes, and you come then up with the amount of hectares disagreeing, and you see this represented in the color schemes. What you can see again here, and what I outlined before, these green areas here in Africa, they show up really strongly. This is presence and absence disagreeing, where world cereal shows cropland has some degree of cropland in terms of presence absence, but UMD cropland doesn't have it. But there's many other areas, and in some place UMD is better, in some other places the glatt cropland, the world cereal is better. What we then did, and there could be endless work, you can look at places of very high resolution and sentinel time series and say which map is better at which location. And we mostly focused on what UMD or glatt croplands and world cereal, but we started also to use other maps because we found that there are places where both maps were wrong and where we needed to use, and these products were mentioned before, like Esri, World Cover, and other products where we then integrate with that. You can't see some of this in terms of color because they're so small areas, but the big areas you can see are where we think world cereal is more correct when zooming into this very high resolution, when delineating these areas. There's also an area, interestingly, in Russia, in the former Soviet Union area, Kazakhstan, where they both complement each other because these fields are so large, and world cereals, because also of the definition of actual active cropland, sometimes misses a lot of areas, so they are actually complementary in these areas because of these larger fields. This is how this kind of mapping looks like. You identify here where you just see these large areas of disagreement, where in this case the glatt cropland is actually detecting cropland, and even though in Africa world cereal is missing it, you see this is quite homogeneous kind of missing cropland of world cereal in this area. It's one of the hotspots. It's actually hotspot number 5. When you flip to this kind of hotspot map, hotspot 5, this is where this is occurring in actually very large areas. And then you can actually just draw and correct and then do your best. You can do this endlessly, but we focused initially on these hotspot areas. And just to show you a few more examples of these hotspot areas, there is another hotspot, that's hotspot 2, so that's in Latin America, where one map says there is cropland, and the other map, which is world cereal, says there is no cropland, and when you zoom in and when you look at it a bit more, you see that these are actually pasture areas, and you find also street level, so we see again the advantage of having street level photography. This helps you a lot to understand landscapes and get the context where there is pasture. These are just some areas, and this is another area, hotspot 8 in Australia. Again, the same thing. These are pasture areas. You see also fences many times around. This covers large area which have, in this case, been misclassified by the glatt cropland product. Coming to the conclusion, the initial validation which we are doing ongoing, and there's going to be a paper published on that in environmental research letters, shows that the hybrid product is of better quality, even though the definitions are slightly different. But also the hybrid map is derived from continental integration, which I've shown you, but we are now seeing that if we use just the GLAD cropland as a base map, and then we just update and improve with world serial, rather than doing this continental integration, we're getting very similar results. So this continental integration we can see that this didn't help us too much. And the 10 minutes are over, but I'm also asked to give some recommendations for, in general for the session. So as we know, in situ data is really absolutely critical. Ideally, we want this in situ data to be fully fair, free, and open. I think there needs to be more investment and more work on this type of data integration we are doing, because it is really important to benchmark products against each other. But there is also, I think, a lot of research still needed to optimize sampling design, also for validation. As we know, it's extremely costly to go to the field and to collect data. When there are no roads, it's extremely expensive. So there needs to be more work on how this could be optimized and how we can still do some level of accuracy assessment without having to go in the middle of the field, where there might be some new methods coming if there is investment on how this can still be satisfactorily done. Just one more last point, if you allow me. These products we are making many times are just one-off products and not operational, but I think the world needs really an operational crop type global Copernicus service. And with that, I stop. Thank you.
I think we will take the global Copernicus service further at the JRC and EEA. We have time for some questions.
Thank you for your presentation, and I'm Peng Yuyin Fao. I'm also working in the hybrid of multiple global cropland data site as one new data site. So can you tell more details about your principle for the hybrid in your slide? Thank you.
So can you, sorry, I didn't fully catch it.
Can you tell more about the principle of you are working on hybrid the multiple products?
What do you mean with principle?
As you're using cropland from world cereal and using the grassland from UMD cropland.
Okay. Oh yeah. You looked very precisely. Yeah, I didn't go into detail. Thanks a lot for that. So what happened? So this was quite rarely the case, but what happened? We could not. We saw on the very high resolution that there was cropland, but none of the current maps represent this cropland. So in order to find that cropland, we had to use grassland from some other product because it needed to come from somewhere. The forest was correctly classified, and we found that a grassland a layer from another product was actually doing the job in that specific small area. So that's why we had to do it that way. But that was an exception, and it didn't happen very often, but we needed to address this kind of issue. So that's how we got around it, but it's not optimal. Yeah, thanks.
I saw there were some other questions, so please, if you have another question. Yeah, Christoph.
Do you think that this kind of map that you make can also be used to improve future versions of the individual maps? And maybe a follow-up question, resource efficiency, is it better to not invest in improving the individual maps, but rather make this hybrid map where you can really focus on the problem areas? It's maybe a bit provocative, but...
Yeah. No, I think these are very valid points, and I think the answer is very clear. Yes, I think when you do this disagreement it helps you a lot to focus on areas where you can improve and where you can also potentially put more samples. So I think there are many ways. Indeed, if you have resources and you can do it, you can focus on these areas and reprocess those areas. You can also, to some degree, see this kind of visual interpretation as some additional training points you're giving to the system. Yeah, so I think it goes all hand in hand. And the point to be made is that this work really needs to be done, and this work is very labor intensive, but if you don't do it, you don't identify places where your map is wrong and where you can improve it. Thanks.
Okay, great. Thanks very much. Okay. Okay, next, so we're going to move on to our final talk by Aisha Chan. Okay, she's going to talk about the integration of administrative data from Eurocrops with agriculture-based text data from Wikipedia using a large language model.
Okay. So hello everyone, my name is Aisha and I am a PhD student at the Technical University of Munich. And here today I am going to present my project called Knowledge Distillation from Big Administrative Data. So to begin with, what exactly is administrative data? Well, these are data sets collected by different government agencies or administrative agencies to support and enable government services. So these include things like cadastral data or the much mentioned GSA, geospatial application data sets. We consider this as a treasure trove of data because they are continuously collected and maintained over a wide variety of fields. This means that it has a huge potential for a huge range of possible reference data for eventual training. As a proof of concept, we demonstrated it through the Eurocrops initiative, where we, through the GSA farmers' declarations, we created a European-wide harmonized reference data for field geometries, including cultivated crops. So at the heart of Eurocrops is this hierarchical crop and agriculture taxonomy known as HCAT, which basically serve as this reference scheme for us to map these crop descriptors provided to us from different paying agencies. This enables European-wide analysis as well as provide a central database for all publicly available data. You can read more about this in our paper, or I still have my poster up in the tent. So, despite the success of Eurocrops, this is done through lots of blood and pain and tears. It requires a lot of manual effort. It has been 5 years of manual Googling, Wikipedia article searches, and attempts to find the best descriptor for all the possible crops declared. It's already gone through 2 PhD students, numerous student assistants, and lots of help from our active GitHub community, which many of our audiences actually contributed in. So what we usually get is something like this. This is a data set from the from Czech Republic in 2023, and obviously it's in Czech. I don't speak Czech, which is why I consulted the help of Google and DeepL. And normally it works decently well, but sometimes you have this questionable thing called diabetes. Yes, that's a corp called diabetes. Sure, I don't believe that, which is why I continue to consult the greater Google. And apparently he still thinks it's diabetes. Even Wikipedia agrees so. So after much frustration, I eventually consulted my Czech-speaking friend, and turns out it's sugar beet. Our dear Czech paying agency decided to not include the second part of this term, which made it very difficult for me to find out that this is sugar beet. And this whole translation process is actually just the simple part of this manual mapping, because there's an answer to this, like it's a one-to-one translation. The real pain is the mapping decision. Here you see a list of grasses, and this brings us to the point of what kind of granularity do I want to map these plants to? Do I really want to create this 2,000 or 3,000, whatever, crop hierarchical harmonized thing? It's not meaningful, you know, so I really can't have each individual grass being a class. So then comes the question, what kind of granularity? Like, do I just map it based on its ornamental properties, or some of these grasses are basically pasture crops, like what do I do with it? Or do I do it by purpose, like fodder for humans or ornamental? Or do I do it for environment, because these are protected areas or things like that? So it's a lot of decisions you have to make, and you really only can make it if you have expert information, which you usually don't. And through this Eurocrops project, we managed to identify all these problems we have to solve, which is administrative data sets almost always occur in different languages. They have different data structures. They have different descriptions. Sometimes it's spring wheat, other times it's summer wheat. They also have very different granularity. Sometimes you have just pasture meadow. Other times you actually have the exact grass that's being grown there. You also have very decentralized access to all the data sets. And manual harmonization, as you have seen, is very painful and time-consuming and very error-prone if you don't have any expert input. So the idea is, how about we use language models to automate this process? I'm sure everyone's heard of GPT, but what exactly do these large language models mean? So I'm going to quote a very well-cited paper in the field. It's by Brown et al., and they say language models are full-shot learners. What does that mean? It means that you don't need a special curated data set. You can just feed it in with large amounts of text corpus, and it can do the job. And the generations are not task-specific. You can do everything with it. In the context of crops, it's not just crop classification. You can also have crop yield predictions and things like that. And this is only possible because it fed in so much data, it's seen lots of examples, and also because of the transformer model, which provided a very wide window of context. This is also known as autoregressive training, where the goal of this training process is to predict the next word based on the existing words. Now that we have some understanding of LLMs, let's convince GPT to do my job for me. So I provided GPT with the same information as I have. In this case, the crops from Brandenburg in 2023. And I also provided them the full HCAT list that we curated. And I tell them the exact outputs I want, which are the translated names and the equivalent HCAT mapping. And voila. So as you can see, it does relatively well. The only thing I would really reject is the fact that wetlands are other permanent crops, but yeah, it did pretty well. You might say, this is a very simple example. This is German, you know, it's pretty well trained, blah, blah, blah. Well, let's look at my pain and bane of existence, this list of Czech grasses. So this was actually done by GPT-4o, which is the latest version of GPT. And at first glance, you can already tell that it did really well in terms of HCAT mapping. It's almost identical to the one I did manually. But if you look closer, you would start realizing that many of these translations are incorrect. These are not different names of the common names, but these are actually completely different plants. This also made me realize that when I tested it with GPT 3.5, they gave the exact same translations. So what this says is that they made almost no progress in translation, but they actually made a huge leap in mapping. So with 3.5, it was not able to map to HCAT at all. I got not known and other for everything. But here, I actually have proper classes being mapped to. And what this says is that it's gone beyond just simple semantic matching. It's gone into actual understanding of what these plant names represent. So that this particular grass belongs to this family. So, but that being said, I still can't say, hey, GPT has done my job for me. So I tried different methods in an attempt to improve the performance. One of it was either, there were two ideas. So first was, how about let's just train a model with crop-specific knowledge, or just fine-tune it with crop-specific knowledge. Well, I tried both. The first, it wasn't very successful because my corpus wasn't big enough. And then even if I want to increase my corpus, I didn't have enough resources to do it because this is a very, very resource-intensive process. So I thought back again, okay, if I can't train something, can I at least do something in inference? Well, yes. This is called retrieval augmented generation. What essentially it does is during inference, you can provide it with some kind of context so that it can verify the generation to the context you provided. So in this case, I provided a Wikipedia page on belladonna in both German and English. So, and I queried llama here. What is the scientific name? And because this can be directly found in the Wikipedia article, it had a very high groundedness, which means it completely agrees with context. However, when I asked for the translation's groundedness, it's almost 0, which means it's neutral. The context does not support or disagree with it. So what this says is that it's great if I can find great reference data, but not so great if I can't find great reference data. So I'm back to the chicken and egg question, really. And through this small little experiment, what I've learned is that essentially LLMs are not better in performance when it comes to machine translation models. But that's not the beauty of it. The beauty of it is that it goes beyond these singular tasks and are capable of understanding. I didn't tell GPT what a table is. I just told them, yeah, I have these headings. Now feed it into a table and populate that table for me, you know? It also had some kind of domain knowledge. These acronyms here, I had no idea what they meant. I didn't bother translating them, but somehow they managed to translate it for me. So, and I verified it. This is accurate. So yeah, LLMs, we believe LLMs has a huge amount of potential, and if we are given more data, it can even just automate the whole creation of HCAT for us, and eventually even extend to other fields like traffic, reference data generation. But to be able to do that, this brings me nicely to my recommendations. Can we please have better access to administrative data? I sound like a broken record now. It's been mentioned again and again, but we really don't have access to these data sets. Like, after 5 years of Eurocrops, we still are missing multiple countries. Germany is still only releasing data from 3 states, so please give us better access to data. And if possible, we would also love to have more compute resources and more funding. Thank you so much, and it's time for questions, I hope.
Okay, super. Questions? Aisha. I know people want lunch. Oh, okay, we've got at least 2 questions. Great.
Hi, Sam.
Sam, why don't
Hello?
you go second? Yeah.
Oh.
Yeah, thank you. Thanks for presentation. Really interesting work. I'm working at the UC Louvain in Belgium, and I work a lot with LPIS data. And I see a lot that there are some difference in the names between one year to another. I was wondering if you were managing this. Do you work only in 1 year? And do you think it would be possible to extend it to other year and computationally feasible to update this every year maybe, or do a general and a common database? Thank you.
Yeah, so as of right now, manually speaking, I have only done 1 year. I've started working on multi-years for Wallonia, and I understand that pain. Yeah, but theoretically with GPT, you can just do it all at once because they just, they have semantic understanding of the terms, and you just need to define the correct granularity to map it to. So like I said, the grasses, they identify the overarching class of the overarching family and mapped it to the whole class instead of whatever individual grass it was or unknown. So yeah.
Really nice presentation, thank you. A comment and a question. We do this kind of stuff in production, not as quite as thoroughly as you've done, so it's really good to see like you take it further and also find the limits. You compared GPT 3.5 and 4.0, and that maybe you might call it reasoning of this higher level HCAP mapping is better. The other axis of improvement of LLMs at the moment is about context length. And some of the newest ones, you could imagine putting all of the crop taxonomies from all of the ELPIS data sets across Europe, even the ones we don't have yet, of all the years, plus all of your proposed translations in the context window in a single prompt. Do you think being able to do that kind of thing has utility, or that it's kind of irrelevant?
So to begin with, I'm not sure that's possible. When you're talking about the context window, the bigger it is, the more resources it's going to take. So you're going to need more memory space. So right now, my small version of RAG, it actually only takes a very small context. So within the whole document provided, it has a small context window that it just takes information from it and then kind of do a verification of the groundedness, but it does not take in the whole document. It only takes in part of the document at once and then batches it through. So it's also part of research to how to do it efficiently and all that, but to do it all at once, I don't think it's actually computationally possible yet.
It
but
is.
Yeah, is it?
Gemini 1.5, one of Google's models, has a context window length of 1 million tokens. It can
Really?
process the entire Harry Potter series of books in its context window in one prompt. So
Okay.
it's not cheap, that's true, but it's possible. And a different approach to RAG, which,
Okay.
because it can then reason over the whole thing, not just chunks. So maybe that's worth exploring.
Okay.
Thanks.
Okay, thanks. So in the interest of time, we'll say thank you. But maybe you can catch Aisha at lunch if you want to have further conversations. Okay, so we know that we're holding you up from lunch, but before we do that, we'd like to open the floor to any further recommendations. So you saw the different recommendations that were made, and also data integration is huge. You can see that there are many different examples of data integration, just even in those 4 talks. So can I open the floor to anyone who would have recommendations for ESA, more generally on the Earth observation side, that we can then report back?
Can we have the mic again? Sorry. Here.
I see this question a bit different. I know that now that we have the big IX data, it's a kind of processing approach that we want to homogenize it after the data is already born or managed. But as this data is derived by a central legislation based on a single logic of direct payments, I think it's more efficient, more reliable to standardize this data at the beginning, because we have the legal tools for that, and then ask the member states to publish the data according to a given standard. And there had been, this logic had been started a few years ago, but it seems that with the new cap regulation, it's somehow a bit blocked again, because although we give higher subsidiarity for the member states to implement their schemes, which is a very good logic, but what we are talking about here is the standardization of the data format, the data structure like OGC and so on. And this is another level, and it does not go opposite to the way of subsidiarity and find your own performance of the cap. No, this is simply data management issue, and I think this should be clarified for the decision makers, and then it might be better.
Yeah, thanks a lot. We made notes, and we will, put your recommendation in our records, and we will also, within the Commission, keep also pushing for these sort of ideas through Agri, but also on the other side, there is indeed also activities ongoing to standardize better within even the Commission, a corporate crop code list. But I agree, for now we are trying to stitch back things together that have originated on the paying agencies level. That's maybe the first thing. Once we've shown that that is done, we could think of a second phase where this could be done more automated. Let's move. That's a dream. I know for many people this is something that has ongoing for many, many years, including ourselves. But I think that recently there have been several developments that are pushing things in the right direction. Not to the extent of what you have suggested and recommended, but at least to something that is opening up also at EU level. So thanks for that recommendation. Do we have any other recommendations? Yeah, please.
Sorry. Yes. So working with data all this time, all these years, since 2015 after the Sentinels, it is surprising that while we require data from farmers, while we require those data to be reliable from farmers, cooperatives, etc., we have not made it mandatory for the member states to provide those data in a harmonized way. This is amazing. Amazing. I don't know how many times I have to say it. It's amazing. They just have to provide harmonized data. It's as simple as that. It's just a decision. Nothing else needs to be made. No budget, whatever. No research on that. Provide the data. That's it.
So I just want to make one point. If I was a farmer, right, I'm just thinking, I think we have to be a little bit careful. I fully agree with what you said, but if you are a farmer and there's another thing you're told by the EU to do, right, it doesn't go down very well. So you have been reporting as a farmer in your local language, with your local kind of context. It could potentially pose quite some burden on the farmer. I just want to say that it might not be as easy as we think in these processes. Yeah, but okay, that's I fully agree with. Yeah. Yeah. Sure.
And you know the most weird thing, that scientifically it's really easy. Each crop has a code in this international species notification book, or I don't know how the proper English name, but you know what I mean. But no one ever has started to translate the large variety of crops. And we all know that with the greening, it came back that the member states inserted like the crop table growth 5 times larger than it used to be before. Okay, this is all okay. But nobody got the point to link it to this international species register and ask the member states, the paying agency or a science, whoever, to take the data and to share the data with these informations attached to it.
Yeah. No, I think this is a very relevant discussion, and one thing that I can do, at least, I think we are all more or less in agreement, but the process is moving slowly. In 2 weeks from now, there is a conference also in Rome called the Ajax Inter-Exchange Community Conference or something, ICE, the old Mars conference. And so there will be another 350, 400 people. There will be all the paying agencies present. And so we will also make sure that we have at least a few slides to hammer down on this point once again. Yeah, there is movement in this space. But yeah, it's not as straightforward as we think. But I think the good thing is that there's also something like maybe peer pressure. We have seen recently after the 2018 regulation on the GSA that much more of the data has become publicly available. Not maybe in a standardized way yet, but we have now up to, how many? 16, 17, 18 different paying agencies that release the data. So there's good developments there.
Is there an answer to why the rest of them do not do it?
Well, you have to go really to each individual paying agency. I think there's a variety of reasons for this. There may be capacity issues, there may be other issues in relation to how does the control system work, what rules are in place, and maybe what fears are in place in relation to this system. But I think it's moving. I mean, yeah, we just need to keep up the pressure. And I think what is nice also to see from the academic world, including the work we just saw from the University in München, that there is ideas on how to do some of these things. And so it is our task to bring those ideas closer to the policymakers, and I think that's what we're working on as well.
Yeah, and well, just also to say that we maybe need also to thank the fact that PhD students are doing this. I think this is a really valuable data set, and I mean, I think none of us would ever want to do that effort, if not for a PhD. But let's also look on the other side, which is from the mapping perspective, we actually have the same issue. And I mean, we are not agreeing on classes that we're mapping. I mean, we see it also in Stefan's presentation. I mean, we try to do there like a hybrid map, but the definitions differ. And usually this is also because the funders, they stress still too much just map accuracy. And the classes that we map, they don't matter. I mean, as long as you reach some sort of a minimum accuracy, it's fine. And then in the end, as a map producer, what do? You define your classes in such way with the given constraints of the input data streams or the temporal range that you can process. You do whatever you can to just reach that map accuracy. And then you end up with all these kind of map products which have different definitions, starting from cropland, which is already different, but then also even going to crop type. Everyone uses different definitions. So maybe already from ITTs that are out there, we should really ask the Commission and ESA to step away from just stressing minimum accuracy. And okay, if you start stressing that you need some sort of a common class legend or something like that, then you need to take into account that the accuracies for some classes are going to be lower. But as long as you stress only accuracy, then you just get incompatible maps that only focus on accuracy.
Yeah, that's an excellent recommendation. I see that now we have to go for lunch. So I think we will close the session, but if you have any input, then you can also always contact Linda or me. And with that, we'd also like to thank the panelists and thank you for your input.
Good afternoon. Can I just ask you if you could come a bit closer? Because I think we're already becoming a bit fewer now. There were people already left. So it would be nice if we could occupy the first row places, the beige colored seats instead of the blue ones. It's not so easy. Okay, I think we can start. So welcome to this last technical session. It's halfway between a panel and a session, so last one before the closing session. My name is Espen Volden, working here in the science section in Esrin. I will let my colleague Joshua introduce himself.
I'm Josh Gray. I'm a visiting scientist here. I'm an assistant professor at North Carolina State University in the United States, but I've been here for the past 10 months in the context of the Science Hub.
So the objective of this very short session of half an hour is to present to you an idea that we have for a new activity. So we are just in the kind of early stages in ESA of discussing what we should do. And we'd like to share that with you here. It's not so often that we do that, maybe, that we have an initial idea and we share it with them to help us shaping it. So I will do a little introduction to this idea, and then Josh will show one example of what we could do or what could be an important subject for what we could do. And then after that, we will open up for discussion to go back, maybe showing some of my slides and see if we can have some feedback from you for the last 15 minutes. So if we could have the first slide. So we have called it Experiment Preparing for New Sentinels for Crops and Soils. I will go and manage this show. So the starting point of this is that we wonder if we could set up some experiment focusing on having lots of in situ data and other data over either one small site or maybe two. That could help us in really solve one or several research questions related to soils and crops in an agricultural context. So that's the kind of starting point. And the kind of first elements of outline of this idea was that
We should at least cover one growing season. We should really take benefit of synergies across sensors and of new products. We should, with this experiment, we should create a nice data set, lots of different in situ data in particular, that can be usable also for other activities that we will have in the future, maybe both from ESA side, from EC side, and from other activities. We should use data that can be considered precursors for the new Sentinel expansion missions, because this idea, we will implement it within our Sentinel user program context. Hopefully, we could use some first data from the FLEX mission, at least if we maybe extend the experiment a bit after the original timeline. We would like to, if possible, use ESA campaign date. We have campaigns preparing for this new Sentinel expansion missions, and also benefit from existing in situ networks. So to more or less extent, it's possible to do one or the other. If we work on only one site, maybe it's not so difficult, it's not so easy to achieve all this, but we can try. And we would like to try also to use then a bit more some innovative measurements for the in situ measurements, and also exploit the Internet of Things. So that was the outline of the idea. And then just couple of starting with these trade-offs. So should we do just one site and have really lots of measurements in this site? Or should we try to go to 2 sites because it's important, because we will have different environments, different conditions, even if we then will have less budget for each site, so less measurements? Is it important to cover 2 seasons, or can we stick with one? Or is it important that we create a site where there can be also some continuity for the future? Or is it, do you think that it could be kind of best use of the money to do a really rich site for 1 year, and we try to use that to solve some scientific question? These are type of trade-offs. And what is important is, of course, that we find out is what kind of data do we really need for this experiment? But in order to say that, of course, the first thing we need to do is to find out what is really the research question that we need to address. So here I list some questions which could be the question that would guide this experiment. Could it be, for example, how to determine stressors that are causing an observed impact on crop health or development? Starting first by distinguishing between biotic and abiotic stressors? Or should we go all the way to try to improve yield prediction by solving then a number of questions, like the first one maybe, but that we really try to look at different factors influencing on the final yield? Should we rather look at characterizing the soil, crop, and runoff part of the nutrient cycle, so maybe focus on nitrogen, at least we know we can do something, and do this in an agriculture context, so starting from fertilizers, etc., and the agriculture practices, and then try to look at this part of the nutrient cycle. Should we also include the carbon cycle and look at that between the soil and the crops and back again? The emissions. Should we rather focus on improving the water balance for an agricultural field, trying to really estimate this in best possible way with using all these different types of EO data that we can have access to in addition to in situ data? Or is the more important thing maybe to look at crop phenology and try to monitor that in a better way, because that will also help us to for example, better predict the influence of different stressors, which have different impacts in different crop phenology stages, and in the end on the yield. So it's maybe that the most important things. So what should be the priority research question for our experiment? Are these questions too narrow or too wide for such an experience? Maybe I should say also something, I didn't put it on the slide yet, for the budget. We are thinking about an experience which would be less than, I mean, a project of less than 1 million euros, but maybe not far away. So just that you have this in mind when we think about what we could possibly do. Should we focus really on agriculture, or would it be better to open up to more general vegetation? So some of these questions. And so the last one I said was about the last idea here was for crop phenology. And for this, I will now leave the word to Josh to say something about what could be possible, what our data needed, etc.
Okay, so again, my name is Josh Gray, and most of the work that I've done has focused on crops, remotely sensing of crops, yield, and things like this. And one thing that I've come to appreciate is how important phenology is when looking at many different aspects of crops. But phenology is important more broadly beyond crops, right? It's very important in structuring the exchange of energy and mass between the biosphere and the atmosphere. It controls migratory patterns and trophic relationships across the food web. It's obviously of agricultural and cultural significance. In fact, probably second only to astronomical observations, phenology are probably our oldest types of scientific observations that are available. We can go back to the 8th century in Japan with records of cherry blossoms, and even further for viticultural records in this region. It's also a sensitive and integrative climate indicator, so it's very understandable by the public. Everybody can see when the daffodils bloom or when the cherry blossoms bloom, and we can understand how that changes from year to year. Here's some work that we did a while ago to show how the carbon cycle relates to the length of the growing season. And this was particularly focused on the timing of spring. And so the basic, it's a bit of an eye chart. But the focus here is that if you get an earlier spring, you have a longer carbon uptake period, leads to greater gross primary productivity, and also at the end of the day, greater net ecosystem exchange. We know this from both satellite remotely sensed data that it's changing. We know this from direct eddy covariance measurements, its importance in the carbon cycle. We know that it's changing in response to climate. So here's some work predominantly in the spring across Europe. We can see the advancement of spring, and to a lesser extent, we have conflicting, contrasting trends for the autumnal dates. So we know that this remotely sensed data is very important, but we don't often know exactly what it means on the ground. Again, most of the work has been on spring and temperature and forest, so we would like to expand those into other ecosystem types. One opportunity that's very low cost and yet yields quite a lot of bang for the buck are a technology called PhenoCam. So some of you may be familiar with these data. It's a global network right now of probably over 700 type 1 sites, which means they all have the same protocols and the same types of cameras. And so they're typically mounted on flex towers or other sort of existing infrastructure. A mast with power and comms is all you need. And it's a very low cost camera, so under $1,000 you can deploy this type of camera. It takes an oblique view of a canopy, and you can see some of the snapshots of some of those over 700 sites here. So quite a lot of diversity. Some are looking over really, tens to hundreds of square kilometers. Some are even below the canopy. Some are looking at only a few tens of square meters in a large variety of different biome types. So this includes a lot of agricultural sites, grassland sites, in addition to the original forest-focused sites. From those camera images, it takes a picture every 5 minutes, sends it to a centralized server where it's processed with a routine set of software to turn it into the time series that you can see at the bottom. So this is sort of analogous to an NDVI time series. This is a greenness time series. So these are only RGB cameras. There's been some work on whether near infrared would make a big difference. Turns out the greenness at this, for this oblique view is actually plenty good for the purpose. They've been used extensively in understanding not only the phenology at those particular sites. Again, they're co-located oftentimes with eddy covariance flux measurements, and so it's very helpful to understand the state of the forest or the state of the leaf canopy, wherever it may be, in understanding those exchanges. So this would be a very powerful technology to deploy at one of these sites. Again, it would take a minute part of the budget, and it's basically hands-off. Until things break, it just goes and it uploads its photos just by itself. It also offers a kind of intermediate step in between the organismal scale phenological observations that you would make when you go out and walk and record, maybe the crop progress, for instance, or whether flowers have bloomed or leaves have colored or emerged, and the satellite perspective. So it's very useful in understanding whether the things that we get from satellite at a coarser resolution, what that means on the ground. It's also, again, they're photos, they're archived, and so you can reprocess them. You can change the area of interest on the image, so look at a smaller or a larger or a particular part of that field of view and reprocess the whole thing. So it's very powerful, and again, very, very low cost. On the other end of the spectrum, the gold standard are the actual organismal scale observations. And so these have been done for, probably, like I said, thousands of years with different types of ad hoc measurement protocols. Obviously, within crops, we have, for many crops, maize and wheat, for instance, there are defined stages of crop development, so you can go out and see what proportion of the field has entered particular stages, like for maize, has it entered silking, or a seed head formation happened in a grassland or something like this. But we have benefited from a centralized protocol that's developed by the National Phenology Network that's based in the US, but this has been adopted more broadly, a standardized way of making these types of observations. So here you can see just an example data collection sheet along with some of the photographs of the instances of the physiological state of the tree canopy, or the leaves in this case. So these are obviously much more intensive observations to make. Somebody has to go out and do those sorts of observations, but you can create very nice complementary data sets to the phenocams and to the satellite land surface phenology with this sort of thing across a number of different physiological states. The biggest difference between these and the previous ones, Landsat or land surface phenology and phenocams, this has actual physiological significance and meaning, right? So the previous ones were just looking at basically relative thresholds of crossing of greenness. Here we're actually talking about particularly meaningful things. So we all know that these are very important when it comes to understanding crops. Some of the work we've been hearing about for the past couple of days about climate sensitivities and things like this. You can't get that right unless you understand what physiological stage the crop is at when it's exposed to those temperatures. So for instance, we did some experiments and showed that you can get actually the whole sign of the effect completely wrong, because whether or not a maize crop experiences really warm, dry weather right at silking or right after silking has a completely different effect on the yield determinant. So that's just one example of why it's important, not just with regards to plant canopies in general, but crops in particular. So to conclude, I just want to make a case that, in my opinion, I think plant phenology should be a part of this observation suite for this intended experiment. And I would recommend that we use phenocams as a really low cost, coupled with a direct observation protocol that's adapted to the particular, whatever ends up being planted there, right? So if we're looking at a particular type of crop, we should adapt those physiological stages, but use that same NPN measurement protocol. And together, those things can really help us understand the land surface phenology products that we can make from the Sentinel. And then it goes beyond that, right? Because it's very important if we have co-located eddy covariance flux measurements, transpiration measurements, things like this, in understanding what we're seeing there. So I'd just like to thank you and conclude with that.
Okay, thank you, Josh. Could you go back to the first presentation again? Thank you. So this, just exactly this slide, or maybe Yes, what you have been talking, Josh, is kind of related to this sixth questionnaire. As one alternative, what is the priority? Maybe we could first get some input on if we went for this as the priority for the activity. Josh has explained type of data that can be used. Are there some other suggestions for what kind of data we would need if we would really address the crop phenology as a kind of priority in our experiment? Yes, Roshanak, do we have a mic?
Hi, thank you for this. I think George covered everything in terms of the aspects. It's just depending on the crop, there's various different things that might be of interest. So narrowing down maybe as a prototype or a first step, it's something to consider. And I would add that for crop process-based modeling, phenology is a key input in there in calibrations. And in the crop modeling community, there has been attempts to use remote sensing data to inform the models of where in the time the crop is. So there is another opportunity there to engage with a different community and task maybe a couple more things in the same spot. Yep.
Okay, thank you. So we have one support for the phenology subject. Are the comments then still on for phenology maybe? So what data would be needed if we go for this? And how to narrow down?
Actually, I think you mentioned a very good point about the phenological cameras. And a few years ago, we did some study on this phenological camera, installing phenological camera and actually directly linking them to the Sentinel-2 data with my colleagues Anton Firling. And what was one of the challenges that we faced when we processed this phenological data from phenocams was that the angle of the observation sometimes was not ideal, and the shadow, and did not actually allow us to benefit the way that we wanted to benefit from these phenocams. And we had installed a couple of phenocams along the study side. However, one of the challenges, I think it was the angle or the view angle was not what we wanted, and it was not matching the observation angle and also the sun azimuth angle and so on. So if such a study is going to be placed, and if there's going to be phenological cameras installed in the field, I would go for a kind of multi-angle phenological camera. So I would not only install one phenological camera in one station, but I would install a multi-angle observation to be done in any location. That would help to interpret the BRDF effect, any shadow effect. This is very important, I think. Yeah. Thank you.
Thank you, Roshanak. Any other comments on the phenology topic? Or what really we should look at, and what type of data we would need? Yes.
So I think for first to decide which crop, and maybe we want to get the big bread baskets like wheat and maize, and management of the crop. So it's kind of basic agronomy would be needed when it was sown, which crop, which variety, what is the management. Different places will have different managements, even in terms of row spacing, which could impact the geometry of the crop and how it grows, essentially. If to be put in a farm scenario, then what was the fertilizing management if there is impact of pests and disease, how that was managed. If it's to be put on a trial set, like on-farm trial with big, not tiny, small trials, but like big trials, are we looking at tackling also one of the other questions at the same time? For example, a nitrogen trial within that area, so you need to know all those little things. And in the end, ultimately, you also need yield, right? Because you want to know how that performed. So this is on top of my head the kind of information you would need. Potentially soil information. If you're putting a camera there, maybe it's easy to put a soil probe as well and make it, get all the cheap sensors and plug in the same thing. I think this is the kind of data that's really needed to drive any kind of crop phenology assessment.
Okay, thank you. So if we want to do the phenology properly, we will also at the same time get quite good data for looking at the nitrogen cycle. Yeah, yeah, that's a good observation. Any other comments to the phenology? Yes, please.
Okay, thank you, Josh, for the nice overview about the importance of phenocams. I was wondering if this exercise goes on, is actually the actual plan of installing the phenocams on the EC Flex Tower or not? Because in that case, the importance is having all other data associated with them that are also important for the study of vegetation.
Well, we're right at the planning stages, so I'll take that as an argument for including EC and co-locating all the other MET measurements and flex measurements with the phenocams. Typically, again, they're mounted on existing towers just for the co-location of those observations. And so I agree with you that the synergy between having those observations is key. So Espen will mark that as a vote for eddy covariance.
Thank you. Yes.
Yeah, so I have two questions or comments. So first, you mentioned one or two sites. So I'm not sure if you want to characterize a variety of phenological stage. Of course, you will need quite some time, because that's what is important and interesting. Is of course the change of the given date for a given phenological stage, so could be limiting for some of the application.
Yep.
And then, yeah, I think for the modelers community, basically for the yield forecasting, what is very important is the phenological stage, like the BBCH stage, really specific. And so this, I don't know. Of course, phenocam are really useful to basically give information about the growing and so on, but this is really what is the key, I think, if you want to improve. So probably something to take into consideration in the way you collect data also on the field.
Okay, thank you, Rafael. Yes, we have two more.
Hello. From my experience, there is missing the temperature patterns, air temperature and also soil temperature, and then plant available water. That's totally different than just volumetric measure or something like this. And then soil microbiology, fungi bacteria ratio is also missing from the picture. Thank you.
Okay, thank you. Yes, Tui. Mic is coming.
Okay, I may have missed the first part of the discussion, but from phenology, what's it for? For example, for our crop monitoring, rice monitoring, we know that the people need to know exactly where is the end of tillering of the plant and flowering, because they need to give water there at those stages and to give the fertilizer there, and not any time. And this is one thing. And for the modeling, the crop model like Horizon, also we need exactly the timing of the, not just the start of season, but all the phenology. And then we, a lot of colleagues working on phenology assessment with radar data, because of the temporal profile not disturbed by anything, and so it's very quite clear. And so that I was wondering whether we could not make it more general for the people to use this kind of observation.
Sorry, to use some more general.
Use of Sentinel-1 for this kind of crops. I have no experience with other crops, but I think that this should be done. Yeah, because the change in the biomass and change in the structure of the plant and change in many things, so it could be seen from the temporal profile of the radar. For optical, it's more difficult because you cannot have the data every 6 days or because of the clouds. Yeah.
Sure, thank you. Thank you, Tui. And yes.
Yeah, I just want to comment on this crop only or more generally vegetation. I think for the phenology experiment, it is very advantageous to have crops. Why? I mean, we had here an agricultural community, so maybe that is the answer is evident, but the reason is that with crops you can have a much wider field of experiments. You cannot change a forest, yeah? But for the crops you can have different seeding dates. The fertilization plays a role on phenology, so you have different fertilization practice, and even the soil has a role on phenology. If you have a low water holding capacity, it matures earlier. So we could measure a lot of information in a relatively small area. I think that is quite helpful. And if there is some biodiversity strips and natural areas, wonderful, cover them as well. But the design of the experiment, to my opinion, should concentrate on crops. And if we do so, I would strongly recommend to have at least 2 test sites. Why? Because there's often a test site affected mainly by availability or non-availability of rainfall. So the water reduced yield there, like maybe in Italy, and in the northern countries is more, there are other factors, and that we really cover at least the 2 different systems where maybe illnesses play a larger role.
Okay, thank you, Heike.
Just a super quick one. I would say that if we can characterize better some specific stages during the that are more challenging to identify as part of the phenology, something that is very relevant is the emergence date, because that's key for lots of modeling, and actually that's the difficult part. If you say, oh, let's characterize the peak of the season, well, that's kind of easy. So maybe try to allocate a little bit more of efforts towards how well we can characterize the emergence date, and with kind of error bars saying, okay, within this window, we can see for some specific crops the emergence date.
Okay, thank you for that proposal for more focus.
Okay, coming from the plant breeding mindset, it's like when we talk about phenology, this is a fairly multidisciplinary topic, and I think starting communicating with different communities, I think would be the first starting point. The colleague here just mentioned about the crop modeling, and but also like we can do a lot from breeding plots and high throughput phenotyping data that can be upscaled, and replicating models that can be generated through that towards farmers' fields and towards bigger fields that can be detected by the spatial resolution from orbital platforms. I think all of that, it's sort of linked, actually. And we shouldn't ignore this multidisciplinary thing and start trying to push further into this and gathering together these different communities and try to leverage on these things that actually it's happening on thousands of plots every day, you know? So my suggestion would be like really try to make this bridge.
Okay, yes, thank you. That could be an interesting opportunity for doing that, yeah, yeah. Any more comments? It seems at least there is interest for phenology in the room. Maybe we can maybe we can look at also at the other questions here. Are there any ideas from, so in addition to phenology, has been seen as an important possible focus for the experiment? Is one of the other 5 that you think is particularly important? If you take the first one, for example, about the stressors, is this a subject where we could really advance if we made such an experiment with limited area, but really lots of different data, different types together? You think that this is a topic where we really could make some advances? Yes, yes. Please.
Yeah, from a risk management perspective, I think what stress, which is very interesting to monitor, is frost on perennial crops, or frost on grapes, frost on apples, on other fruits, because this is something that is becoming more and more important, because with the warm weather, this kind of crop blooms earlier. And it's a topic which is very acute, I would say. I'm not sure we can do anything about it, but if we would manage to monitor frost, late frost on blooming or on perennial crop, it would be really useful for at least for the government and insurance business. Yeah.
Okay, thank you.
I'm Mirko Boschetti from CNR. I have just some doubt about the first question. If an experiment we are thinking about, 1 site or 2 sites, short, you say in the other slide, few years or maybe a long time serious, if we can reply to that. I mean, in particular, we cannot handle biotic stressor. I mean, we should do experiment using pests and diseases. It's not, you can do that only in a control plot level experiment, and abiotic depend on the year. So if we have a long-term experiment, we can get the situation like Heike was said before. In Italy, maybe is a rainfall problem, and in the north others. So what Francelino was commenting about, connecting with phenotyping activity, that could be a reason. So it means that we're going to change the scale. It's still a remote sensing approach or remote sensing plus modeling, but not, let's say, a satellite observation. So if we want to really see how we can determine it from remote, from signal, whatever signal it is, those kind of problem, maybe we should really think about an experimental, control experimental facility that can generate thousands. We see the importance of numbers for artificial intelligence or machine learning approach. So in that case, and there is a community, the phenotyping community is doing this kind of activity and using sensing activity. Sometimes they use it in a qualitative way because they want just to detect the response of genetics. So if there is statistical significant difference between genetics, we could do something more that we do quantitative retrieval of the status of those crops. But I don't think that a single site with a purpose to monitor from space could reply to the first topic. So we should, or it is a long-term site, then we will come across to that problem sooner or later, or else we should do a mixed, that the same site could be a scaling up approach with something that can be observed from remote, from space, and other has to be controlling the field with sensing.
Yeah. Okay, thank you. Thank you, Mirko. Yes. Okay. It's faster over there.
Thank you. I was thinking that if we have limited resources and time, then maybe we should try out an everything is very important for agriculture, of course, but maybe we should try an experiment that could be crop agnostic, because this is the main problem. If you talk about yield prediction, that you talk about crop specific services. So if you go for, I mean, the issue of fertilization is huge now due to the cost of it and, of course, the new CAP. So if we are to address an issue that's really important for the farmers and the farmers community in general, and we do it in a way that we can replicate it in different geographical regions and in different crops as well, and maybe if we can do it in a way that we can also include this new discussion about carbon and carbon credits and carbon market, which is huge also in the European Union, maybe this way, by taking aside the crop-specific issues and the time that you need in order to control biotic or abiotic stressors, then maybe in this way you can have an experiment that will actually make an impact very quickly in a big number of farmers.
Okay, thank you. Thank you for that point. Any other?
Yes.
We had, yes.
Thank you. The question was what's important from those points that are highlighted at the moment. So for me, the fourth question that carbon as well, actually it is about carbon. In my experience, the soil organic carbon determines, when we look at field variations, where and how biotic and abiotic stresses occur. It's all about the yield also, and soil characteristics, and about application of fertilizers. The soil carbon determines how much nitrogen can I apply, what are the production zones. And it's all about water through the carbon also. Yeah, thank you.
Okay, thank you very much. I discover now that it's almost 3:45, so I think we will have to close. So thank you very much for all your inputs. That was very helpful. And you will see hopefully this autumn that there will be something coming out with some inspiration from this discussion. So thank you very much, everybody. So then we can move to the closing session where we will have summaries from each of the sessions. So yeah, I think for the first session summary, I think the co-chairs have left, so I will have to step in. Okay, we wait a little bit before it's on, that would say. I saw that. Okay, perfect. Sorry. Great. So the first session that we had was about new missions to agri-space, and I'd like to show some of the highlights for this. We had first presentations of the new Sentinel expansion missions and the next generation. I'm going to not go into details. Then we had a presentation about Constellar, so 30-meter thermal data we will have soon, hopefully after October 2024, with the 5 satellites that should give up to a daily revisit. And this one could provide very nice synergy with LSTM. We had a presentation on the Prisma mission, so the 30-meter resolution hyperspectral data, and we already saw that with this type of data, that you could make such spectroscopy-based products, for example, the crop residue coverage, or monitor the crop development stages. We also had a presentation on NISAR, which is also very, very close to launch, scheduled for 2024. Where we will have a L-band and S-band at 10-meter resolution and a revisit of 12 days. So this is also a precursor for us for the ROSE-L mission. And at last, presentation on the high thermal mission HydroSat, which will provide 50-meter thermal data up to daily revisit again, and also planned for launch this year. And they showed also a service being developed for evapotranspiration and irrigation based on sharpened thermal EO. So it looks like we have much to look forward to, and even during this year. Some of the recommendations for this mission was to try to do create synergies between institutional missions and the commercial missions. I mean, we saw a nice example presented by Ben on the LSTM, where between the institutions, we already created nice synergies between LSTM and SPG and Trishna. But the recommendation were also to really create a synergy with the commercial mission, and the kind of the major benefit from this could be the temporal revisit. It was also mentioned the interest in quality verification of the EU data provided by the missions, and also on how the data will be made available to the users and how we will help the uptake of this data by the users. Also recommendation to work on the data policy to make the data available to wider audience, and to consider the wider context, so beyond the Earth's observation, for the retrieval of required agriculture information. And last, to try to develop application, making use of complementaries between the institution missions and the new space, so linked to the first recommendation. So that were the recommendations from the first session. So please, can we have the next? And if the co-chairs, sorry? Okay, but next one is, okay. Soil and crop. Christoph or Martin? Okay.
This is very much prepared. Oh yeah, go on. From long ago. Yeah, okay. So we had the morning session on soil and crop monitoring together with Martin. And in the session, for those who don't remember, most of us probably, we discussed a wide range of monitoring applications from early R&D activities, focusing on the new hyperspectral experimental missions, but also to like really operational dashboards. If you remember FAO presenting on the WAPOR counter to bridge the gap between consolidated data products and end users. So this was really not really a very focused session. We had a lot of different things, but that's maybe also good, from very R&D, early stage, to all the way to operations, which I think is one of the main challenges we face as a community. And the overarching theme remains the need for harmonized and open reference data. I mean, we've seen it in the many sessions that came afterwards. To train and to validate methods and the long-term continuity and also the expansion of the Copernicus program was one of the first times that it was mentioned there, but also in many sessions that came after. Some specific highlights. So we had, I think, 2 presentations using experimental hyperspectral data from Prisma and EnMAP for new applications. So one was on plant water monitoring, the other on estimating and predicting crop nutrients using hyperspectral data. And then there was the multi-year GSA, or geospatial application, parcel declarations. I think Martin also really wants to put out the word again. We heard it a few times. LPIS is not something that we should use anymore as a name. No, it needs to be GSA, geospatial application. So from now on, no LPIS, GSA. So they harmonized it into the CHEAP database to have the multi-year harmonized data from the GSA building upon Eurocrops that holds unprecedented reference data. We've seen that. It enables innovative method development, parcel delineation algorithms, crop type algorithms, adding crop rotation to improve crop mapping accuracy, develop new in-season crop mapping approaches were just 2 examples presented by JRC on how this data can be used. The WAPOR accounter was an example dashboard that bridges the gap between data products and end users. That's usually a step that we miss. And NRT harvest monitoring in Ukraine using planet data and unsupervised clustering methods was a very specific example where it was presented that with the high resolution planet data, harvest could be predicted fairly accurately. Okay, so the recommendations, there were 2 major recommendations. So in situ data as a priority, and it needs to be open, was one of the first times again here that it was highlighted. Many times thereafter. The GSA remains extremely useful. We need more countries to open this up. It has to be pushed politically, has been repeatedly stated. We also need to define larger test areas, commercial farms. I think Heike was raising that point where we can have open data going beyond just crop types, but also including a lot of data on farm management that can be opened up to the community. We had some suggestions that similar partnerships with farmers need to be built outside Europe, for example in Australia, but we as Europe can really play a leading role on how this can be organized. We need to also push for a larger budget share because it's a huge Copernicus program, but only a very small part at the moment goes to in situ data collection and sharing. So we really need to be pushing for more budget share going to that part as well. And then for the remote sensing, data processing, and sensor design, we need more focused efforts on standardized pre-processing workflows. Usually pre-processing is just one thing that has been taken for granted, but we as a community are not in agreement yet on whether we need to do no pre-processing at all or as much pre-processing as we can. Everyone has some results going into one or the other direction. We really need some benchmarking on the pre-processing steps itself so that we can put out some guidelines that not everyone needs to reinvent the wheel. Standardized data access in terms of stack catalogs and cloud-optimized geotiffs so that our products that we create can be found, can be ingested into platforms easily, and can be reused. Focus on the upcoming SWIR bands. That's also something with the current Sentinel-2 missions, but also the next generation Sentinel-2, something we need to focus on. And then with the hyperspectral data that's there now and also the upcoming hyperspectral data, there will need to be some fusion to be done between the current optical missions and then the hyperspectral data to also increase spatial and temporal resolution. Finally, we need consolidated guidance on methods that work. FAO was raising that point, like there's so much out there, but it's for us very hard to find out what is actually working well in operations, and we need continued efforts to improve and operationalize them, stepping away from purely the R&D, but also making sure that things go in operations, and that end users like FAO also know what to use, what works and what not. That, I think, was it from our side.
Do we have Mark North? Yes. Mark is there. Great.
Okay. Yeah, there's
No, the layout has changed. We had quite a variety of different presentations. So we made the summary, but I see that someone has played with the bullets. So now you have a bullet soup coming at you. But okay, I'll do my best. The first presentation was on the Geodata for Agriculture and Water program. So this is really a big thing. So that is the satellite-based services for smallholder farmers. And there, if you look at the numbers, more than 4 million smallholders reached, about 1.2 million users, decreased use of inputs, increased production, higher income for farmers. So, and if you look at the areas where this works, it's insurance, services for pastoralists, high-value crop advice like vegetables, pepper, and some diseases like late blight in potato. Then the second presentation was on germination insurance for smallholder farmers in Africa, and there we have developed all the parameters that are needed in our pilot in Ghana. Farmers consultant with seed companies and other insurance providers discussed, and farmers think this germination insurance is very relevant for them, and the combination with yield insurance is also interesting, and we are exploring that. The third presentation was on the farm-scale water accounting model in Italy, and there they had a success in estimating over-extraction and working on compliance with the WFD, the Water Framework Directive, and the Italian government regulations. They developed a groundwater management tool and farm-scale water balance and a better estimation of the crop coefficient using remote sensing. The fourth presentation was on Australia, near real-time monitoring of irrigation water use per farm by combining satellite and in-situ information. So they succeeded in improved irrigation area mapping, irrigation water use estimates using a concept that was developed on hydrologically similar pixels, and then calculating the incremental IT. And the good news there is that there's a paying client and there's opportunities for scaling up to other countries. Then we went to Egypt for the crop phenology at field scale in the Nile Delta. There the outcome of the test was that there was no significant improvement of Sentu-like if you use that compared to Sentinel-2, but a good agreement in Sentu-like and Planet Scope. And there are opportunities to study the climate shift effect on crop phenology and thus support agricultural practices of smallholders in Egypt. Then the last presentations looked at mitigating food security challenges in Afghanistan with geospatial, and they used remote sensing and field data for weed monitoring and DVI and water management intervention. They were especially interested in flood analysis with optical radar, GLOFAS, and the WI, and they analyzed the trenches because that's an indication of water harvesting, and they plan to make use of vapor to improve their operations. Recommendations, general recommendations that can be synthesized from the different presentations, so that coincides a bit. For developing countries, having successful implementation of activities, especially when it's innovative, like things with remote sensing, that takes time, often more time than you expect. A user-centered approach that was echoed in many of the presentations, and digital inclusion using active monitoring and evaluation mechanism is needed. Bundling of services for smallholders that gives additional benefits. And very important one, smallholder farmers are not likely to pay for services.
So you should establish links with other actors in the value chain, like input providers, off-takers, financial institutions, etc. Education and trust remain crucial success factors when working with smallholder farmers. That came also out of several presentations. Better soil data needed for good fertilizer advice. So this is a very specific one. I'm not going to echo the higher temporal and spatial resolution, etc., that we all want, but because that will come back in other summaries as well, I think. And then what also came out of several presentations is that you have to develop not only your services, but also your service delivery in such a flexible way that when your clients or your target group comes with different things, with different requirements, that you can adapt it. And you also need that as a basis for scaling up, because the conditions in different places and the requirements of the people will be different. Then what is very important, and also I think in other sessions, you have to find ways to establish and maintain your in situ data infrastructure. That is very important, and find mechanisms to promote and facilitate open and free data sharing. And then the last one, on that satellite-based services implementation should take into account collaboration between research and industry, clearly communicate with end users, and consider their internal decision-making processes, and be ready to integrate future EO missions. So that echoes also a bit the flexibility that we just talked about. So that was the summary and the recommendations. Thank you very much.
How do I switch? Next. Okay, so our session was on impact on climate and environment. Again, here we had very diversified presentations. So the first presentation was regarding the nitrogen use efficiency, and there was a nice framework presented to improve nitrogen use efficiency using Earth observation, in situ data, and also other types of data. It was highlighted that the nitrogen efficiency is still a central pain point for farmers and also for an environment. Here, one of the conclusions was also that physical crop models are necessary for impact assessment, especially in the changing climate. The next presentation was regarding the EO market segment. There was an analysis of EO market segment usefulness for various let's say segments, and here for climate, environment, and biodiversity applications, we've seen the highest percentage. So here, EO market can really be very useful. Okay, sorry, I lost myself. Okay. Then, of course, it can. We've seen in the presentation. We've seen the blockchain approach that could also serve for the food and agriculture, and insurance, and finance segment. The next presentation was about the cap controlling, and we had the nice widget-based apps that enable paying agencies to get fast access to the information on the parcel level. And then the next presentation was about the landscape features and the importance of landscape features on so important effect of the landscape features on farmland biodiversity. And here, one of the conclusions was that the potential use of Earth observation data has not been fully exploited yet. Then there are a couple of challenges in this area. So at present, only the woodland is monitored from the Copernicus, with also some issues of overestimation. So this is still something that could be improved and studied. Then the next presentation we had about the impact. Sorry, I didn't write it, so I'm a bit lost. Okay, there was a presentation on the use of machine learning to assess the impact of agricultural treatment, cultivation practices on the environment. And then the last presentation finally was 6 years of probably observations for oil palm plantations. And some recommendations. Okay, so the main recommendations, of course, here we know that providing farmers with information to support decision making should be the final goal of Earth observation-based services. It is quite straightforward. Then integration of Earth observation data and physical model, that is essential. Of course, machine learning and integration or hybrid approaches combining benefits of physical and AI models that should be further researched. Then again, I think recommendation that is we've seen almost in every session, open source farm reference data sets with good quality are needed and should be available for the larger community. Here also improvement for CAP monitoring services still requires including additional machine learning algorithms. Then for landscape features, we should work with the high resolution remote sensing products. And finally, finally, the final conclusion here for monitoring industrial plantations that should be also considered in the framework of EUDR. I think it's all. Let's see. Yes. Next one.
Thank you, Magda. So do we have sorry. Do we have Belen or Michel in the room? Yes.
Okay, yield forecasting session. I will try to make a summary. We had a lot of presentation about really focused on in forecasting and mainly at the field level. But we have seen also example at the subnational level in the first day with the keynote speaker. So we have seen that in various of these presentations, Sentinel-1 was found to be improving the accuracy on yield forecasting when using in combination with Sentinel-2. SWIR bands were also found to be useful beside typical VIs or biophysical variables. GDD normalization also played a role in increasing the accuracy in various presentations. What we observe is that while gridded metadata, meteorological variables are often used at the subnational for the forecasting at the subnational level, they were not used at the field level. We also observe, and this regards the data-driven methods, general challenges in estimating the yield of an unseen year. So when they were doing leave one year out calibration validation, poor performances were observed in a number of presentation. However, we have also seen examples on how to, let's say, reduce the effect of this reduced length of the time series, probably introducing this error in the leave 1 year out method by the use of crop growth model in conjunction with Earth observation data to provide yield forecast in the full absence of ground data. And this was shown for Ukraine. Yeah. Coming to recommendation, once again, we have seen it, we have heard it for many sessions, the importance of in situ data, and here quantity, quality, and the availability of long-term time series. So multi-annual time series to sample all the possible, or at least a few climate realization. And also a need to use harmonized collection data and of course make data public. A few presentations reported on limitation of Sentinel-2 spatial resolution for application in smallholder farmers, and so probably Sentinel-2 next generation will be very useful on this. All the presentation also underline the importance of mission continuity. We have seen we had a problem with Sentinel-1, and in general I believe that it would be a crisis of the sector, of the yield forecasting sector, if one of the Sentinel-2 fails. Progress in cloud masking were recognized. Sentinel-2 cloudless was taken as an example, but still improvements in the masking are perceived as needed. Potential improvements reported from some of the presenters about using LSTM, so which is very much welcome. There was a recommendation for harmonizing and agreeing on metric for the accuracy, and also for splitting validation and test. And here I reiterate for those working in yield forecasting, I reiterate the invitation to join the AGML initiative that was proposed by Ioannis on Monday, which is a place where to discuss metrics, take in international agreement on how to evaluate and intercompare model. Final recommendation, it's an example that we got from FAO, but it's probably similar to what I've seen today from Letuan, and they basically showed the importance of understanding the user needs, co-design and co-develop, to guarantee the long-term sustainability of the operational product. And they showed the example in Malawi, Namibia, but the idea is probably that if we start operational program and we want them to be there after a few years, these are really important features. And this is it for crop yield estimation and forecasting.
Do we have Sophie or Inbal in the room? No? Okay. Did somebody agree to do the presentation on their behalf? Okay. Since we are very late with respect to schedules, so I think maybe we will skip the summary slide. Recommendation is also a long one. Sorry. I mean, I could read very quickly through it, but I think for the sake of time, we will have I mentioned that we will have the report with the slides later. So I think we will go to next one, water resources intelligence. I guess that's the one also. We don't have Livia or Jacopo. Oh, we have Jacopo. Please, Jacopo.
Okay, this is the summary of the session on water resources intelligence. I had the pleasure to co-chair with Livia Peiser from FAO. Short summary, we saw several presentations showing that the monitoring of irrigation dynamics through multi-source satellite data is feasible, but of course the room for improvement is large. One common issue that arises from the presentations of these sessions, and also I can see of other sessions, is the lack of in situ reference data. That is one of the major challenges actually to be faced, and actually this is also in the recommendations. Then we saw that many methods relying on several EO products do exist, and probably we should standardize somehow or them or made it somehow comparable. We also saw that satellite data are offering the possibility of monitoring irrigation impacts on freshwater availability, particularly interesting over areas that are already facing water scarcity. With satellite data, we can also assess or, however, monitor benefit of irrigation modernization strategies. And also we saw presentations that were focused over Northern Africa, and here we discovered something that actually we already know, but it's a confirmation that satellite data are very useful to monitor areas that are scarcely monitored by in-situ data. So, recommendations, we had the first one on the need of land surface temperature and soil moisture at higher resolution. This is something needed. There is also the point of integrating information on agricultural practices into in-situ databases. There is an hope for future missions aimed at reducing or allowing to reduce, however, spatio-temporal mismatch between satellite data and irrigation dynamics. This is something that is essential to properly monitor irrigation dynamics from space. And also, again, we come back to the need of high-quality in-situ data sets. This is something that I think is very clear from the whole workshop. Then we highlighted that long time is needed to adopt digital services when available by water authorities. There was a suggestion of integrating the WEPOR dataset into the Copernicus data space ecosystem. Then there was a point raised by Luca during the question time, because we saw a lot of presentations based on machine learning. So we have, from one side, machine learning approaches, and on the other side, process-based approaches. And probably now it's time that the relative communities should somehow interact with each other. Then another point that probably is now needed is a comparison of the many methods that are currently available for irrigation monitoring. There is also the need of considering operational aspects of ETA algorithms, and also a final remark that probably it's good to look at irrigation monitoring from space in its entirety, so by looking at concurrently timing, so detection, mapping, quantification, all the aspects of irrigation. And that's all from this session.
Thank you very much, Jacopo. Please, Tui.
Okay, so this is the section about drought, pests, and other stressors. So the session addressed multi-source data for multi-stressor, 1 paper, for drought, 3 papers, and for pests, 2 papers. And multiple stress has been addressed separately for different sites, crop and condition, like salinity for rice, looking for wheat and for water stress for maize, and a different site. And some applications are very local, and when global scale is addressed, the approaches still remain qualitative. It was said that there was a mismatch between scan of EU products and the reporting outcome in spatial maps. Need additional consolidation because for statistical reporting. Most contributions use statistical regression approaches, although some attempts to establish a physical-based model has been given, for example, soil moisture in Africa. Quantification of indicators is still a challenge, and most work are still in R&D. Involvement of stakeholders need to move to operations. Recommendation. We need to guarantee the access to contextual data to facilitate the access to ancillary data in the public domain. To make available the links to sensitive data, for example, socio-economic vulnerability data in Europe and globally, particularly in developing countries. To involve the stakeholders in the whole process, from the definition of the objective until the validation of the result, and in the follow-on exploitation of the result. The discussion, precise definition of quantitative indicator needed. For example, when we say crop failure, how percentage of crop failure, pest impact, etc. Evaluation of uncertainty. Is uncertainty evaluate with what kind of preference, with the training sample or by the user, etc. The use of EO information, we need to use EO information, which is the best proxy for each of the stressors. For example, thermal for drought, red edge or swear for pest, SAR for water content. Whatever the stressor, and the community used to work with what they have in hand. Yeah. And integration of multi-source EO data should be further exploited. And the last thing is analysis of multiple stressors, cascading effect should be explored, not one by one, but globally. And so I can add that we have to observe quite globally in order to see also globally, regionally, to see the cascading effect and different effects like the drought before and then the pest afterwards, then okay. So we finished this session. Thank you.
Thank you very much, Tui. So Lara Conju will present the next summary on climate adaptation. Please, Lara.
So I apologize in advance because this presentation has been done in a hurry. However, here are some highlights. Okay, so we had projects that had a focus on the first one, the analysis of agriculture productivity of crops using machine learning and process-based models to create soil and farm management maps, but also to predict future climatic scenarios. The second project focused on crop seasonality. Assessment of maize calculations were carried out, including variables such as rainfall, sun related to the growing season, to better perform crop yield estimation and identification of optimal planting. The third project dealt with the winter wheat production and migration of cropland to analyze the impact of climate change to better plan and manage production. And then the fourth project focused on rice crops in Senegal, because in Senegal, rice represents a major nutritional crop. And the goals of the project were to increase the crop fields and their intensity while maintaining an effective irrigation network using EO data. Then we had the Viesco project aimed at improving food security in the Mekong Delta. Stressors on rice farming due to climate change and human pressures were analyzed using in situ and satellite data for model-based observations, and the outcomes have been the adaptation of the crop calendar, reduction of cropping density, and conversion to other land use, and the decrease of methane emissions. Recommendations. So here the main recommendations stemming from this session on climate adaptation. There is a need to improve temporal resolution of EO emissions. The analysis of climate change impact on agriculture require high resolution climatic data with large area coverage. Winter and summer crops need separated in geospatial products. There is also the need of continuous integration of EO data and machine learning models in intervention and aid strategy. There is the need of an enhanced integration of EU and regional data and data from agriculture organizations, along with coordinated reporting of yield data. In addition, satellite data should be adapted to tropical regions, not regionals. More investment is needed on ground data and IoT. This is mainstream in many sessions. There is the need of integrated observations of impact of multiple stressors on crops concerning climate change. Analysis is also relevant. Last but not least, it is important in investing in better user uptake of EU applications, services, and products by co-developing solutions in partnership with the relevant local stakeholders, but also involving them in the testing phases. That's all.
Thank you very much, Lara. So the last summary for technical sessions. Do we have Marijn or Linda? Please.
Okay, so they didn't have time to put everything together yet, I think, since I just literally uploaded them. Okay, so I hope people actually remember what they saw pretty recently. But so the first one was on drones, you might remember. So the idea of low-cost drones, and the difference there is a sampling strategy. So it's cheaper, you can do the data collection much faster, you gather much less data, but the big potential there is, or the big promising use case is CalVal for Earth observation data. Second presentation was on Lucas photographs, so in situ data from Lucas photographs. Computer vision was used to do semantic segmentation. That then gets put through a random forest model and produces land cover. And then the Lucas data were used to do a kind of an accuracy assessment of high resolution land cover maps, like produced by Esri, World Cover, their new dynamic, Esri's new dynamic land cover map. And then you can see the accuracies range between 52 and 59%. And then they undertook what was called a semantic gap evaluation. So basically looked at those places where the land cover maps were in error, and then looked at the photographs to provide some context and information. And then we can try to understand maybe why those maps are having problems in identifying those classes. So the promising use there is detecting areas and biomes where commission errors are happening. Okay, and then presentation number 3 was the integration of existing products that have just come out, very high resolution on cropland maps in order to create a better hybrid cropland product. So the first thing that was done was to compare them to find the areas where there are disagreement. And then when there were real hotspots in disagreement, using experts to do corrections based on very high resolution satellite imagery and also other sources of information like street level imagery and then also the grassland map and other things like that. But basically it's a promising approach as it's a really simple way of producing a better product, a hybrid map, and it can be used for lots of other different applications. And then the final talk was about integrating administrative data and content from Wikipedia on crop types using a large language model. So you might have remembered the example of how much time was spent by PhD students in doing this matching of GSA data. So again, GSA data with this HCAT taxonomy. So you've got all these different languages and all these different crop types and trying to harmonize that. An approach was used called retrieved augmented generation with a large language model to train it to see whether it could do this approach. And you might remember some of the results were promising and some of them were a little bit less promising in terms of the translation. But in general, it is a very promising approach in the future for doing this kind of automated matching and translation. Okay, so recommendations. For the drones, complementarity of small drones for high-resolution mapping, also this flexible data acquisition. You might remember you could do it tomorrow, for example, if the strawberries were flowering. You can exploit the benefits of drone sampling, explore drone products for validation of existing EO products, support new EO satellite missions, but that there is a risk of fragmentation because there's all these different drone products and infrastructure, and so we need sharing platforms. Okay, in relation to the in-situ photographs and remote sensing, it's to maintain the temporal stability of in-situ products like Lucas. We've also heard the same comment for maintenance of temporal stability for the Sentinel satellites. Street View as a source of information for land cover mapping has incredible potential that hasn't yet been exploited. Other recommendations in relation to the hybrid cropland mapping, most of this is to just do with the in-situ data. So gaining a better understanding of the influence of the quality on the final classification. So for example, should you invest more in getting high quality in-situ data, or should you invest more in your deep learning algorithm and the processing? So more needs to be understood. Data integration can best be done if we have fair and free data, ideally cloud optimized, etc. Some of that was already mentioned. Again, this idea that you really need high quality ground data and it's insufficient at the moment. And we need more research on optimizing the training and validation data collection because it's expensive. So can you reduce the cost while still maintaining a minimum level of statistical robustness for validation, for example? And then the last one is really not necessarily for a European Space Agency, but an operational service for crop type mapping of major global crops is needed. Okay, then for the third presentation, some recommendations were provide better access to administrative data. We just heard that recommendation, in particular GSA data. Provide more computing resources, provide more funding. Other recommendations in general from the discussion were to standardize data, such as the GSA, ask member states to publish them according to this international standard, like the International Species Register, or automate this process. We had this discussion about that we require this data from farmers, but it's not mandatory for member states to provide these data in a harmonized way. Why? What can be done to improve this? And then finally, that funders should put much less stress on the need to reach a minimum level of accuracy and instead should stress common terminologies so that the products are comparable, even if this means that some of the individual classes might have lower commission or omission errors. Okay, that's everything. Thanks.
Thank you very much. Okay, so that was the last summary. So now we are about to close. If I can invite the whole organizing committee to come up here. Sorry. No, we skip the panels. The panels will be included in the report. So. And we would not have time for it. I don't know if there are place for everybody. At least I will go over to leave my chair. Please, Sabrina is missing. Lorenzo is it? I had to leave in the end. Okay. Sabrina, Magda, and Evelina. So I will just, if you can set up the closing presentation. Oh, it follows it's directly the same. Okay.
Yes, we didn't have time for that.
Okay. So this is the workshop almost closing session. And the reason why it's only the almost closing session is that we will have another session starting at 5 until 6:30 with lightning talks from ESA projects and EC projects, Horizon Europe, that were most of them that were not presenting during the conference. So it's an opportunity to also see some of these projects that were not presented earlier. And we also use it as a kind of kickstart for the meeting that we will have tomorrow, that we launch the ESA Agriculture Science Cluster, which is a mechanism that we have to enable different ESA projects to work together and to work together with the Commission projects. Then the next step will be that we will draft a workshop report based on these summaries, and we will send it out to co-chairs, hopefully within a week or so, so that co-chairs can review it, and we get back comments, and then we can publish the workshop report in June. And after that, next step is that on the ESA side, we will be able to take that into account for defining the work program for 2025. If we have any money left for 2025, because that's the last year of our cycle before we ask for a new budget. And then I hope that we will meet again in 1 year's time, 23rd to 27 June. We will organize the ESA Living Planet Symposium. And as we have done in the last symposiums, in several of them, we will for sure have a number of sessions dedicated to agriculture. So I hope that we will meet again then. So with that, I will go the other way. I would just like to do some thanks. So thanks to the partners of this workshop. So to the European Commission, to FAO, to World Food Programme, and to GEOGLAM. Big thank to the organizing committee. I will not name them all. I'll give a special thanks to Sabrina, who's been working day and night and the weekends in supporting this. But of course to the whole team, our host team, to Evelina and to Magdalena, of course, from ESA side. All the organizing committee has been very active and helpful in organizing, so thanks a lot. Thanks to the scientific committee that helped in reviewing all the abstract and selecting those in that way, a very nice program that we had for this workshop. And also many other people from the scientific committee have been chairing the sessions. So thanks a lot for that also, for chairing and for providing the summaries. Thanks a lot also to the conference bureau, has been enabling that this workshop has been running themselves also. Seen Julia and I don't remember your name, have been running fast around with the microphones to help us. Thanks a lot to the technical experts in the background who has been helping with the audio and the video. It has been running very smoothly. Thanks to the guards who have been providing security for us. And to all those that I have forgotten. And last but not least, thanks to all of your participants, and a special thanks to those who are still hanging in here on the Thursday afternoon at the end of these 3.5 days. So with that, I would just say thanks a lot, and I will give the word to the two remaining partners of the organization, to the European Commission and to GEOGLAM, please.
I think we are all exhausted, so it won't take long. But just I want to thank especially all the organizer, and I think we are exhausted, but we are at the same time reloaded, because when it's exciting, when you go to a scientific conference, you meet other people, you expose, you work, and that's really the magic of a conference. And I think that was really exciting to see all the nice science that has been done. And yes, I think the Commission is really, I mean, on the behalf of the Commission, you've seen that the colleagues remotely and also in the room, they were really active, because we really want to support this. We really believe that science for policy is very important. It's not just some wording. So thank you, especially also for all the scientists who have presented and the nice work. And yeah, we hope that there will be a lot of success in all these projects in the future. Thank you.
Okay, I don't think I need to add much. I think we're all dead after an intensive week. We started on Monday afternoon. I don't know, well, you saw today how many sessions we had. It was an overload of information, which was great, because I think that was the setup of the conference as well, to get information and to discuss. From a geo perspective, this was a very successful meeting. I think some of the recommendations, we talked a lot about EAVs, the in situ data was put very clearly that there's a clear need for that. Despite the overload of information, I think everything ran very smoothly during the conference. So I was going to say the people in the back, but they're in the front here. Also special thanks for actually getting the highlights of the days and of the different sessions directly on the website. So I think that's in fact very impressive, I must say. So if you saw them tockling there, they weren't doing their emails, they were actually listening and writing. So that's cool. Also, recommendations and the session shares, they also did a big job to get the slides up today after the coordination of the session, and then the talking and the discussion and the networking, they still had to work. So that's also a big round of applause to them, please. It feels a bit strange to close a workshop while we have a coffee break and still a session. So, but anyway. Okay. Is there something special during the coffee break? Salty coffee, yeah. It's a new Roman tradition, salty coffee. Very interesting. In fact, in the cafeteria, they don't have it, so it's very exclusive there in the marquee. Very good. Anyway, I'm in between coffee breaks, so I want to thank you all very much for sticking around. 5 days, very intensive. Some of us left, but I think most of us, well, I guess most of us will go home with a very good feeling. It was very interesting. The networking was excellent. So thank you all, and we'll stay in touch, definitely, on the whole next steps. Looking forward to meeting you all again in next conferences, workshops, online and in person. Thank you very much.
Okay, so please, coffee is waiting, and please be back at 17:00. Yes, you can speak for it, yes. Yes, I think we should start the lightning talk session now. So this is a session where we will see short presentations of a number of EC and ESA projects. They were not all presented earlier here. So I will just ask the presenters to be on time. I think we have said 3 minutes for each, and then because there is always a little bit of time between when switching. And also, I think you know the order, so that you can be ready when you see that the preceding presentation is finishing, so we can switch quickly. So with that, I will just open the session and have the first speaker from the Cerberus project, please.
Good afternoon. Good afternoon. How can I put the slides? The slide will come up.
Sorry, if you can have the lightning talks presentation now, please. Thanks.
Sorry about that. Okay, good. So, good afternoon, everyone. I'm going to present very briefly the project Cerberus. It's a project on crop health and pest control. And we are very focused. We are just looking at 3 crops only: grapes, olives, and oranges. That's the most important Mediterranean crops. And 6 pests: 3 quarantine pests, 3 regular pests. Why do we need Earth observation? Because we are going for early detection and large scale. We also have large scale from citizen science, but we very much will get all our large scale analysis from satellite images. So our project is a multi-platform project where we have the Copernicus and other local platforms, digital communication between to get all the data and then all the citizenship. For us, the most important thing is to disentangle the images that we will be getting from the space. So, in order to do this, we have a strong ground level sensing. We will have robots, have traps, 2 kinds of traps: conventional traps, electronic traps, and then we'll have a sprayer to close the cycle and fix the problem. So, this project started in January, so it's very, in these 4 months, we are already setting all the ground traps, first in Italy and Cyprus with grapes, because Lobesia botrana is very active right now. This month we have been setting some of the traps in Spain, and then the ones in the olives will be set up in the next 2 weeks. So part of the program was to involve stakeholders, and so we had a group dynamic and involve several kinds of stakeholders to ask about satellite images, because it's one of the key topics in our project. So we asked about parameters, usefulness, information layers, area coverage, and other features. So this was a multi-table event where we had people from research, cooperatives, small farmers, big farmers, and some of the results, which are the challenges we will be facing, is that many of their solutions are very limited for fruit pests. So it's very difficult to find the problems that are on the fruits, because from the top, most of the fruits are inside or below the canopies. Many users found it too complex, so we'll have to do a big job trying to add training and make things much smoother than they are today. And some of the solutions are crop dependent, so it's a big challenge for us. We only have 3, but we want to extend our solution to other crops. And this will probably be some of the challenges. So we are working in both large scale, local scale. Both of them will be using Earth observation satellites at different scales, of course. And this is what we have done pretty much in these 5 months that we are in the air with the project. So thank you very much. And of course, I will be here today, tomorrow. And any collaboration, please let me know. Thank you.
Okay, so can we have the next slide with, so then we will see the next presenter. Okay. Okay. Yes, so I would invite Scale Ag Data.
Okay. So thank you very much. So I'm here now to present. Test. Okay. Okay. So Scale Like Data project, we're Horizon Europe. So as you can see in the title, the whole idea of Scale Like Data was to see, if you look in agriculture nowadays, more and more sensors are being used and deployed in the field that are measuring different things continuously. And the question that the Commission had is, what if we can unlock this whole new source of information that's available, that's lying around, but that's not accessible? What if we can make it accessible, and how, once it is accessible, can we use it to improve the European monitoring capacities for the agro-environmental conditions? So it's a bit two-sided. On the one hand, all this data is there from sensors, how to access it. Secondly, if it is accessible, how can we improve the European monitoring capacities? So we started a year and a half ago, quite a big project with 26 partners. The whole range, so from EO service providers, technology providers for farmers, advisory services, also from insurances. So it's very broad because we need the whole ecosystem to be present, given the complexity of the system. I only have one slide on the project itself, but it's quite a full one. So here it's the logic of the project, also looking at the different activities that we have. So we work through research labs or pilots, which are deploying sensors in the field, and we are working with them to see then how we can make them accessible. So we start with them once you have sensors. Usually it's already existing ones. Take, for example, the harvester data, if you're looking at yield measurements. It can also be soil moisture sensors, it can be weather stations. Also on diseases and pesticides, there are also sensors available. So they're all deployed in the field. So then we will look at, okay, which innovations, okay, that's not working. Which innovations do we have on the sensor technology, but also how they can be used is one very big component of the project. How can we make it accessible, data standards, API, communication protocols, and also data quality and harmonization of that data, because different sensors measure sometimes the same variable, but in a different way. So how can you make them interoperable as well? So that's really on the sensor data itself, a big component. Then the next one is, let's say it's all available. The quality is good, it's standardized. What can we then do from the monitoring component? You can look, for example, at training new products. For example, if you have a whole archive of soil moisture data, you can recalibrate the soil moisture products. But we also have the advantage that these data become available in near real time. So you can also look at ways to include these data flows into adjusting existing products. So you have soil moisture products available through Copernicus, and we have the sensor data coming in real time as well. So how can you then correct these data based on the sensor data coming in? Same with harvester data, for example. You do yield estimations, but you have then in real time new data coming in as well. Let's say that all works. You have these workflows ready as well. So all of a sudden we have much better EO products available all over Europe. Then we get actually to the right-hand side of the figure, and that's what can we do with these data. On the one hand, we want to know what's the benefit for the farmer with all these data. So both the sensor data as the better satellite products, what is the benefit for them? Because in the end, they have to decide to open up this data, yes or no. So what's the feedback? What's the benefit from them? So there's a whole component on how to use these data. On the other side, if we have these data, that's going to the bottom of the figure, how can it be used for other means than the farmers themselves? So talk about insurances, talk about CAP, talk about the Commission itself with all their environmental monitoring that they are doing, the financial sector, and so on and so on. So it's not only of the farmers, but it's also other players in the field. So that's, I think, in a nutshell, scale egg data. Thank you.
So, good afternoon. My name is Theodor Zachariadis. I am technical CTO of Synelix Solutions. Well, the project that I'm going to present is AgriData Value, and it is a sister project to the previous one. It was accepted at the same call. Synelix is a company that provides solutions for farmers, and among others has a product line which is called Synfield. We have more than 300 installations in 15 countries in Europe, Asia, and Africa. AgriData Value is a large project with 30 partners, large industrial partners, SMEs, research institutes, and also 3 CAP-paying agencies, and we have involved 14 countries throughout Europe. What is important, and I would like to stay in this presentation, is the following. Within AgriData Value, we have tried to face a number of projects. We have seen a number of problems. We have seen these problems in different presentations that we have these days. And AgriData Value is providing technological solutions for many of them. So first of all, we have seen that in situ data are very important, but they are not sufficient. So within AgriData Value, we are going to install more than 200 new sensors. Actually, many of them have already been installed, and we are going to also have more than 4,000 RFIDs for use cases that are using traceability. The second one, and it has been also discussed these days, is that in many cases data owners and in situ data owners are not willing to share their data. And this is a very important issue, and we need to give incentives to these data owners in order to share this data. This is the only way to go. So what we do in AgriData Value is that we utilize NFTs, blockchain, and smart contracts in order to give these incentives and micropayments to the ones that have the data in order to share them. The third one is that, as we have seen, in situ data are and will continue to be in silos. And this is something that happens for various reasons. For scalability, for business issues, because they are different heterogeneous data that exist there. So within AgriData Value, what we do is 2 things. On one hand, we are implementing adapters in order to have interoperability standards with IDSA and Gaia-X. So we have International Data Space Association as one of the partners in the consortium. And on the other hand, we are adopting federated deep machine learning. So we have models that can be federated and trained at the different silos of data, and then we aggregate in order to create the new machine learning model at the source that has initiated this machine learning. So in this way, we can utilize data without necessarily transferring them to a central repository. The third one is that we have seen that in situ processing, power is not sufficient. So what we do is we adopt edge computing resources in order to do whatever machine learning processing we need. And what we have seen also from our experience is that there is still a quite lack of trust in AI from farmers. So what we have adopted and we are implementing is that we apply explainable AI techniques in order to provide justification of the machine learning and how this is implemented. So what we have implemented already is an aggregate value architecture that can be federated. This is just an instance of this architecture, and you may imagine that this is instantiated at different locations from different organizations for different companies at the end, and has all the different components. And also what we do in order to validate in the project is that we have 23 pilots with 7 use case clusters that go from arable crops, vegetables, multi-annual crops, livestock, cross-sector use cases, cap realization, and also climate monitoring. So I will be happy to discuss all this later. Thank you.
I thought originally that I was number 5 on the list, but anyway, I'm excited that I'm not disqualified like in the Eurovision Song Contest. Tembo Africa. This is a project that is about open and freely available in situ data, but to do that, we have to generate sufficient revenue. As was said earlier, this is really a complicated issue. How are we planning to do that? It is by developing sensors, by delivering product and delivering services. So we have a number of sensors on the atmosphere, commercial microwave links for rainfall, X-band radar in a cheaper version where we can be more locally present, intervalometers for rainfall detections. We have land surveys. We work with the boron solution for soil moisture that we're experimenting with, and with low-cost GNSS receivers. And then we have, for open water, we have river-based dischargement, and I changed this in an earlier version, but I see it dropped out again. But what is there is UAVs and fish finders and also GNSS to do better water management. Our products are related to that: rainfall maps, soil moisture maps, open water measurements, river discharge, floodplain mapping, and bathymetry. And what you see, the little elephant on top, Tembo means elephant in Swahili. And we made it a Lego elephant to show that we are making building blocks which we can assemble in different ways. That is one of the guiding principles of the project. Then the services. Germination insurance was already discussed here several times. We have flood early warning systems at the moment, especially in Kenya and other places. Flooding is a big problem, including one of the areas where we have our first pilots. So we're happy to show that at least the early warning works. And the other is reservoir management for hydropower dam reservoirs in Africa. There we have pilots with the Bui Dam in Ghana and the Lusemfwa Dam in Zambia. The advantage there is that because these dams are really important for the energy provision of the country concerned, there is also more funding available. So we hope that we can have them as paying client. And one of the big problems also related to agriculture there is that when the rainy seasons come and when you do not have a good prediction of what your outflow of the reservoir will be, then they are surprised and suddenly they have to release everything in one go, and you have a lot of flooding downstream, which apart from a disaster also causes a loss of production in agriculture. So that is very short, the summary of the project. Thank you very much.
Good evening. My name is Mikhail Safiev. I'm from Finnish Meteorological Institute, coordinator of SILVA project, which was originally called a System for Real-Time Observations of Aeroallergens. It's still called like this, but since then we moved a little bit forward, so we're now looking not only at aeroallergens, but also other bioaerosols, different types of those. But jokes apart, those species which we are after, pollen was the main motivation, and that's historically the main bioaerosol considered. But comparatively recently, we got a chance to look into spores. Now thinking about bacteria, we'll see if we go further beyond that. What is color here says that, shows the attention. Most attention will be put to pollen and various impacts of that one. Allergy is the first, of course, but also gene transformations, climate change, and things like that, interaction between environment and human society on pollen side. But spores are more relevant in current context, and that's what we are trying to do. Next, yes. SILVA is a workshop. It is a project which develops the technologies. We do not that much build of services. That is rather an outreach of the project. The main goal which we have is to make absolutely new instruments which were not existing, not even prototyping 10 years ago, whose first prototypes appeared 5 years ago, and still we have single-digit serial numbers in several of these instruments. And these are the main one is, of course, at the bottom is the flow cytometers, the in situ devices which in real time can tell us what bioaerosol is in the atmosphere, and not only say that it's present, it can say what bioaerosol it is. It can recognize, with help of machine learning, of course, it can recognize type of pollen, it can recognize type of spores. We are hoping to train it to some bacteria as well. Apparently, it's possible to train some LiDARs to recognize some bioaerosols. Didn't know about that just 5 years ago, but apparently now there is a working algorithm which gives us something like 3 families of pollens. And of course, DNA, recent breakthrough on 3rd generation of sequencing gave us an instrument to look into metagenomics of the atmosphere, and the models come to the game as well. Right now, SILVA is in the 2nd year, and that's the 1st year of our pilot demonstrations. There are 3 of them. By the rule of the call, we were supposed to give the devices hard life. That's exactly what we are trying to do. The devices are sent into Arctic, they are sent into 3 kilometers in Alps, and they are sent into semi-desert, desert area in Spain. Just one example is comparatively mild situation, a pollenocytometer at the roof of Finnish Med Institute in Helsinki. And I put it here also together with the model which shows that the peak of birch flowering is something like 2 weeks later this season, and several other species, you see this different colors of the lines, they are synchronized by the weather. Actually, pretty unusual. They should flower in different moments. Thank you.
Hello, everybody. My name is Valantis Tsiakos. I am from the Institute from the iScience group of the Institute of Communication and Computer Systems.
and I'm going to present briefly Eiffel project. So Eiffel aims to exploit the vast amount of data that are available in the GEOS portal and facilitate the development of novel climate change adaptation and mitigation applications, and demonstrating these capabilities in the context of pilot applications. The main problem that the project tried to address was to facilitate the uptake of this data in the context of the stakeholders and the user community, try to design novel tools that facilitate this process, including AI-based cognitive search tools and so on, and also foster the design and co-design of climate change adaptation and mitigation applications. Here it is an overview of the concept of the project. So the project is towards its end this month. So essentially, the three main parts, as you can see in the figure, we have the Eiffel data exploration tools, all these innovations that facilitate the exploitation of the data, the augmentation of the metadata that are available, and their enrichment in order to be able to be utilized in the context of data-driven applications. We have some augmentation tools that aim to address challenges associated with coarse resolution of the data. So in this context, we try to improve both temporal and spatial resolution by harnessing heterogeneous data sources. And all these are demonstrated in pilots that cover food security and agriculture, transportation, sustainable urban development, disaster resilience, and water and land use management. As I said, the project is in its final month. Currently, we are finalizing the validation phase, working closely with the end users, and trying to communicate our achievements. So just to stay on one or two items that I think that are relevant also in the presentations that we see during the workshop. One of the novelty that introduced by the project as an horizontal part, it is the augmentation of the EO data, the ability to harness EO data along with in situ data. For instance, one of the applications was the super resolution of all Sentinel-2 bands at 10 meters spatial resolution, and also the super resolution of Sentinel-5P, where at this part neural network architectures were employed, and we used also in situ measurements that were collected from the EA air quality e-reporting data repositories. Another approach, another application that it is related to the agriculture pilot of the project involves the computation of soil organic carbon stock at national scale. So essentially here the project adopted a hybrid approach. I mean, physical process-based model was employed, including also data-driven of enhanced resolution indicators of soil, like soil organic carbon and clay. And this hybrid approach allows us to assess stock of soil organic carbon at national scale and provide improved results. And further to that, we also want another relevant case. It is the assessment of different nature-based solutions on soil organic carbon. So the idea here it is to apply, we have applied an explainable AI-based solution that is able to quantify the impact of different practices on the soil, and also being able to assess, the applicability of the soils, for instance, for organic carbon, and so on. Thank you. And I'm staying here because I think I have also, another presentation. Okay, this one is about Theros project. So Theros aims to apply a scalable and integrated toolbox in order to address cases of adulteration in the quality labeled food products. We are examining both organic and geographical indications. And at the same time, we aim to ensure increased traceability, trust, and security. So the project, it is nearly in the halfway there. Here also you can see the overall concept. We have different technologies in order to be able to assess adulterations, relying on Earth observation, on photonic systems, on IoT networks, on DNA authenticity kits, that all these are being harmonized and assessed through a dedicated component, and also are being associated along the food supply chain. Based on this information, we'll be able to assess and verify the status of the organic product and detect any adulterations taking place. Some of the items that are worth mentioning also here and relating to the workshop, it involves the use of photonic systems in order to discriminate and detect, most probably, incompatible practices to organic farming. We covered not only the soil, I mean substances in the soil, but also substances in the actual food product. I mean, this is an example from Greece where you are using oranges. And also, apart from this targeted approach, we employ all sorts of observation data in order to be able to distinguish and discriminate between organic and conventional agriculture practices. Here, we've worked with neural networks, architectures, currently utilizing Sentinel-2 in order to do this distinguishment in the practices. But also some other items that we are currently examining. It is the application also of super resolution methodology, because as discussed in the workshop these days, we have cases also in organic farming with small farms, that it is something that it needs to be addressed. And also other approaches that involve rules based on other markers that are being computed and associate different information regarding the phenological states of the organic crops. And last but not least, we also check here the carbon footprint of the production in order to see if indeed and assess if the organic agriculture practices act as carbon sink and rather than producer of greenhouse gases. Thank you.
As you see, you cannot get rid of me. I keep popping up, and I'm even going to do 2 presentations now, so but it will be very quick. And these 2 projects are more industry-oriented projects, and they're managed by the Horizon water, increasing water scarcity, etc. So there are all kinds of problems where we think that with Earth observation we can do something. And what was discussed this morning as well, what we try to do is to integrate in situ information with Sentinel-1 and Sentinel-2, and then try to come up with a solution that helps the sugarcane value chain. And in parallel, that we can have an improvement in the situation for the environment, and that we help with adaptation to the effects of climate change. So we will start with the area around Cali in Colombia, in close cooperation with, from farmers to the mills, to the associations, and the technical people involved to improve the situation. So thank you very much for that one. And now I go to the next one. And this one almost ended. It was presented here also in the session on smallholder farmers, so I will go very quickly. It is called WaterSense. It's a cooperation between European companies and Australian companies and the university. And this is on improvement of water management. And so it is both water accounting, more efficient use of water, and the successes are in better estimating how much water is used, where it is used, etc. So it's two things. One issue that was already discussed is to detect water theft, but the other is also prepare for climate change, that you have a more efficient use of resources and that the responsible government departments know what is playing and how they can anticipate on that. And the good news there is that one of the government services departments is already a paying client. And because we had the opportunity to develop these services where you have to take into account, like in Australia, farmers have a specific way of irrigation. First they pump the reservoir and then they irrigate, which for establishing the water use was a hurdle we had to take. But with what we have now, we are ready to export it to other countries as well. So thank you very much.
Hello, my name is Manos Lekaikis. I'm an agricultural engineer and I work at AgroApps. AgroApps is the coordinating partner of, this doesn't change. Next. Okay, thank you. The coordinating partner of AfriForecast project. The other partners in the AfriForecast project, which started on January 2023, are GMV with headquarters in Spain and the University of Sapienza. So we wanted to address food security and food safety in Africa. To do that, we needed in-situ data, so we collaborated with two African entities in Kenya and Uganda. We wanted, in the case of food security, we wanted to provide a framework for the African entities that will be easy to use, and of course to use it for the future in order to find any probable yield gaps. So we collaborated with the University of Nairobi. As you can see here, a lot of data were collected, in-situ data, and of course from Uganda with the environmental surveys, SIPs. In the case of food security, you may say that we are old-fashioned, but we are not, because we wanted to provide a framework that will minimize the field campaigns. So we have done previous work on using publicly available databases, like, for example, the soil grids, soil data, and the ERA 5 land and reanalysis data from the Copernicus Climate Data Store. So we made a framework, a fully automated framework, which actually runs on the aquacrop model, the newer version, the 2022 version of aquacrop model, which is the model that can run for a single parcel or for multiple parcels, so therefore it could run at the regional level. We used satellite data to calibrate the phenology of the model, so keeping in mind that we have different growth patterns for these three crops, for rice, maize, and wheat. We provided ready-to-use databases for the crop, because one major part of aquacrop model is the crop input. And then, of course, we also used the pro-sale model to feed the model with, to feed aquacrop model with canopy cover measurements. On the other side, we had the food safety part. The food safety part involved rust disease, detection of rust disease with earth observation data, and aflatoxin with agrometeorological models. We collected, data were collected for both of these two services. from Kenya and Uganda. And then, of course, after defining the services, we determined the data that were missing from the two targeted, let's say, new missions of the European Space Agency, which is the PRISMA and the EcoStress. So we did the spatial enhancement of hyperspectral imagery in order to have a better resolution, to fit the model with the canopy cover measurements, because canopy cover is very important for the crop growth model. And of course, we did a framework for the spatio-temporal enhancement of the EcoStress by using MODIS and calibrating and validating this with Sentinel-3 data. Thank you.
Hello. I will be presenting again a project related to EO Africa Explorers, and more specifically the water resource management. Okay. The consortium is consisted of two companies from the Planetech group that has been around and involved in the space industry from 1994, and an intergovernmental organization specializing in the Mediterranean basin that has mission to promote the cooperation in fields like the agriculture. And also it involves local stakeholders and institutions from Egypt. So the project is related to Egypt, but can be applied also to the whole Northern African countries, because the situation is quite similar in Morocco and Algeria and Libya. So the objective is to develop and validate techniques to estimate the crop water stress and evapotranspiration using all the sensors that we've been discussing for the past day. So PRISMA, ENMAP, EcoStress, and of course Sentinel and Landsat data. And also creating an open source model to estimate the actual crop evapotranspiration. So we've been dealing with this situation and getting data for two different crop cycles in this pivotal area crops in Egypt, in a cultivated area of around 14,000 hectares, using in situ data as well. And our methodology is briefly mentioned here. So we have a model composed of Earth observation-based evapotranspiration, ground-based evapotranspiration that serves for the validation of the Earth observation evapotranspiration, and it would be an input for the real-time crop developing monitoring. And very briefly, this model allows the estimation and mapping of the actual evapotranspiration through the KC and the crop water stress index. So some of the results can be found here. So we've been calculating several indices, some of which you can see here, but also we have been comparing the in situ data with the EO data in order to find some irregularities, like the one you can see in the right-hand side, where we have an in situ problematic measurement due to highly irrigated fields. And the last thing that we have been dealing with is the creation of a platform in order for the user to be able to access and use the data in his own will and time. Thank you.
Good afternoon, everybody. First of all, thanks to be here. I know that it's a late session, but there's still people in the audience, and I know also online. So I'm Mirko Boschetti from CNR. I'm presenting another EO Africa Explorer. This project is led by the University of Twente from Michael Marshall. If who of you was yesterday here, he was presenting the results. Yeah, I'm just presenting the project. So the idea, we already know, is the problem of water scarcity and drought in Africa. Traditionally, we can use statistical indices based on meteorological data like the SPI. But of course, thanks to the new polar orbit satellite, we have more and more potentiality in deriving information from vegetation health. And one of the indicators that is not used so often, but it's become more and more popular, is the estimation of evapotranspiration, like the colleague showed before. So the project wanted to compare two ways of estimating evapotranspiration from the PT Priestley-Taylor JPL model and the TSEB model, exploiting, as you can see from the call, but also from the title, eco-stress data and hyperspectral data. Previous study demonstrated when we include hyperspectral data in the model, we can better describe the soil moisture transpiration and the canopy transpiration. So the scope, and Michael demonstrated yesterday, that when we ingest hyperspectral data in the model, the results of the estimation are much more better. The overall idea is to, the long term is to, of course, to provide farmers in pastoral area of Africa with the geospatial information, with enhanced geospatial spatial split information. And of course, those study has the long-term perspective to open the path for the future CHIME and LSCTM mission that will be the necessary input data for operational monitoring and production of indicator of drought based on evapotranspiration. Thank you.
Monitoring project. Slide, please.
Do we have the online presenter?
Yeah, I am here, Aspen.
Perfect. So just tell me next slide when you want to proceed.
Perfect. Next slide. So basically, CRISP, that stands for Consistent Rice Information for Sustainable Policy, is a funded project that aims to address indicator SDG 2.4.1. And it is in collaboration with an heterogeneous group of early adopters, and will contribute to achieve the target set for 2030. The project involves a user co-creation and a user uptake phase to finalize objectives, and they engage also stakeholders among the community. The system is based basically on the 10 years, or more than 10 years, RISE project that SARMAP has carried on during the last 10 years in Southeast Asia. Next slide, please. The focus of this project is quite clear. There are three pillars: where and when, how, and how much. Regarding where and when, we wish to assess the spatial and temporal distribution of rice cultivation. How is regards how monitor rice growth through the season, of course, highlighting cause-effect connection, especially during adverse natural events. And how much regards the yield, and the project will to estimate seasonal rice yield and production, of course, at harvest. Next slide, please. CRISP wish to select among different algorithms which are the best for different occasions, for different events, but it's not only selecting these algorithms. The following step is to integrate everything into a cloud computer infrastructure in order to optimize also scalable processing. This infrastructure is for us Insula, and Insula is provided by CGI, provided and developed by CGI, is the front end of CRISP. And basically, it's an EO platform as a service that aims to empower organization and individual to harness the full potential of the Earth observation data. And its capabilities also stays into the auto-scaling feature that try to optimize large-scale processing in terms of efficiency and also cost effectiveness. Next slide. Where we are, just CRISP started last July of 2023. So basically now we are reaching the middle point of our journey, and we are carrying on some test site. Next slide, please. Sorry, Aspen, next slide. So we are during the phase of testing our algorithms in several places, and we have selected 5 test cases in India, in Asia, so taking on cases in India and in Philippines, and in Africa with other 3 cases in Kenya, Senegal, and Nigeria. So here I can show you briefly the first results in Luzon, in Philippines, that represents the drought showcase. And here you can basically see the difference between one reference year, where we can show the yield in a regular season, and in another condition in which the season was affected by a severe drought. Next slide. And those are also the results in terms of a graphical interpretation in which you can clearly see a reduction of the hectares in the cultivation in the cultivated area, and also a production loss of several tons comparing to the regular season. So that is the next slide. I think I finished. Yeah, perfect. Thanks a lot.
Normally, you should have a déjà vu if you see this slide. I shamelessly reused the slides from the presentation earlier this week, so I hope I can be brief. The ESA World Serial Project, originally 3 years, extended by 3 more years, so running until the end of 2026. We produced the first global maps of maize and cereals. There's also a global cropland map. We heard quite a lot of that already, so find the products wherever you want. The reference data repository is a very important thing where we're hosting already 75 million harmonized samples. We hope to get more and more. There will also be soon an API access where you can get all this harmonized reference data. And we are looking for a way to sustain this also beyond project lifetime. We hope to discuss this tomorrow with the rest of the community. We have an updated classification approach coming up, where we are working with self-supervised learning in collaboration with NASA Harvest to use the Presto encoder to leverage large pre-training of transformers and then have a lightweight supervised approach using a cat boost algorithm that produces crop type maps. And we are refactoring the entire system to be as lightweight as possible, running by default entirely in the cloud on the Copernicus data space ecosystem leveraged by OpenEO. So the idea is that you as a user can run your own, generate your own World Serial Project products, either using default models or in a later stage by retraining your own models. And everything is taken away from you of like downloading data, pre-processing data, computing features, doing model inference. Everything is taken away from you so that you can just normally press the button. And I think that normally is already it. Oh yeah, it's going to be onboarded in the ESA network of resources so that hopefully you can apply for some free funding to create your products. That's it.
So good afternoon, everyone. My name is Tian Hu from Luxembourg Institute of Science and Technology. So basically, our project is about eco-stress. So the target of this eco-stress project is to generate a high spatial and high temporal resolution, density of temperature of transpiration, and also couple the ET with GPP on the same modeling framework, because we know that the mean thermal infrared observation is very important for agricultural ecosystem functioning, researches, and applications due to its, a link to the density of temperature and water stress. So currently we're in the phase 2, in the phase 1, conclude in 2022. From 2020, it lasts from 2020 to 2022. So in this phase 1 of EEH, we targeted at comparing different LST retrieval algorithms and AT models using eco-stress observations and homogeneous ancillary data. So it's more like scientific exploration and model comparison to support the second phase. So for LST, we choose this kind of algorithms. For ET, we choose our own stick model and also compare with the T7 and SEPS model. And currently, we are in the second phase of EEH, which started last year, and it will be end by the end of January 2026. So for the second phase, it built on the first phase of EEH. So in this phase, we're going to go further. We're going to, for sure, through the scientific exploration of first phase, we now know what data and what model we're going to implement it. So we're going to use the TS algorithm, and also we're going to use our own stick model for LST and ET estimation. And also we're going to go one step further to couple the ET with GBP on the same modeling framework, and also because the daily ET would be more interesting for the agricultural community and the other stakeholders. So we're going to also develop the daily ET estimation algorithm. So in total, these kind of 2 phases will support the future high-resolution thermal missions from different space agencies across the, over the globe, including Trishna and the SPG World LSTM. And for all this data, they are available on the WASDI, which is a Luxembourg company. They support this kind of geo information data storage and also processing and also visualization. The data can be accessible through a link. And these are some some results. For LST, impact on ET, and also some results for our own developed LST retrieval algorithm. And this is the result for the ET evaluation results. So this is the daily ET upscaling method. So actually it's quite interesting because, for the other, a lot of applications, they need this kind of upscaling method. So this method is pretty simple and also, with very high, with compatible accuracy with the other more complicated models. So I think that's all, and I look forward to discussion with you guys tomorrow. Thank you.
So hello as well from my side. If I counted correctly, 3 more projects until your well-deserved after-work drink. So the briefest summary I can give about the project called GEOGLAM is the title itself, so yield prediction and estimation based on Earth observation. A few more sentences based on this. This is the overview of our project or what we intend to do. So we collected quite a lot of in situ data for crop yields and used and established a database with all the crop yield data and the Earth observation data like Sentinel-1 and Sentinel-2 data. And now we establish crop yield forecasts on a field scale and on a regional scale, and we want to test them in a variety of different science and demonstration cases. So we'll now focus on how well these forecasts can be used, for example, for irrigation or irrigation advisory tools or fertilization advisory tools. So just to explore a bit what we can do finally with the results. Here, just a brief overview again. I already showed this slide yesterday from where we all collected the data. So for the circles, you can see we have some field scale data. And for the countries in Central Europe and France, we have some regional scale crop yield data. Yeah, this just very briefly, these are some first results we have, but these as well, I've presented them yesterday. So I will not go into much detail, but just to show again that we did crop yield forecasts on a field level on the left-hand side, and on the right-hand side, the crop yield forecast on a regional scale. Yeah, and that's already it from my side, so I will hand over to EO for Nutri.
This is the last two. So again, me, Mirko Boschetti again a project led by University of Twente, by Mariana Belgiu. This is a very high-risk, high-gain topic because we try to see how far we can go with remote sensing in estimating and predicting crop nutrients. Means the characteristic of grains, not only the yield like we see before, but also the characteristic in terms of macro and micronutrient. That is an issue for what is called hidden hunger. So we have two scientific cases. One is to advance the understanding of life cycle of nutrient from soil to crop canopy, and the other is to deepen understanding of nitrogen uptake, again from soil to the canopy. So the second is much more related to what we saw also in other presentation, because it can be related also and useful for the nitrogen fertilization, but in this case is for the quality of the grain in terms of protein content. So how we perform that? Because it cannot be simulated, do not exist, so we have to acquire hyperspectral data together with the ground information relating to our crops. 3 crops we're monitoring: maize, rice, and wheat. We do that in different phenological conditions, in vegetation, in reproductive, and in maturity stage. In these stages, we acquire canopy characteristics, plant samples, and of course at the end, before of the harvesting, we also have grains from which we send to the laboratory and we obtain information about the micro and macronutrients. So what we obtained up to now, or which are the ongoing activity, we did a kick-off meeting in September, and it's allow her to set up a position paper on the topic. And the two main approaches we are actually using is an hybrid one that exploit some radial transfer information to assess nitrogen content in the plants, nitrogen uptake, while for micronutrients we have to base everything on artificial intelligence machine learning. So we will use the samples from the field and the ground measurement of hyperspectral data to retrieve a model with machine learning, and then we will use Prisma data to spatialize that and apply to produce map of that. Okay, thank you.
Hello everyone. What a surprise. You had me first in the morning. You're gonna hear me last in the evening. It's my day today. So I just used my previous slide. So our project is the EO for Cereal Stress Project, which is funded by ESA. We are like around 7 months into the project. And basically the project, as I said earlier, is to try to develop methods of estimating stress, both individual stress and multiple stress where possible, and provide some stress monitoring products, and also generate some roadmap that can be used to invest in future stress monitoring programs. And as I said earlier, this is basically what our approach is. So we'll collect a lot of field data. Already we've collected a lot of field data, which are currently being processed following a number of methods shown there, using machine learning, using radiative transfer modeling, and also using empirical regression methods. And we hope out of those analyses, we're going to generate some new algorithms that we can use to detect stress. And then we can apply those algorithms to generate some stress detection experimental products. And then that will inform the scientific roadmap that we'll develop from the project. So we have a number of pilot sites, which I described again earlier in the morning, and we are working in 3 sites. In Spain, where we're Andalusia, where we are looking at salinity, nutrient deficit in soils, and soil toxicity in rice farms. And also the second site we're working at is the Bonifice farm, where we're looking at wheat lodging. And finally, in much field data, we were looking at water stress in maize and summer wheat. And I think that's it. So that's our website if you want to have a look at the progress of the project. Thank you.
So thank you very much. Thank you very much to all the speakers. And what's amazing that we were able to finish on time with all these presentations. We have a few minutes. I mean, if somebody has some questions, I would be very impressed after such a long day and week. But if there are some, and you see that the speaker is still in the room, you are very welcome to ask some question now, if we still have a microphone as well. Tomorrow. Yeah. No, I will not push it. So if everybody is fine with closing down now, I just say thank you again to all of you who stayed here. Yes. And I think that we'll see most of you again tomorrow morning. Thanks a lot, and have a nice evening. Sorry. Okay, so there will be only one bus, and it will leave now at 45. Oh, yes. Jamie, thank you very much. And was the only one, no? Marianne as well. Marianne, thanks very much.